All right. Good morning, everybody. Welcome back. It's wonderful to see so many familiar faces and so many new faces. 21st Annual CubeSat Developers Workshop. It's amazing that we've been able to grow together as a community for so many years. Just quickly, it's always curious, how many is this first time at CDW? Excellent. Welcome. And at the other end of the spectrum, where's Kyle? Kyle's up there. We were talking this morning. He's been to all but one. Has anyone been to the same number as Kyle? Oh, how many have you been to? All but one, right? So we have a couple very, very familiar faces and a lot of new faces. Hopefully you'll have a good time this week, over the next couple days, mingling, learning a lot about what's going on with some of the CubeSat programs and some of the work that's happening in the industry, and just generally enjoying yourselves. My name is John Bellardo. I'm the director of the CubeSat lab here at Cal Poly. If you have any questions, logistically, look for these orange lanyards, right? The folks wearing the orange ones are lab members. And if they don't know the answer to your question, they can find me or find somebody who knows the answer to your question. So if you're lost or you have an issue with your booth or whatever, come find one of us and we'll help get taken care of. I want to point out that and thank our sponsors. This event would not be possible, being able to be in this beautiful facility and enjoying some of the banquet that we're going to have tonight would not be possible without all our sponsors. And this year, I have to make sure I get everything right here, sorry. This year, our presenting sponsor is Millennium Space Systems. We have gold sponsors of DHV Technologies and Blue Canyon Technologies. Silver sponsor Maverick Space Systems. The bronze sponsors are Leaf Space and Experior Labs. Most of our sponsors also have booths, so please stop by and chat with them and figure out if their products and services work for you. So can we please give a big round of applause to our sponsors. All right, their support is key year after year to continuing to host this. Okay, yeah, as I mentioned, a lot of good exhibits out in the main floor this year, so go and check those out. Our posters are on the second floor, so after you've talked to all the exhibitors or when all the exhibitors have a big long line, head upstairs, check out the posters. If you haven't been in this facility before, you're looking for views and it clears up a little bit, the weather is, a lot of times it's a little more sunny. Go up to the very top floor of the pack and there's a little balcony or patio on that end of the building on the top floor. I have great views of the area if you just want to catch some fresh air or something like that. So feel free to do that. If you are a presenter, you should have already uploaded your slides. You can check at the registration desk. There's a couple of laptops. You check in up there to make sure they have your slides. And then make sure you're backstage, about 30 or so minutes before your presentation so you can make sure you receive your instructions and things like that. So if you're a presenter, do that. Let's see. We have outdoor seating, obviously, for breakfast and lunch. There's also some seating inside the building, but please don't eat your food here in the main lobby, in the main auditorium. Right? Stay in the outside, hallways and whatnot of the building while you're eating. I mentioned that we're going to have the, we're going to have the networking dinner tonight. That's at Slow Brew. If you've been here before, it's the same spot as last time, or at least if you've been here last year or the past couple of years. If you haven't been here for 15 years, it's a different spot. Either way, Slow Brew, it's the Rock location. Slow Brew has a couple of locations here in the area. The Rock is out by the airport, so when you're mapping it, if it's right next to the airport, you're in the right spot. If you're not next to the airport, you look for Slow Brew, the Rock. And again, if you're not able to find it or you have any questions, see one of us with the orange lanyards and we'll help you out. That's going to start at 6 p.m. and it should be good. You do have to check in to receive your drink tickets and your badge. I know it's on my badge, yeah. Your badge should have a little knife and fork on there indicating that the networking dinner is part of that. For example, some of the one-day passes don't include the networking dinner unless it was purchased separately. So that's on your badge. Schedule updates. Our schedule is usually dynamic due to people's travel plans and things like that. Some people might not be able to make it. We printed the program out not too long ago, like Friday, is when we printed that program. but the schedule has already changed a little bit since then. We won't reorder your time slot, your presentation slots at this point, but I do encourage you to look at the website. The website's going to have the most up-to-date schedule. You know, if somebody had to cancel or somebody who's not on the schedule needed to be subbed in, that'll be reflected on the website. So please look there. There's also a link for the live stream up on the website in case you want to go back and you missed a presentation because you're out visiting with your friends or the exhibitors and you want to go back and catch one. You can do that as well. Okay, those are all the announcements. I'm excited. One of the things that I'm excited for, I'm always excited for our keynotes, but it took me like 8 years to find this keynote speaker, approximately, right? Why? Because he retired, was it 8 years ago? I forget, not quite. It feels like 8 years, maybe 6 years. He retired 6 years ago. A lot of you have at least heard of Jordy Puig-Suari. He's a aerospace professor emeritus here at Cal Poly, ran the CubeSat lab, the CubeSat program here for a long time. In addition to running the program here, he was instrumental in founding the CubeSat standard, right? So he and Twigs worked together to found this, all the way back in like 1999, right? So he's been part of the community for a long time. I'm sure a lot of you have interacted with him. He also founded TIVAC Nanosystems in 2011 to help provide some infrastructure and support for the CubeSat community. So with that, please give a warm welcome to Jordy. And I think this is his first time back in San Luis since he retired.
Okay, you can hear me. Awesome. Thank you, John, and thank you for inviting me. That was kind of a surprise. And it's actually the first time that I'm on this side of the stage and I'm actually presenting, which is kind of intimidating. I was always doing what John does and running around without like a chicken with no head trying to figure things out. And now I have to actually make sense, which is a lot harder. So I appreciate what the presenters go through every year. So it's the 21st workshop. That's quite a few. The workshop can join us for a beer tonight. And it was a very important thing, and actually it's even older than that because we started doing workshops in Utah at the SmallSat conference before we did this one. And it's a workshop that's specifically for CubeSats, and there's reasons for that, and it's very important because CubeSat is more than a standard, it's a community. And the fact that it's a standard creates the community because everybody has the same problems, everybody's fighting the same demons, and the solutions tend to work for everybody. So that's really, really good. And in those years, there's lots of stories, and I have many of them. And I thought initially that I was going to come here, and be the CubeSat grandfather telling stories, and we were going to have a good time. But I decided that no, if you want stories, Aaron Zuckerman is coming up with a new book. He's interviewing everybody. We're telling him the stories. He's going to put them together. I recommend it. Go for it. You want stories from me, maybe over a beer tonight, we can do that. But I want to talk about something else. This is a question that I've been asked several times in the last few years. Whenever I interact with the press, with lots of developers, are CubeSats still relevant? Do we care about CubeSat? And that makes me angry. I'm sorry. I have a personal attachment to this thing. I know I'm extremely biased. But today I decided I'm going to answer that question. Or I'm going to give you my answer and why. So why is that happening? Why do they ask this question? What's happening? So we started with 1U, and immediately people said, oh, I want more, 3U. And then NASA came and said, we want more, 6U, 12U. And now everybody's doing 500s and 100s, and it's exploding. And it's really good. And that's happening with, look at the list of sponsors, Blue Canyon, DHV, TIVAC. Everybody. VACO is out there, and they keep getting bigger. There's all these companies. The money is with bigger satellites, and I understand that. However, there's a thing that they don't tell you. Many of those players starting over there. Okay, they started with CubeSats. They learn, they made inexpensive mistakes. They all did. They won't tell you because their systems are extremely reliable now. They weren't when they started. They learn a lot, they gain experience, and then they move to bigger things. Okay? So now if you come into this new space community and you look at things and you say, oh yeah, the place to be is at 500 kilograms. Your mistake is going to be a lot more expensive than theirs. So be very, very careful, okay? There is things that you don't see if you walk into the room today. Things happened in the past that are very important. And one of them is that all those companies started with, some of them with 1U CubeSats. Terran Orbital, what used to be Tyvak that we started, has a 1U CubeSat in the Smithsonian. That was one of the first products they flew as a company. Now they're building 500 kilogram satellites and going to the moon. And they say that's what we should be doing, that's where the money is. But a lot was learned with those 1Us. So let's not forget that. So what did CubeSat do? And this is the nanosat, survey that the European put together that shows the trends in nanosat launches. And what that shows is that CubeSat started a revolution. And it was CubeSat. It was an AMSAT, it was in Surrey, it was in SpaceX, it was CubeSat. And I have answers for all those other companies not being the reason. If you want them, and we can do it over beer. But CubeSat started the new space revolution. And we've been very humble and very nice for many years, saying, oh, it was whatever, Bob and I started things. I've been thinking about this for a few years. It was CubeSat, okay? It happened right here. Actually, it's a little down the road. And the building is not there anymore. But that's where it happened. And it happened, Stanford, Bob and I, but it also happened at NASA Ames, and happened at Orbital Sciences, and happened at NASA Kennedy, and happened in Europe, and happened in Canada, and happened in Japan, and happened at universities all over the world with students doing amazing things that were not possible. And that's an interesting part of that revolution, is that over there, CubeSats were too small to do anything useful. Does that sound familiar? We need to go bigger because these things are too small. I've seen that story before. It didn't end well for the dinosaurs. Okay? So what are the key elements that make CubeSat successful? Number one, the CubeSat standard. The simplest, stupidest standard ever. Make it a box, stay within the box. You have no idea how hard that was, keeping people in the box. It was hard enough that Bob Twiggs, my colleague in creating this monstrosity, violated the standard on the first launch with the 3U, okay? And there were more violations on that one that we let him get away with because he was right there writing it with us. But that created a community. Everybody had the same problems. The solution that somebody found worked for somebody else because they were all the same. That was really good. But there was one more thing that we did. We had a deployer. There was a box. It's really, really high tech. I think they called it, inspired by this great invention called Jack in the Box, I think is what it's called. And that forced the standard. Immediately people wanted to go bigger, but they could only make it to 3U, and then that was it. There was a door at the end. And actually, these two things combined are, and I've come up with a name for it. It may stick or may not. They're core isolator. Cost, risk, and effort isolators. What does that mean? They save you from documentation, from analysis, from design. They keep the launch providers happy that if something happens to your satellite, you're not going to break everything because you're inside a box. You can go and buy the whatever solution that somebody else came up with because it will fit on your satellite as well. And that's the only explanation why CubeSats can be called low-cost launch opportunities when 50% of the mass is a box that you leave on the rocket. Okay, if you think about the way we teach spacecraft design, mass is king. You want to minimize the mass, optimize the system. And we created something that added 50% mass penalty, and it was low cost. Go figure that one out. Okay? I taught design, and I just figured that out recently that it's like, crap. That went against everything I was teaching my students. Interesting. That's still there. That isolation that the CubeSat standard provides you with the deployers still exists, even though people are building 500 kilogram satellites. The fact that the CubeSat provides you with isolation from the launch vehicle, from risk, from all those things, is still there. It starts to break down when you get big, like 12 U's. I don't know how much a 12U deployer makes sense, you know? Maybe we shouldn't do that. But in the smaller cases, it makes a lot of sense. And the truth is that if we want the 100s and the 500s and those guys to be as revolutionary as CubeSat was, somebody needs to find similar isolators. You need to figure out a way where it's easy, you don't have to redesign every time, you don't have to do the analysis every time. You go to the launch vehicle, you show up, you meet the standard, you go fly. And that's what we accomplished with CubeSat. What were the initial objectives of this thing? And there were two. Well, the primary was education. We wanted to train engineers. We wanted to train engineers because Lockheed and Boeing and all those guys said, we need people with hands-on experience. Nobody teaches integration and testing. There's all these things that are missing. And we said, well, somebody has to pay for it. We probably can do tech demos and test things in space and make those people pay for the missions. And actually, it worked really well. The thing that's more interesting than this was easy. It's easy to understand. It's easy to see. But there was something else that happened. There were surprise results that we did not expect. CubeSat is an entrepreneur creation machine. I've never seen that happen in the space industry. I've never seen that happen anywhere, where you go to a university and you say, hey, build a CubeSat. And a bunch of students build a CubeSat, and within a year, they start a company. And that happens all over the place, okay? Tyvak, Mavericks, Astro Digital, the Europeans, ISIS, GomSpace, Nanoavionics, all of them, Acciona. You know, there's all these people, ISAT, Satellogic. There are all these companies that a bunch of students, Planet. There are all these companies, a bunch of students build a CubeSat, and they go and start a company. And you know what? And the companies actually work. How the heck did that happen? I think part of it is that if you build a CubeSat, you understand the complete system, which in the space industry, if you go work on bigger satellites, those 100s and 500s, it's very, very difficult. So to be a person that can start a company, that can see a whole satellite before, you needed 20 years of industry experience. Now, people got it when they got out of college. That was a complete surprise to us. The other one is that it became an entry point for new players. And by new players, I mean people that were not in the space industry, students from computer science, EE students, countries that had no business freaking building satellites. And now they're not just building satellites, they have companies that are successful. South Africa has attitude, determination, and control, top-of-the-line companies. That shouldn't happen, you know? Well, it does. I was talking with Aaron, and he said that the latest count is something like 40 countries that their first national satellite was a CubeSat. And I just realized, it's like, wait a minute, there's been 40 countries that have launched CubeSat. There's more, because there's the ones that it wasn't their first satellite. So it's nuts. And then there's a bunch of companies that came in, not just the ones that the students funded because they had done satellites. There was a lot of companies that say, I'm going to start by selling my products to the CubeSat. The HV, Blue Canyon, their first products were components for CubeSats. Tyvak, Acciona, Phase 4. And it goes on and on and on. And then there's the companies that use CubeSats to test the technology so they can do bigger things. Planet, Satellite IoT, Kepler, I think they did as well. There's all these companies. The first test is a CubeSat, a 3U, a 6U. We're going to check, everything works, awesome. And now we're doing 100s, we're doing 500s, which is totally fine. But we didn't expect that. That energy that the CubeSat community created at the entrepreneurial level was a complete surprise. And people have forgotten that that's where that spark started, okay? That started before VCs. I mean, these students, they were crazy enough to go start companies before it was like, oh yeah, if you want to start a company, you go to Silicon Valley and they'll give you money for space companies. No, these were even crazier students than that. They said, there is no money, but I'm still going to do it. And they succeeded. Whatever. Okay, so what's going to happen moving forward? And this personal opinion, extremely biased, of course. The innovators will be trained on CubeSats. Some of them are in this room. Some of them are having coffee outside. Some of them are at universities all over the place. There is, some 20-something kid in Southeast Asia, and he or she has an awesome idea, and he's going to blow our socks away. And that's happening right now. Those innovations will be tested on CubeSat. It will be a university mission, it will be a low-cost mission, it will be something simple that somebody will go, they'll prove something, and it will blow your socks away. Because it has happened before. And those people will become new players, and there'll be new countries and new companies and new institutions and new everythings. But there will be some that don't start that way, I agree. I'm not saying everything will be CubeSats, but I'm thinking that will still happen. And that's the other one that I'm counting on. Technology will continue to make sure that we can do more than we think we can. Okay? When we started, the idea of doing imaging with a CubeSat was nuts. No, you cannot do that. And I think there is some vortex of the universe where physics has changed, because the things people are doing with CubeSats today, when we started, and I'm not a physicist, I'm not an optics guy, I was told the physics means you cannot do this. And now it's being done. So I don't know if the physics has changed or somebody came up with a really clever idea. Probably a clever idea. I still have some faith in science. So that's going to continue to happen. There'll be things that are impossible that will be possible. So let's watch that space. You cannot go interplanetary because radiation will kill everything, so you cannot do CubeSats outside low Earth orbit. What the hell happened in Mars a few years back? Yeah, what is this thing around the moon that's been testing some crazy orbit? I don't know. That crazy orbit test was probably the same price of the simulations that we would have done on the ground to test that orbit thoroughly. So that will continue to happen. So what's my answer? Of course, Yes, CubeSats are still relevant. Okay? They're not the only ones. They're not the revolution anymore because there's more parts to that revolution. But by golly, they are relevant. And ignore the community at your peril. It was done before. No, they cannot do anything. They're too small. It's not useful. Boy, were they wrong. Be careful. You may be wrong again. So just to all those companies that are saying, I'm moving bigger. Awesome. Move bigger. But maybe keep an eye for that little kid in Southeast Asia that's doing something new, because they may kill your company in 10 years. Okay? Final thoughts. And this is mostly for the students, because I know there's lots of you here. Leverage the standard. There's real advantages to using the standard. It really makes your life easier. And that was the whole point. It's an isolator. It protects you from a lot of paperwork and a lot of testing and a lot of analysis that you don't have to do, because it's just a CubeSat. Everybody understands it. It's going to go in the box. Does it fit in the box? Yes. Let's go fly. Okay. Did it pass some very simple tests? Yeah. Go. Now build a 500-kilogram satellite. You can do more, but they're going to watch you a lot closer, and you're going to spend a lot more money. So just be careful. Leverage that. Engage with the community. That was one of the things that at the beginning was incredibly effective. There's a little bit more competition now because there's money to be made and all that kind of stuff. But the community is a very powerful thing. Everybody has the same problems. Everybody's looking for the same solutions. And the solutions that somebody else finds will work for you fairly easily. You don't have to redesign everything. You don't have to optimize everything. You can get an ADCS system for $120,000. If you want to design your own magnetic system that points 100 times worse, you'll spend more money than that. I can tell you that because we tried. Continue to question the experts, and I put myself in that category. Okay? Listen, but don't trust but verify kind of thing. And I'll give you one quick pointer, just a quick one. If you ask somebody, why do we do this? And they tell you because we've always done it this way. Stop listening. Okay? Because they're wrong. So ask yourself why. If you cannot answer that question, you should go think about why. And if the answer is because we've always done it this way, that expert is not worth your time. And of course, never forget to have fun. Okay? I had a lot of fun doing this. I still play the CP2 or CP4. It was CP4 beacon, and it gives me goosebumps. Okay? And you can also have that if you get one of these puppies upstairs. And that's it. Now, I think I have some time for questions, if there are any. Thank you.
Right. Thank you very much, Jordy. Again, welcome to CubeSat 24. Thanks for being here.
Thank you.
It's a pleasure having everybody here. All right, we have our traditional post-keynote break. The sessions are going to start at 10:20. So we'll see you then, back in here.
Awesome.
Thank you.
Thank you.
Unless you have questions, you can also take questions for Jordy. Sorry.
Carl has a question. We're in trouble.
You can stay for questions as well.
Oh, you give it.
What's the aerodynamic efficiency of your sail?
It's not very good. It's not very good. And I hated aerodynamics. That's a funny story. We can talk more about that.
Did you tell them you sailed, Jordy? Do they know that?
No, I think we're good. But yeah, I'll be around all week, so let's chat and yeah. we'll figure things out. Oh. So just speak loudly.
Yeah, so we're pretty much brand new to this whole community.
Okay.
We just got selected by CSLI, thankfully, and we're just wondering what's the best way to actually engage with the community.
You're here.
Oh,
Okay. The question was, what's the best way to engage with the community? They're just starting. Being here is the best way to engage with the community. And just talk to everybody, listen to everybody, make contacts, ask questions, question the answers.
Other questions?
What was the origin of the name Tyvak Nanosatellite?
It was the cool name. It sounded good. Literally, fair enough. There was nothing behind it. It's a very bad choice.
And you forgot the most important thing. The domain name was available.
And the domain was free. Yeah, that was very important.
Other questions?
Okay. People are still waking up.
Yeah, it's early. All right. Thank you very much.
Thanks, everybody. I need to get it.
Welcome back. I hope you all enjoyed the break. I know I had some good conversations up there. Since this is our first presentation, I'm going to give you a quick little procedural overview. So we have 20-minute presentations. That includes questions. If the presenter goes the full 20 minutes, we won't have time for questions. If it's short, a little shorter than 20 minutes, feel free to ask questions. And so what will happen is before each presenter, one of our lab students will introduce them, and then they'll have the stage. So welcome back. And Jackie, please.
All right. So let's welcome our first speaker, Ben Bradley from NASA Ames Research Center, presenting Biosentinels.
Where's the speaker?
All right, hello everyone. Stairs over here. So as they said, my name is Ben Bradley from the NASA Ames Research Center, and I am here to speak with you about Biosentinel, Deep Space CubeSat. All right, so first up, what was Biosentinel for? The primary goal of Biosentinel is to have a way of sending biology into deep space and having that biology be exposed to the deep space radiation in such a way that is relevant to humans. So we are sending a model organism of yeast, which is conveniently a eukaryote, same as you and me. It has this DNA repair mechanism that evolved once in eukaryotes, and the yeast is able to, when it's exposed to deep space radiation and has its DNA damaged, it repairs its DNA in the same way that our cells will. So in this way, it's a good model organism, and also nobody gets upset if it doesn't come home. Additionally, the secondary goal was to test out the technology on CubeSats to go out into deep space. We launched on Artemis 1, we'll get there in a little bit, and then also we're collecting radiation data to compare against the Earth analogs that we create and test against. All right, so our current knowledge, or prior to Biosentinel's launch, of eukaryotes and life in general in Earth, outside of Earth in space, goes in two general bars. You have the long term there on the ISS in low Earth orbit, and you have approximately the length of the Apollo missions out to the moon, and that's it. There haven't really been any other biology missions that go into the big black unknown area. And if we want to go and send people to Mars, we would like to make sure that we're able to provide them with the appropriate level of radiation shielding. So big point of Biosentinel is figuring that out. Now, Ames has a history of working on a variety of different biological payloads. You don't need me to read all of these to you. Just know that Biosentinel is a continuation of a lot of the technologies that we had been developing for previous missions. Most of them are low Earth orbit. Biosentinel is unique in that it was going out into deep space. And also it was using yeast as opposed to some of the other organisms that had been previously used. I know it looks like I'm plowing through these things, but there's other fun stuff coming later. So a little bit more information about the yeast and the space radiation environment. So our scientists took a bunch of yeast and stuck them in particle accelerators in order to prepare them to understand what was going on this mission. The particle accelerators, though, are not able to replicate the deep space radiation environment. They are too low flux, or rather, they're too high flux. It's a low flux environment out in space, and the duration is off. It's very expensive to run a particle accelerator, so we can't leave them out there for months and months and months like we would if we were in space. So the yeast that we selected, like I said, it's a eukaryote, easily to genetically and physically manipulate. We sent out 2 strains of yeast, what I like to refer to as the science yeast, and what the scientists refer to with the fancy Latin name that they have up there. I'm just a project manager, I'm not a scientist. So in general, we had 2 strains of yeast. One, it was the wild type. It was the normal yeast, the normal kind. The other one had that DNA repair mechanism that I was talking about intentionally broken so that we could observe the differential growth rates. The one that was repairing its DNA, we hoped would grow better, and we'd be able to see all of that in the data that came out of the spacecraft. So, onto the hardware that implemented all of this science. It's Biosentinel, 1 mission in 4 parts. We had the free flyer unit, which you can see up there in the anechoic chamber with the nice guy checking out its solar panels. And then we also had a few control experiments. One of them was the ISS unit. You can see it bottom center up there. It's our golden boy who was installed up on station. And you can see an astronaut putting it into a Sable up there. It was temperature controlled, and we were able to get power and data to it. And then we also had Earth-based analogs in order to ensure that we had the control data from being on Earth. We grew all the samples once of the yeast and divvied them up and put them into these various different areas. So you can see there's a rocker thing on the ground. It's sort of our lo-fi way to make it resemble microgravity in that the yeast just isn't going to settle into its wells if it's rocking back and forth all the time. Now, to give you a sense of scale, there on the ground segment, you can see 2 biosensors. That's where all the science magic is happening. And each of those is for you in our 6U spacecraft. So moving on, we have the blowout diagram of how Biosentinel was constituted. So you can see the large biosensor right there in the middle. And that seriously is taking up 4U of our 6U spacecraft, which means that we have 2U left for the spacecraft part. The one other thing that becomes relevant later, the LET radiation sensor, it's a spectrometer that detects the solar radiation information so that we know what the yeast are being exposed to. Now, overall, because we had to cram an entire spacecraft for a 6U mission into a 2U bus, we did a lot of creative engineering on our own. We had, I was just speaking with the people who were working on the electronic systems, and they were arguing for millimeters as to how big their battery packs could be. So that's the kind of tolerance that we were looking at. One way we were able to save some space is by 3D printing our propulsion system in-house. So a university student had designed it, and then we hired him, and he was able to design and print the 3D propulsion system. In there, we also have the Iris radio from our colleagues at JPL. We have our attitude control subsystem, which we purchased from Blue Canyon. And the solar arrays, you have the 2 gimbaled arrays plus the 2 flat arrays that fold down flat against the body. And then if you take a look over here at the microfluidics system, you can see a bit of how we implemented the the yeast detection system. So we launched with the yeast in these wells. It was desiccated, and when it came time to grow the yeast, we would pump a combination of a nutrients fluid and also the dye Alamar blue into the well. And you can see each well is about 3.5 millimeters wide. The fluids would go in, it would wet the yeast would start to grow, and we had an LED emitter board on top and a light detector board on the bottom, and we were able to determine the yeast growth rate based on a combination of the color that was transmitted, because Alamar blue changes colors to Alamar pink. It's not actually called that, as it goes through yeast metabolic processes, and also it would just become more opaque as it grew more. And then we had two banks of 9 of those cards, and that's what made up the internals of the biosensor, along with the bags for the fluids and desiccant and all of the associated pumps, etc. So we launched on Artemis 1. It was very exciting. You can see there, Orion is departing the interstage from the second stage, which we were attached to. You can see some CubeSats in there. None of those are Biosentinel, sadly. Those are some of our sister payloads that also launched with us. I believe it was 10 that actually made it onto that rocket. And for being a secondary, it was also the first flight of SLS. We found that we had to comply with perhaps more requirements than is standard on a normal rocket that we're used to. That said, we persevered and made it into space. And here we get to see a fun video of what the deployment looks like. You can see Orion's going off. It's going to do its thing around the moon. And then we come back to the second stage, and we can see how it is totally calm and not spinning and not tumbling and just gently ejects everything to go along their way, which is totally not how that happened. So, bringing us to the next slide, trajectory uncertainty, keeping paraloon altitude positive, in that we didn't want to hit the moon. There was a possibility that when we were going on this mission where we knew that we were going to be slingshotting around the moon, that the slingshot might be slightly problematic and that we would hit the moon. We decided a roughly 10% risk of that was fine. This is what our trajectory people said was going to happen until they got the actual launch dates. And then they came back and said things like 30% and 50%, and we didn't like those numbers. So we asked the classic question, not of what is the system designed to do, but what is it capable of doing? And I mentioned earlier that guy that we hired for the 3D printed propellant system, that was primarily for momentum management, because you can't use magnetorquers in deep space. He installed a center mass valve and thrust assembly on the propulsion system. We said, why? There's no requirement for that. He says, well, you never know. And then, like good project managers, we said, fine, we're not testing it, though. And then we launched and found out that we might need to use it after all. So we did a whole lot of analysis in order to find out what the performance of it could be. And we had a wide variety of solutions ready to go. Fortunately, the spinning, tumbling system ejected us into a orbit that would not hit the moon. So we didn't need to implement any of those contingencies, which we were all thrilled with. That said, we did have other unexpected contingencies happen. Well, I say unexpected. The launch was delayed a bit, so we had time to think of more contingencies than we would normally. And one of those contingencies we thought about later is one that came to play out. So after Biosentinel was ejected from the upper stage, it was tumbling around as expected. However, its tumble rates were higher than we had originally planned for, and the pre-scripted detumble routine that was supposed to get our solar panels pointed at the sun did not accomplish its job. So we had our very first, and what DSN was telling us was our only pass in order to make sure that we could talk to the spacecraft, and it was a very busy day for DSN. They didn't want to have a bunch of small sats go around and bother them about passes. So we were able to get our one pass, and the low gain antennas were, I mean, they're Omni, so we were able to talk to it just fine. It was tumbling and tumbling and tumbling, and it wasn't going to stop tumbling. And a fortunate thing for us, since we designed the bus and we designed everything about how it operates, we had the people who designed it in the room as the operators. So we were able to look at the battery expert and said, how long do those batteries have? He looked at his voltage rates and said, it got 2 hours. All right, when's the next pass? Next pass, 5 hours. Which is a bad number, because if we freeze the biology, it's dead and it can never work. So we did a bunch of very quick negotiations, and with a lot of thanks to one of our sister payloads, got one of their passes for a transmit only. Now, because Biosentinel had been in Florida very recently, it had not had a chance to cool down to its operational temperature. And the operational temperatures were intended to be a lot lower. It was too high, so we were able to only transmit to it. We were not able to get a transmission back because the radio is very warm. So we had to transmit this code to fix the detumble system. We sent it up in the blind, and then had to wait for 3 hours in the middle of the night to find out if it worked. The fact that I'm here talking to you about a successful mission tells you that it did, and the high energy and high stress situation ended up paying off. So well done to the team. And now I say successful. Unfortunately, all of our yeast was dead by the time it reached space. Biosentinel was designed to be stored for about 6 months at 5C and was instead stored for 18 months at Florida ambient temperatures. And the hardware that we built to move the fluids around, that all worked. And then we started getting some anomalies saying that there were shorts in the system telling us that there was a very humid environment in our sealed container. So that told us that our desiccant was saturated. We saw the same thing on our ground control system for this. So honestly, it was just the amount of time that we were sitting out. That said, we still have that LET spectrometer, and it's still collecting good data on the current solar maximum. So the sun doing a bunch of stuff right now, got solar flares all over the place. And Biosentinel, I'm going to go to this video. As you can see, it will progress. Biosentinel ends up in an orbit where it's basically by itself. We don't have any other solar radiation sensors out there. And if you take a look at stereo ahead, that used to be part of 2 missions, stereo ahead and stereo behind. Well, stereo B is sadly no longer with us, but Biosentinel, albeit in a much more limited capacity, has sort of taken up residence where stereo B should be for this. So we have a little bit of data to compare against stereo A, and it is helping our colleagues in the heliophysics department gain some information on the current solar maximum. So what's next? We have a project called Leia that we are working using the same biosensor type technology that is going to go on a CLIPS mission to the moon, and it will be up there for a lunar day. It will expose everything to the radiation there. Basically a very similar mission to Biosentinel, though the organism that is being used is different. And I'm looking over at my biology colleague to make sure I'm saying true things. And that is it. They haven't showed me the 2-minute sign yet, so I think we have a moment for some questions. Yes? What was the procedure for handling the biological payload when we were assembling the satellite? So when we were assembling the satellite, we had a hood that we had all of the biology under. So we grew the yeast. Our scientists grew the yeast, and they did it in their science lab, doing it the science way. And then they handed it over to the people who were building the biosensor. And it was a positive pressure hood to make sure that no contaminants could get in, sanitize your hands and wear gloves and everything. And at part of the encapsulation process, we had the scientists there observing the process to make sure that we were following all of the safety rules, that we avoid contamination. And then once it was encapsulated and the biosensor was put together, then it was a hermetically sealed box, and we no longer needed those precautions. Sure thing. Anyone else? Yes, we have one up here, and then one up there. Yeah, so you're asking about mitigation strategies for a future launch delay. It's tricky with biology because biology likes to be treated a certain way. In future cases, ideally it would be late load. We grew our samples in 2019 and then proceeded to have a pandemic where nothing happened for a while, except for the inexorable march of time. So that aged our samples. One thing that could be done in order to improve this specific design is add more desiccant to it. It would take up more space, but it's the humidity that we think is what did our yeast in. Yep. And last question, I think. Was it the ambient humidity that penetrated the sealed box, or was it something else? We have bags of fluid in there. It's the nutrient fluid in the Alamar Blue solution that I mentioned earlier. So in order to feed the yeast, we needed the fluid to be there in a liquid state, and then we had our microfluidics pumps that would move it around. So it was, our seals were slightly less than perfect. This was a known condition, and we put the amount of desiccant in there per our design specifications, but then we exceeded the design, and the desiccant became saturated. All right, and I think I'm out of time. That's it. Thank you very much. If you come to the NASA area, you can get your very own Biosentinel flat print, and you can build your own, probably faster than we built ours. Thanks, folks.
All right, thank you to Ben Bradley. Next up, we have Jaejing Lee from the Korea Astronomy and Space Science Institute, who will be presenting the Snipe mission, Formation Flying Nanosatellites for Small-Scale Space Weather Research.
Good morning, everyone. So it's my honor to talk about our Snipe mission. Snipe stands for the small-scale ionosphere and magnetosphere plasma experiment. And 2017, I introduced about the Snipe mission here. Today, I'm going to report about the initial result of a Snipe operation. Snipe is a CubeSat constellation. So each spacecraft has 6 use size. And so each spacecraft has the same payload, the Langmuir probe, solid-state particle detector, and magnetometer. These instruments measures space weather phenomena such as electron density, temperature in ionosphere, magnetic field, and energetic electrons. So if we use this, just a single satellite, then we have some problem in identifying spatial and temporal variation of such the small-scale plasma structures. So we developed 4 spacecraft, and we change each satellite distance by formation flying algorithm. And Snipe launched this last year in Korean launch vehicle. With such kind of operations, so we will do this kind of the small-scale space weather phenomena. So such as the electron microburst, plasma trough, black patches, ionospheric bubbles and blobs, and field-aligned current. All of these are small-scale plasma structures at the low Earth orbit. And this slide describes about the Snipe bus system. Snipe spacecraft has 3-axis attitude control system, and so they have the very excellent microprocessor, and also they have the deployable solar panels that generate about 44-watt electric power. And for the communications, we have two communication channels. One is the UHF, the other one is S-band. Actually, experimentally, so we boarded the Iridium communication module, but I think that it is not work now. And for the formation flying, so we have 1.5U thruster, which one is the cold gas thruster produced by Beko. And this figure shows the flight model of a 4 spacecraft. So actually, so we completed the integration of a flight model at the end of 2021. So we launched the 4 spacecraft 2023. So almost 1.5 years. So we did test, but I realized that the test could not be enough. Actually, just even a night before leaving to the launch site, we tested our spacecraft, and this picture is our team members just after we changed flight software. And this picture shows the deployer, and so we are putting our spacecraft into deployer. And then analysts, last year, 25th of May, we launched the 4th spacecraft by the Korean launch vehicle. And so, but Snipe B is, as you can see, Snipe B successfully is separated, and Snipe D also, so we can get the pictures, the separation of spacecraft. But unfortunately, another side, the Snipe A and Snipe C cannot take a picture. So, but and unfortunately, Snipe C was not separated from launch vehicle. So now, so we have 3 spacecraft on orbit. This one is our result, the measurement results. So first, Langmuir probe. Langmuir probe instrument is measuring the current and voltage on the ionosphere. So you can see, so we got this a very nice IV curve. So on the top right, from this IV curve, we can derive the electron temperature and electron density. And this one is the result. And so as you can see, we successfully observed some ionospheric small-scale structures, such as the F-Litton anomaly or the morning overshoot of electron temperature. This data shows the magnetometer measurement. Actually, so at the time, so our spacecraft very slowly rotate so with respect to y-axis. So red one red line shows the y-axis magnetic field. So you can see it's the very slow variation, while the x-axis, g-axis has faster variation. This result shows the solid state telescope data. We can measure the very successfully energetic electrons. So as you can see in the left-hand side, so as you can see, we can measure the energy dispersion around 100 keV electrons. And so this result is very similar to the Van Allen probe measurement data. So we are very happy with this kind of data. And then I'd like to talk about the formation flying. So actually, so many people interested in this kind of formation flying. We plan to do two different kinds of the formation flying. First one is the along track formation. Along track formation means the all spacecraft on the same orbit plane, and we control each spacecraft distance, see, like this. So you can see the each spacecraft distance closer and closer. Our target is decrease the satellite distance to 10 kilometers. Yeah, which already is ambitious. And after along track formation, we do cross track formation. Cross track formation means we separate each spacecraft distance with respect to longitude. So we can do observe temporal variation of space plasmas by along track formation, while we can observe spatial variation of plasma structures by cross-track formation. In order to do formation flying, we need a thruster. So we adopt cold gas thruster produced by Veco company, and we use the propellants of the R236FA. And so the size of thruster is 1.5 U. It's not small in the CubeSat. The mass of propellant is 1.2 kilogram, and with such kind of mass, we can get the del V of 50 meters per second. And we need another the performance for formation flying. That is the attitude control. So this slide shows how we do attitude control. We upload this command to orient some directions with the quaternion coordinate system. So at the time, so we command oriented to the quaternion 0.5, 0.5, 0.5, 0.5, and then as you can see, the measured quaternion converges to the 0.5, 0.5, 0.5, 0.5. So successfully, so we can control the orientation of our spacecraft. And this slide, this video clip shows the current orbit of Snipe mission. We have 3 Snipe spacecraft now, so 2, 4, and 1. Unfortunately, so we have some problems in Snipe 1. Actually, so power issue, actually. So we cannot operate normally with this Snipe 1. We can just temporarily communicate with Snipe 1. So we are trying to changing the Snipe 1, Snipe 2, and Snipe 4. So now the Snipe 2 is much faster than Snipe 4. Snipe, Snipe, yeah. So we have to make Snipe 2 speed slower. How we do that? To do that, so we have to increase the altitude of a Snipe 2. And this one is the result. We fired 3 times of thruster, and the first one, first firing, so we failed because we failed to orient our spacecraft attitude. But the second one, third one is successful. As you can see, we increased our Snipe spacecraft altitude about 0.8 kilometer, so for each firing. So totally, so we increased our spacecraft to 1.6 kilometer, and then I believe that we can almost the same make almost the same altitude with the Snipe 2 and Snipe 4 if we fire twice. So now we are trying to such kind of operation. So summarizing our Snipe mission's status, unfortunately, so we have power issues of Snipe A, and so we also have some problems with the star tracker and so reaction wheel moment dumping. However, so anyway, so now so we are trying to control the distance between Snipe B and Snipe D. This one is the last slide. Then, so why such kind of operation is important? If several spacecraft on the same orbit plane, then the Earth is rotate, and each satellite pass over different location. And then, if each satellite has their own downward the Earth images, then so we can integrate all images, and then we can make the large field of view imaging. And this kind of operation is very useful for surveillance or reconnaissance. So now our ongoing project is the space scanner. And so space scanner has EO/IR camera, and not for space weather instrument. And so for more information about our payload, so please don't miss this third 20 today PM the presentation. Thank you. First.
Thank you for a very interesting presentation. When you operate a propulsion system, it looks like you operate over a day or so. Is that correct?
Day?
The propulsion system?
Yeah.
You operate for 1 day to increase the orbit altitude?
Yes, we fire, the operation time is about 20 seconds. yeah, just the parts actually. So, yeah, actually, so big issue in operating propulsion system for CubeSat is the CubeSat is small and very quickly rotate. So, so yeah. Actually, so our propulsion system has a four thruster, and so we control each one. So combination actually. So, but such kind of combination cannot be continued a long time. So yeah, maybe 20 seconds would be some maybe yeah proper time actually. Yeah. Pardon me. For Snipe A. Yes, we don't know exactly, but they have they generate enough power actually. So maybe some solar panel issues. So maybe we have the fourth solar cell string, but maybe 2 or 3 solar cell string has some problem, actually. So we can see. Actually, so the solar cell generates the enough power. That means they do not generate the enough current. Yeah. Yeah. Your question is about this slide? For any of the slides. I'm wondering if the laser probe is taking 50% of your power budget, 75%. How much do you think it's taking? Your question is about the power. Actually, so our satellite has the spatial orbit dawn dusk. So we can get the our spacecraft can view the sun 24 hours. So actually, so our spacecraft has no serious power issues. Even if we have some problem with the attitude control, actually, yeah. Okay, thank you.
All right. Thank you, Jae-Jin Lee. So let's welcome our next speaker, Steve Dunton from Cal Poly, presenting Space Duck 2024, The Final Frontier.
All right, hello everyone. My name is Steve Dunton. I'm faculty here at Cal Poly. This is your first time here, welcome. If you've been here before, welcome back. It's good to see you. This morning I'm going to talk about Cal Poly's multi-year collaboration with a startup company called OWL Integration to fly their radios, which they call ducks, in space. And so this talk is called Ducks in Space. This briefing has a lot of pictures in it. A picture's worth 1,000 words, so not so many words. I will provide some of them. I won't provide 1,000 per picture, but I do want to talk about what you're seeing on this cover chart. So, oh, and my contact information is at the bottom. On our path to flying in space, we've been doing high-altitude balloon testing. That tends to be an annual event with our students. That's a good culminating event. And so the photos you see are getting ready to launch a couple on balloons, high altitude and higher altitude. Oh, that has a typo. I'm sorry. We did not achieve 900,000 feet. We achieved 91,000 feet on our last flight. So definitely high altitude and suborbital, but gives you an idea of our radios, which we call ducks, what they can achieve. Our mission is primarily line of sight, but you don't always have line of sight, and so we want to have the ability to close the link through a high altitude node or potentially a node in space. So the background with OWL, OWL stands for Organization, Whereabouts, and Logistics, and they form mesh networks with low-cost radios. So radio A can talk to radio B, can talk to radio C, and that way A can get data to C, or D, or E, or F, or Z. And their mission is to provide communication infrastructure where it does not exist, either because it was never there or it's been destroyed. And so they have, they came out of a hackathon effort in 2018, I think, when there were multiple hurricanes, Atlantic hurricanes that did significant damage to infrastructure, and most significantly Puerto Rico. These things work great when there's a cell phone tower in range. But when the tower is knocked out and it takes a year to replace the tower, then you need some other way to communicate. And so their radios, which they deployed in Puerto Rico, you can connect via an app on your phone and then send text to those radios, and they could relay data across the island. And that provided a method for connectivity. There are also applications for oil exploration as well as monitoring. We have a grad student who's working to integrate a methane sensor. One of the problems with methane and stopping methane emissions at oil refineries or remote locations is merely detecting it. It's hard to detect an odorless, colorless gas. And so we're looking at these as a way to integrate that. We have another grad student who's working integrating them with sonar detectors underwater and then relay the data above ground. There are disaster relief, FEMA-type organizations in other countries that we've supported. California, we deal a lot with wildfires, and so how does the firefighter communicate back to the battalion when the cell phone is down? And they have radios, but the goal for OWL is to be a low-cost radio. So our price point that we're working to is $50 per radio. And at that price point, the radio becomes almost disposable. And of course, the Department of Defense is interested in this technology as well, because defense often operates in areas where there is not existing comm infrastructure. So again, these are low-cost handheld radios. We support up to 2.4 kilobits per second. So you could do voice. We currently do text as our primary application. And what else I want to say? Oh, and these are based on LoRa, on the LoRa waveform, some of you might be familiar with, and the network protocol that provides the mesh after the duck radios is called the cluster duck protocol, which got me interested in this project when I had a student working for them. Let's see. We are currently under phase 2 funding from AFWERX and AFRL, and it is wonderful to have funding. Such an enabling thing. And we're able to have a number of students working on this, and we are actually having students. We have a grad student leading this effort. We are iterating their hardware design for them. So it's a close multi-year partnership with OWL, which makes duck radios. You may have heard, right, Cal Poly, our motto is learn by doing. So this is primarily a student effort with faculty advisors. We have over 20 students who are currently working this, primarily in EE and Aero. I mentioned the master's projects. We also have multiple senior projects. Seniors are required to have a culminating project experience in order to graduate, and so we have a number of projects that students are working on here. And we are also preparing for to fly in space, and so we are going through an environmental test program. I think that's been great for the PolySat here. We are basically providing, training and pathfinder activities, operating the thermal vac chamber, getting ready to go to vibration with our electronics. We have a current version of the electronics that we're going to test this spring. We're iterating over the summer, and then our final flight version we will test in the fall. Let's see. I think I pretty much talked about that. Oh, I have this possible advanced OV1. Again, this is primarily a line of sight radio, but you don't always have line of sight. And so we'll fly another balloon this spring. That's what we call Space Ducks. That's a nice event. But we also looking at having aircraft. We have a plane. We'll have a drone and try to see how many different nodes we can connect in a scenario planning situation, a real life situation, and that our customer is going to use that for their work with AFRL, who is also interested in putting these radios on drones. Again, at this rate, you could support, you can't stream video, but you could support telemetry and command, things like that. We're also looking at evolving the hardware. This hardware started as just commercial, and as we all know, commercial pretty much means Chinese electronics, and there's a certain reluctance in the United States government to be dependent on Chinese electronics. And so we are evolving the design to use domestic or at least allied resources. Currently have some chipsets from the UK, Japan, France, and we are migrating toward really a trusted source for our supply chain. Additionally, we are currently single waveform. We're using the LoRa waveform, and we want to have the ability to support multiple waveforms, and so we're looking at some of the low-cost software-defined radio applications. And one of the lies, in my opinion, of a software-defined radio is that they are actually software-defined. Most software-defined radios aren't truly software-defined. They're application-specific ICs that implement functionality that then's parameterized, and so you have the ability to select parameters, but not necessarily truly software-defined. And we have this low cost point, but we're looking at what's out there. We're currently exploring a Lime SDR and seeing our ability not to only replicate the LoRa waveform, which is in an ASIC, but also our ability to generate other waveforms. So that's future growth. Let's see. So this is a graphic of our overall roadmap, and as I mentioned, we really just started with commercial electronics and trying to test range, high altitude balloon testing. We later started testing at Cal Poly in the lab, and we believe we were able to demonstrate 850 kilometers of range. That's a challenging thing to demonstrate when you're simulating range with attenuation, because we needed 100 dB of attenuation. And so that really became an EMI exercise for the students who are working on it. How do I know that the signal I'm measuring is actually the signal going through the attenuator and not a leakage path? And so we built custom Faraday cages around it. They learned all about how to wrap and terminate shields on cables and things like that to try to get us that kind of isolation, and did error rate testing, and we're able to achieve a reasonable burr for these radios at simulated great distance. Of course, we're low data rate, so it takes a long time to collect statistically significant data in 1e minus 6 when you're only sending something on the order of 1,000 bits per second. So one of the things we've been doing is automating our testing, coming up with not a full burr test, but quicker functional performance testing that we can use in laboratory settings and in field settings where you don't have the opportunity to run a performance test that takes hours to run. Let's see, we've also been helping them I'm understating this, but there's a fair amount of firmware that goes with this that our students have also been involving to improve their network performance. So this year, the last column under our phase 2 funding, our automated test is about done. We're going to do Pathfinder environmental test. We have also integrated, well, we're in the process of integrating our antenna into our board. So if you have a CubeSat, we could be a hosted payload. We could maybe even be your TNC at 2.4. We will have an antenna on one side, our electronics on the other side. And if you provide bus power, could be unregulated, then we don't need to fly a battery pack as well. And so we're changing our form factor from this long, skinny handheld to a 1U so that we can fit. We'll environmentally test that. And we'll do these demonstrations like you saw the scenario on, fly on an aircraft, probably on a drone, certainly on a balloon. And we have been on a path to fly on the space station with nanoracks. But Cal Poly has this wonderful CubeSat program, and not every CubeSat is fully populated. And so we're looking for an opportunity. We may be able to onboard even one of the current missions and get a launch in space. We would fly receive only, and so we don't have to worry too much about the power. We'll transmit for the ground, but if we're able to achieve that on this upcoming mission, then we're much closer than we realize to finally flying ducks in space. Okay. That was my last slide. Any questions? Oh, thank you. Yes. I'm sorry. Yes. Yeah, the question was, is an omnidirectional antenna? And I was just talking with a student who is doing the antenna this morning, because I told him I wanted at least 180 degrees out of the antenna. And it's by the way, so we're operating at 915 megahertz in the ISM band, and I looked at the antenna patterns. It is roughly omnidirectional. And on these CubeSats, we don't have a lot of attitude control. The mission we're targeting will have some degree of attitude control through hysteresis rods, but we can't count on a high gain antenna that we can appoint. So it is omnidirectional. I guess, so yeah, thank you for that question. Just another comment that I wanted to make, and is, because I see we have some midshipmen here, I see some folks from the Air Force. From the warfighter's perspective, when you perform a mission and you need a pace plan for your communications, you need primary, alternate, contingent, emergency plan for how you're going to communicate. This is not your primary communication path, and it's maybe not your alternate path, but a $50 radio that has line of sight that could also close to a drone or an aircraft or a satellite, boy, that could be a really nice contingency or emergency path for you to be able to get text data through. So that's why we've been able to attract some sponsorship from AFRL to pursue those efforts. Yeah, another question. Yeah. The question was, how many do we want in orbit? So for what we're currently looking at is just a demonstration. So on the ISS or on a CubeSat, those fly low for ubiquitous coverage. You all know how that math works. We need lots and lots and lots of that. And I don't think that that's a good price point for our sponsor. But the learning that we'll get from that and the PR that they'll get from flying a duck in space is tremendous for them. And can I go back? My sub-bullet here, developing and demonstrating a space-capable product assures a robust platform for airborne and disadvantaged users. If we can close the link to space and we can meet space environments, then we've asserted and helped fund our CubeSat program that we've demonstrated a very robust product. And there is an application where you could potentially have a node in space, but we're not looking to be the next Starlink. Yeah. Any other questions? Yeah. Yeah, the question was how power hungry are we? This can run, we run in, peak transmit is we're below 200 milliwatts. And so receive mode quiescent is 100 milliwatts. And so what we're looking, certainly on the ISS, we're an experiment. On a CubeSat, we're a hosted payload. But our power demand is very low. And I think we could potentially be a TNC or an alternate TNC for other CubeSat missions. But we need to get through environmental tests, we need to get through our scenarios, and we need to get through our demonstration before we offer that. But if there are CubeSat programs who are interested in a hosted payload as a demo, see me during lunch or dinner or there's my email at the bottom. Okay. Yeah, one more. Yeah. Yeah, the question was, I think about our capability at Cal Poly, and it was probably on the roadmap. Let's see. So Cal Poly does have a ground station, 2 antenna sites. I'm sorry, what's that? Oh, the anechoic chamber. I'm sorry. Yes, we have 2 anechoic chambers. I teach in both electrical engineering and aerospace engineering. This anechoic chamber is in our electrical engineering facility. It's roughly maybe 2 meters square. And then we have a larger anechoic chamber out at Aero. Anybody know how big the Aero anechoic chamber is? It's bigger. Yeah. Yeah, but yeah, so yeah, wonderful place here at Cal Poly. 5 TVAC anechoic chambers. We have an airplane. And so it's been really a nice environment for students to learn and for us to help our startup partner on this. Okay, thank you, everyone.
All right, thank you to Professor Dunton. Next up, we have Dr. Karsten Charlemagne from the University of Applied Science in Wiener Neustadt, presenting CLIMB, a CubeSat mission to the Van Allen belt.
Good morning, everybody, also from my side. I have my first technical problems with this microphone, but we're talking about CubeSat, so everything is trying out. Anyway, I'm very happy to be here. My very first CubeSat conference I had in 2004 in Huntington Beach, and since then I'm hooked up on CubeSats. Back then I was a researcher for propulsion, actually, and then I got in a position where educating students, and I'm doing this actually in Austria. I have a small slide here for those who don't know Austria very well. We are south of Vienna. And we built up a program, aerospace engineering program, and one of the things we did for our students was establishing a CubeSat project. We got into this by participating in a project for some, you might know it, QB50. It was a European program. The idea was to send 50 CubeSats into the thermosphere. We participated in that, and it was kind of a nucleus for our CubeSat project. And we succeeded actually in launching 1 satellite. You see this over there in 2017. It was called Pegasus, and one of the things we did for Pegasus was also establishing all the facilities you need for testing, vibration tests, thermal vacuum chambers, Helmholtz coil, etc., etc. So we did all this, and we launched Pegasus in 2017. It was flying actually until January the 8th this year, until last hour of before it really kind of stopped communication. We even downloaded still data and communicated with it. The thing we did back then was not buying subsystems. We wanted to build everything ourselves. That was a discussion which I regretted a lot of times during the establishment, during the development. But then we had a very good inside knowledge of all the systems, and that was very beneficial, especially when the satellite was in orbit and we had to deal with anomalies and take care of that. So it's a standard 2U CubeSat. The special thing was we had a Langmuir probe system on 4 single Langmuir probe systems where we took data and also calculated the plasma density and plasma temperature in space. So this back then was pretty successful, and after the launch we of course thought about, hey, what are we doing now with all the facilities and the expertise we established. This one photo just showing the launch and then the decay of the orbit in the last part, and like I said, August the 8th, we had a re-entry into the atmosphere and it burned up. So the next mission we wanted to do a little bit bigger, a little bit more challenging, of course. We got the taste for developing CubeSat, and our students developed some ideas, 6 or 7 different projects, missions. And the one we chose was actually CLIMB, and it's really not an acronym, it's meaning climb, to climb up, because the satellite will be launched in a low Earth orbit, 450, 500 kilometer altitude, and using a propulsion system, it will go up, or it will increase the apogee to 1,000, 1,500 kilometers. So this project will start, probably we will launch next year, and go in a low Earth orbit. The apogee rising will really be done basically by operating the thruster in the perigee. That has 2 reasons. One reason is the propulsion system needs about 45 watts, and we have only 42 watts we can produce on average, no, not on average, maximum. So we can operate the thruster only for 10 minutes in the perigee, and slowly over about 8 months increasing the apogee. The second reason for doing this way is Austrian law requires us to deorbit the satellite within 5 years. Otherwise, we don't get the launch permission. That was similar for Pegasus. And with only the apogee increased to 1,000, 1,500 kilometers, we can do that easily within these 5 years. When we are in 500, in 1,000, 1,500 kilometer apogee, then our science phase starts. Our science phase is we have developed a rather accurate magnetometer, about 1 to 10 nanotesla, and of course we are doing also radiation measurements. Yeah? I come to that in a little bit more. So this science phase takes about 1.5 years, and then we will deorbit the spacecraft by actually lowering the perigee. This animation is obviously way faster and also not to scale, but just for those who are not so in the orbital mechanics, we increase the apogee slowly over time, like I said, 8 months, and then science phase starts, and then we decrease. The main purpose of this mission is education of our students. Like we heard it this morning, CubeSats are very, very relevant in my mind for education still, but also for science mission, but this is a different topic. So the main thing is this, but we are doing radiation measurements together with some institutions, as you will see later, and also the magnetic field measurement for a CubeSat, I believe, in a rather accurate way. The mission challenges are really the propulsion, and I'm not talking about the mission, the power providing and the alignment, but to operate this propulsion system, to make sure that we want to operate about 16 times a day, 15 to 16 times a day, and that needs a lot of preparation in operational field. Radiation, we do a lot of radiation testing. We design our systems that they are radiation mitigation, let's say, or they mitigate radiation effects, and communication. We have an S-band, an experimental S-band on board, which is also a new system for us. This is how the satellite looks like. I don't want to talk too much about it. It is a free U. Has a double deployable solar array. Again, we are not buying things. We're developing it all ourselves. The three issues I want to talk about shortly is actually the thruster we are using, the magnetometer, and the radiation monitor instrument we have designed with external partners. First of all, the propulsion. We're using a FEEP, electric propulsion system. So FEEP stands for Field Emission Electric Propulsion System. A spin out of the university and our research corporation, Impulsion, was founded 2016, and they have, I would say, pretty big success. They have more than 200 systems by now in space, and they work together with us and they provide a propulsion system. FEEP systems have roughly 2,500 specific impulse and a thrust of about 350 micronewtons. And use this system we are using about 45 watts. Yeah? So 45 watts, when you put them into an electric propulsion, you generate 15, 20 watts dissipated heat. And to get rid of that is actually rather challenging. Operating the spacecraft, aligning it, making sure the batteries have a lifetime sufficient for about 8-10 months of operation in the beginning, and then later when you deorbit, still enough capacity. This is all rather challenging, battery management systems, etc. So integrating a thruster like this into a CubeSat is a big challenge, was a big challenge. We even had to design our new facilities. It's a thermal vacuum test facility where we can actually operate the thruster while it is in the thermal vacuum testing and integrate it into the satellite. So you see on the left schematics, and on the right actually the satellite peeking out. This was an old version of the thermal vacuum chamber we had, peeking out of the thermal vacuum chamber, and on the very right is actually operating. The magnetic field measurement, like I said, we plan to operate or measure fields with about 1 to 10 nanotesla accuracy. That requires already a lot of thought into magnetic cleanliness of your spacecraft, certain materials you shouldn't use, even aluminum contamination for the rails or the structure is aluminum, but contamination of this aluminum can cause magnetic field which distort your measurement. So we did some measurements. We have a small vacuum, a small Helmholtz coil facility at the university, but we went to a company in Germany, IABG, they're called. They have a Helmholtz coil in a building which is built out of wood in very far remote forest, actually. And the Helmholtz coil you see on the right side has a side length of about 14 meters. So they test also huge, big satellites. And our tiny little satellite was there in the middle, assessing the magnetic field we're producing ourselves by power generation, by operation of the propulsion system and other subsystems. And all was there to assess the magnetic field distortion by our own operation, and then basically take it out of the measurements when we are finally in orbit. I mentioned also we do a lot of radiation testing. This is because this is one of our goals, objectives of the mission, to use codes. We are not working with radiation hardened components, we are working with codes, but we design the circuits such that they, for example, avoid a current avalanche that can destroy your subsystems. In order to see if the subsystems we are designing are actually functioning, we are doing radiation testing, accumulative testing, up to 50 kilorad at the moment. What you see in the picture on the top right, there are 2 OBCs on board computers, and we are testing them in the facility and see if our systems work. What you see on the bottom right is a test in a facility where we can test SEE effects, single event effects, on our subsystem. I have, I think, a next slide what you see, the facility, it's always cool when you have such small satellites, but you need these gigantic facilities like the Helmholtz core or this accelerator. Of course, when we do our tests, we are not working in this room. We have small experimental rooms where we build up our experiment and do tests, and they look a little bit like this. What you see here on the side, I think it's the PSU or the OBC, I'm not 100%, no, it's the OBC. And we can actually guide the proton beam to very specific points and like in the raster, make measurements and see the OBC is operating during this time and see what effect it has. And if single event effects are actually happening there. So this is the type of measurements we're doing. This was ongoing for about 2.5 years. It's actually still ongoing. Each relevant subsystem we are testing like that and adapting if we need, so that we can be sure that this thing is operating in orbit the way we want, and we can actually survive about 3 years in a radiation-intensive environment, at least during the time we are in the Van Allen belt. I don't want to go into this. This is not my expertise. A little bit a colleague of mine is doing that, but we are doing also tests in order to increase or to work together with physicists to increase to decrease the sensitivity of certain components. There's actually 2 or 3 PhD positions out there right now in order to increase this knowledge we consider as essential for future CubeSat missions which leave the vicinity of Earth. All right, we also built up ground station. This was the Pegasus ground station, very, very modest, I would say, but enough for UHV and a low amount of data. For the climb mission, we switched to S-band. We have an S-band station, S-band antenna, and our ground station, of course, expands. It's actually now a little bit even bigger than what you see here on the screen. So this is all new for us, but somehow it's an extension of what we did for Pegasus. What's really, really new for us and difficult, I have to admit, Pegasus, during the science mission, we had to align the satellite, etc., etc. But the last years, Pegasus was doing whatever, and if we are not there for 2 weeks, nobody cared. Climb is different. Climb needs 24/7 monitoring and operation. That's just some schematics of the ground station. And we have to plan operation very well in order to decide if we can use the propulsion system. In order to use the propulsion system, it's not just switching it on, as you probably know. It is we have to check if there's enough battery power there, if the spacecraft is aligned, if the thruster is all okay, if the orbit position is the right one, etc. Yeah? Otherwise, it happens that you lower the orbit or you change the orbit in a way you don't want. This is a little bit the schematic we at the moment are building up on. It basically is a 5-week stretch where we plan our operation for the next 5 weeks in segments of about 6 or 7 days. For these days, there will be kind of a script written with all the mission, with all the steps which were to be done and during one 24-hour period, and then tested. The script is tested, especially at the beginning, in a flatbed, representative flatbed of the satellite, and only if it then is validated, we upload the script and the operation gets done. This whole thing takes about 3 or 4 weeks in order to validate the system and be sure, okay, we are doing the right thing. The whole thing, for me at least, the operational phase and to build up the tools to operate it is more complicated to a certain degree, or as complicated as the technical development. Because as a university, a small university, we cannot have somebody sitting there or several people 24/7. So we have to try to automate the operation as much as possible. And this is just some screenshots of the tools we developed, Grafana, to have always a good idea of satellite health and what it is doing, short-term, long-term, how we define what kind of steps we are doing, do we transmit data, do we operate a propulsion system, etc., etc. So this is what we are building up since, let's say, last year, and trying to get ready for launch next year. I said at the beginning, this is all for education, and this is true, but like Impulsion, which was spun out in 2016, we are encouraging our students with actually innovation centers and startup centers to build up their own companies, and the next company after Impulsion we spin out was Rspace. Rspace is dedicating its business for IODs, in-orbit demonstration IOVs, and wants to make it possible that if you want to test your technology, we bring the stuff up in 6 months into orbit, test it for you. This is a little bit the idea from Rspace. It was founded in 2021, and actually we have 2 spacecraft launching next year, and still some empty space for experiments, technologies who need to be tested in space. So if you're interested in that, contact either me the next few days, I'm here until Thursday, or take this email address and just write and see if we can fly your system. And with that, I think I'm also out of time. Thank you for your attention, and if there are any questions, I'm happy to answer them, hopefully. Please.
Hey, so wonderful talk and approach. Thank you. I appreciated
Thank you.
the validation process you're going and the mission planning. I'm curious on Pegasus. 6.5 years for a CubeSat, very impressive. Did you do the kind of radiation characterization for that mission as well? And did you do any like reliability assessment, or do you have any redundancy plan? Can you talk about that on your both Pegasus and your upcoming plan?
All right. In Pegasus, we actually started that with the, let's say, a clever design of the circuitry. Yeah, watchdogs, software-wise, we try to find ways, in case there are radiation effects, to mitigate them. Yeah, but we didn't have back then the possibility to do this kind of testing. Okay, the Medaustron facility I showed you, the huge accelerator, that's actually for cancer therapy. Yeah. But the funding from the government also required that academic efforts will take place. So this is now available to us for the last 1.5 years, something like that. So back then we didn't do this effort. We are just building it up now, both in accumulative radiation effects and the single event effects. And really our goal is to use codes as much as possible. Or actually, up to now, it's nearly 100%. No radiation hardened. Yep. You're welcome. There's a question in the back. Sorry, say it again. The capacity, you mean the impulse? You mean in delta V now? Sorry, I didn't get it. Oh, the battery capacity. You got me here. We have 8. It's not lithium. It's like lithium ion, but a little bit less capacity. I'm not 100% sure. Yeah, but sufficient. We are doing for the last nearly year. We're doing battery charging, discharging tests, and to understand the capacity loss. And we are using iron sulfide batteries, not the lithium ion batteries, something else. They have less capacity, but a much better charging, discharging behavior. So the capacity loss is really low. I can recommend it to everybody who's having a strong charging, discharging need of the batteries. Lithium ion are cool. Yeah, they worked for us for 6 years, 6.5 years, but Pegasus was harmless in terms of power consumption. There was a question here? Yeah.
I'm just curious, are you aware of any like unique challenges as operating as a European university as opposed to American universities?
All what I can say is that the regulation in Austria are pretty tough, actually tougher than in France or in Germany. So we have to get a permission from the government. That was already the case for Pegasus. It took me 1.5 years to get it, or took us, and I actually counted it because somebody asked me, more than 800 pages of reports, analyses, and whatever. Yeah. So this is what I can say. If the regulations, I think they are the same also in the States, you kind of adhere now to the 5-year. In the past was 25 years, that you had to remove your satellite in 25 years after your mission. I think now slowly everybody accepts the 5 years, if that's what you're asking. There's a question. What's the funding? Tough. We are lucky enough that I live in, or the university is in a region which is called Lower Austria, and we were able to excite them about CubeSats as educational tool. And they have funded the development up to now, together with the university. And just 2 weeks ago, I was told they will also fund the launch. So, yeah, go. Say it again? See, the students work and they work for free.
Right.
I mean, we all know that. You guys are exploited, but you learn a lot. I think at least, so it's a bargain in both ways. But the hardware cost is about $250,000. And frankly, because we get the propulsion system for free, it's cheaper, but the ADCS is a big problem for us, financially. Okay, thank you for your attention.
All right, thank you very much, Dr. Karsten. Now please welcome our next two speakers, John Moore and George Hollister from the United States Naval Academy, presenting Bridging the Gap, a standard bus for non-standard payload.
Good morning, everybody. My name is Midshipman First Class John Moore.
And I'm Midshipman First Class George Hollister.
We're coming from the United States Naval Academy out in Annapolis, Maryland, and we just want to say we're really grateful for the opportunity to talk with you guys, and we're really excited to talk about what we've been working on for these past 2 semesters. So the title of our slides is Bridging the Gap, a standard bus for a non-standard payload. Essentially what we're trying to say here is that we're attempting to bring the modularity of the CubeSat world into the educational realm at the United States Naval Academy. So the method that we like to call it is the tractor-trailer method. So on the left side of the screen there, you see a tractor and a trailer. The tractor is supposed to represent the Naval Academy standard bus. So this is the same bus that will fly up with every mission, and it's going to be the same every time. So just like a tractor, you make one, and you can reproduce that every time, and those trailers, as long as they're able to meet those same requirements, are able to drive, or in our case, fly with that tractor or Naval Academy standard bus. The trailer is able to be either a 1U or a 2U payload module. I think our clicker isn't working. Okay, so getting into the big picture concept, at the bottom of our slides, you see a series of NASB storage. Again, that's our Naval Academy standard bus. And so the concept is every midshipman through their senior year is going to have the opportunity to construct this Naval Academy standard bus, which has already been completely designed for them. The boards, essentially it's going to work like a kit. So you're going to have pre-populated boards and everything that you need to put the standard bus together, so that way the students can focus on the assembly, testing, and integration of that fully functional satellite, because the Naval Academy standard bus is able to fly on its own with or without any of the payloads. On the left side of the screen, you see student-designed payloads. So this is that 1U or 2U module, or that trailer that we were talking about before. This 1U or 2U module is essentially able to hold anything that fits with our requirements, just like most CubeSats. And so these midshipmen, while they are assembling that Naval Academy standard bus, are able to go through an entire mission design profile of their own payload. And those requirements are already set out for them while they're doing that assembly. So that way, you're learning about testing and integration while you are designing your own payload that's completely unique. And so this is going to give us the opportunity to have a stockpile of these standard buses, which allows us to work with other entities or internally with our midshipmen. And so when we have a launch manifest, whenever we're able to get that, we can launch. And even if one of the payloads isn't ready, The idea is that if we have that stockpile of standard buses, that's a fully functional CubeSat, so it can fly on its own without one of those payloads. So just to push harder one more time into that metaphor before we move on. On the left side of the screen, you see a picture of the Naval Academy standard bus. That represents that tractor. Again, that's going to be mass produced. That is the Lego style learning, that assembly, that testing and integration. That's 1U. And then moving over to the right, you see a 2U payload module. That represents that tractor. And so while that module will be the same, anything that you can get inside of that tractor or meet our technological requirements, you're able to fly. And then on that right side of our screen, you see a full 3U module, for example, which is that tractor and trailer, which are fully integrated and ready to fly with up to 3 payloads. A crucial part of this is the interface control document. The concept is generally, it's going to be the exact same for everyone. So we're going to have one interface control document, and so when you're going through that mission design profile at the Naval Academy or at the Air Force Academy or wherever, it's the exact same requirements that you're working on, so that way you can fly with any of these standard buses that we've created a stockpile of.
So we've talked a little bit about the overarching big idea that this mission is trying to accomplish. Now we'll get into more of the specifications on the 1U standard bus and the payload module. So first we have the general 1U standard bus here. Like we've said before, it's quick to construct and it's repeatable. This allows us to create the stockpile of this same standard bus. It has a mass of 1.2 kilograms, and for communications we'll be using a UHF antenna for uplink and downlink communication. We'll be using an S-band patch antenna for downlink data dumping when we come over our ground station. We have a passive attitude control system using hysteresis rods and passive magnetic alignment. And so we'll be using that when we launch the 1U standard bus on its own. But should a payload in the payload module need a more complex attitude determination and control system, that'll be housed within the payload module and will act as one of the 3 unique payloads in that module. Like we said before, this bus can accommodate a 1U and up to 2U payload module. So here is the actual payload module, right? It's pretty simple. All we do is pass power and communications for up to 3 unique payloads. This also provides a physical connection for the payload module to the bus to allow them to remain together while in space. So we'll jump into the mechanical interface that we just talked about between these 2 modules. So here you can see, just to get an idea of how they actually connect to each other, the Naval Academy standard bus is on the bottom and the payload module will be on the top. We'll take a closer look into this connection right now. So here you can see on the bottom this orange board, that is the top of the Naval Academy standard bus, and the gray base plate, that is the bottom of the payload module. Using these 2 boards in between, this allows us to connect the 2 modules together, similar to Legos, and screw them together using 2 screw connectors. On the right of the screen, you can see a mock-up of what this stack will look like when it's fully completed. So here, like I said, we're going to be using 2 screw connectors to connect the 2 modules together. We're not worried about flight loads during this, as most of the flight loads will be absorbed by the P-pods during launch, so we can use only 2 screws to hold the 2 modules together while we're in space, which is pretty nice.
Great, so now we're going to switch over to the electrical interface. A key component of the electrical interface, and what I had the opportunity to spend a lot of my time working on, was the payload interface board, or the PIB. So on your right side of the screen, you see a diagram again of that full 3U module, and the bottom of that payload module is that purple rectangle. That's where the PIB, or payload interface board, lives. And again, on the left side of the screen here, you see a tractor, and the analogy continues on of this PIB provides those connections that are going to be the same for every single payload to hook up with us. So while in a tractor you might have an air brake hose that you need to connect, for us that might be voltage or communication. So here's a block diagram to talk about what the payload interface board is capable of providing. So on the left side, you see from the Naval Academy standard bus. That's a 10-pin connector that provides voltages, 3 separate voltages and UART connections, so we can transfer data. That power is passed along, and the data is passed along to the right side of the screen. I have 3 rectangles up there, and that's to represent that those 10 pins that you see on the right side are identical. So you have 3 10-pin connectors that those payloads can hook up to. So that way, every payload is designing to the exact same requirements. Additionally, for the data, we are running that through the Featherboard, and that we are able to store data and pass along UART, and as well as provide an opportunity for one of the payloads to be hardwired to our bus. Finally, the PIB is capable of switching that power. So while we do hardwire some power into one of the payloads, if that's something that they need, we're able to switch that power. So that way, if there's something going wrong with one of the payloads, we don't have to lose the entire system. And those relays are controlled by our Featherboard, and every command will be sent up from the ground station through that bus to the PIB, which will then turn off that power or turn it back on again. So here's a picture of what one of the iterations of the PIB, again, payload interface board, actually looks like. This is just to emphasize, on the left side, you see one set of 10-pin connectors coming up, and then on the far right side, that's 3 sets of 10-pin connectors that all of the payloads hook up to. So again, it's the same exact connections for each of them, and you see our Featherboard and the series of relays that are all running the board systems. So now I'm going to focus a little bit on the software and the capabilities that we have there. Again, this is specifically in the PIB. So on the left side of the screen in red, you see bus command. So if the bus were to send a command up to the payload interface board, now we're in blue. The PIB is going to receive that command, and it's going to determine whether that's something that it needs to accomplish, or if that's something that needs to be sent on to one of the other payloads. Let's say we're sending a command to payload number 2 of take data and download it on the PIB. So staying in the center, we're going PIB sends, now over to green, and payload receives. Payload operates that command, and we are able to, now down at the bottom, send that data down to the payload interface board where it can be set there for storage. So that's an example of one command. Now, if we wanted to get that data down to our ground station when it flies over the Naval Academy, we'd have to send up another command. And so again, back in red on the far left side of the screen in the middle, we send a command to the PIB. PIB realizes that's something I need to operate, and it's going to begin that downlink process through the bus down to our ground station.
So that is the basic design of the Naval Academy Standard Bus and the payload module. Now we're going to focus into the mission that we've been working on for this year, the USNA-16 mission. So here you can see the payload module for the USNA-16 mission. The full 3U CubeSat will weigh 6 kilograms. Power generation will be creating 5.5 watts at the beginning of life and going down to 5.2 watts by the end of our life. Our mission orbit is 500 kilometers with an inclination of 60 degrees. This is good for us as it goes through the South Atlantic anomaly, which is something that we are looking to measure. We'll get into that a little bit more as we get going with these slides. We have a mission life of 2 years, and we'll be holding 2 payloads with us. We'll be using one from the University of Maryland and one from the United States Air Force Academy. If you look to the top of the payload module, you can see that is an antenna deployment system for the University of Maryland payload, and we'll describe that right in the next slide. So here we have the payload mechanical specifications, which are laid out within the ICD. They have to fall within these dimensions, and their PCB rail hole alignment has to fall within the Pumpkin standards to allow for seamless integration. They're allotted 0.4U, and we're required to have a cut on the positive X face of their PCB to allow for wires to travel from the bottom of the payload module to the top. On the right, you can see a general architecture of what it'll look like within the payload module. We'll be having our payload interface board. We'll be having a dummy weight to act as a ballast and proof of concept for a future mission payload. Then we'll have the United States Air Force Academy payload, and finally, at the top, the UMD payload. So here, the University of Maryland payload is basically a UHF radio and an antenna deployment system. This is a proof of concept that they can communicate with their ground station at their university, and that they can operate a payload and create a payload and go through that design process at their school, more or less. Right, so they'll just be delivering us a PCB and an antenna deployment system, which you saw on the top of the module. We'll be connecting that, they'll be operating their own antenna, and we will be only providing power to their system. Next in the stack, we have the United States Air Force Academy payload. They'll be carrying along a dosimeter that will measure radiation within the South Atlantic anomaly to gain more data and information on that. What we'll be doing, more or less, we'll be passing them a NMEA GPS time code that includes the current time, latitude, longitude, and their altitude of the satellite. they'll be taking this and adding it to the data that they collect and sending it back to us on the PIB to send down to our ground station where we will be doing a majority of the data processing once it's been received at the ground. And they'll be the second payload within our module. Finally, we have a dummy weight. Like I said before, it's going to act as a ballast to ensure that our center of mass is within our tolerance. This is also provides an example showing that we can carry along 3 different payloads within our module, and it's kind of a proof of concept that this is something that we can do. It will be 334 grams and will be 50 millimeters from the bottom to ensure that our center of mass is where it needs to be. And it'll be made of aluminum.
So, as a student at the Naval Academy, this is a really special project to me because we've been on the ground floor developing a new class structure that is going to really forward our major, so you're going to have the opportunity to make a fully functional satellite. Like every midshipman's going to have that opportunity, and they're going to be able to design their own payload that's going to match up with that fully functional satellite. Additionally, this gives us the opportunity, like you've seen, like we've been working with the Air Force Academy really closely to learn about integration long range, because we've made a lot of mistakes working with each other through communication and learned a lot through that whole process. So I'm super grateful to have been on this project, and thank you.
Any questions? Yes. That is a good question. I think that's above our scope. That's within talking with the professors and everything. Yeah.
Yeah. Yeah, so the loads that we're working with and a lot of the instruments, really that hasn't been a major concern, and we've seen like pretty small variances in our calculations for the thermal analysis, and so a lot less of a problem than we actually expected. Yeah.
For the NASB, how did you go about defining what your outputs are going to be for the standard?
Another great question. There's a separate team that worked on the Naval Academy Standard Bus, and so we focused on the PIB, Payload Interface Board. So I think that's a question that I can pass on to them, and if you want to find me after, we can clarify that.
This is just a question about payload to NSAB, basically compatibility. Would you need to use like a pumpkin chassis for that, or could you use other potential chassis for that dimension?
As of right now, we're using a pumpkin chassis just to keep it standard so we can bring them together. But basically, we provide the chassis, and the payloads provide their PCBs. As long as they fit with, as long as the holes are aligned and they fit within the requirements that we set out in the ICD, we'll be able to slide them into the chassis and launch it.
Yeah, and if you decide to work with us, there's some smaller changes you can make along the way. So if that's a requirement you have, it's generally modular, but you can make small changes along the way.
No encryption. We're using checksums for data confirmation to ensure we're using the right or receiving the right data. But other than that, nothing encryption-wise, at least right now. I don't believe so. All right, I think that's all our time. Thank you.
Thank you to John Moore and George Hollister. We will now be going on an hour break and returning at 1 p.m. for more presentations. Lunch is provided for you right outside the main lobby and at the entrance of this building. Please enjoy, and we will see you at 1.
Welcome back, everybody. Our next presenter will be Safira Akins and Christopher Freitas of the University of Hawaii, presenting their abstract on their CubeSat relativistic electron and proton energy separator.
Good afternoon, everyone. My name is Safira Akins. This is Christopher Freitas with me, and we're presenting on behalf of our team at the University of Hawaii at Manoa on the CubeSat relativistic electron and proton energy separator, better known as Crepes for short. So outline of what we're going to talk about today, it's going to be just mission operations objectives, and then we're going to go into our payload design and our satellite design. So starting out, what is the Crepes mission? The Crepes mission aims to monitor high-energy protons and relativistic electrons in low Earth orbit and to find their incoming direction, all while utilizing some newer technology that does not have much spaceflight heritage. And we're going to get into that technology further as we move on in the presentation and look at our payload design. So for our science objectives, we're following, of course, NASA Heliophysics Decadal Survey, and we're following section F2, which is particle acceleration and transport. So we're interested in learning about the flux of these particles, those high energy electrons and relativistic protons, other way around actually, relativistic electrons and high energy protons, the incoming direction of those, so we want to be able to monitor where they're coming from, and then we also want to monitor the amount that are coming after solar energetic particle events like coronal mass ejections and solar flares, and we're looking to do this in time intervals of 20 to 60 minutes within our orbits. And then for our technology objectives, we're looking at an opportunity to enable GEM detectors, which are gas electron multipliers, more spaceflight heritage. And so we actually just received a CSLI, which is super exciting, and our anticipated launch we're looking at the very end of 2025 or beginning of 2026. Right now our mission is in the CDR phase, so we're still very preliminary in trying to, I guess, develop our design, and we don't have much of it built yet, but we are prototyping currently. And then just to get into some of our mission operations and what it's going to look like, we're aiming for a sun-synchronous dust-on orbit so that we're in constant sunlight, specifically for our particle detector, which will be looking at the particles that are coming from the sun. We're at an altitude of roughly 530 kilometers with about 90-minute orbit lengths. And so for our data collection, what we'll be looking at is about 12 minutes of active data collection with our particle detector. The rest of that, per orbit, correction. The rest of that is going to be time spent generating solar power and then also powering up our detector. So there is kind of a power up time for our detector in order for it to function. And then for our downlink, we have about 10 minutes per orbit where we'll be over our Hawaii Spaceflight Laboratory downlink station. And then for our total mission lifetime, we're looking at about 6 months to 1 year that we're hoping to be operational in space. And we're going to move forward to our plate readout detector.
All right. So just a quick show of hands, how many people here are familiar with GEM detectors or know about GEM detectors?
Sweet.
Yeah, not too common. So yeah, GEM detectors stand for gas electron multiplier. They're actually most commonly used in physics experiments like particle accelerators. They've also been used for some medical science and for imaging. Their mainly priority is to characterize or help characterize particles. They can also give trajectory information, do some timing things. It's basically to help identify particles and characterize, their qualities, their energies, and their fluxes. So I'm no physics expert, but I can give a rudimentary explanation of how these things work. So when a ionizing radiation or some kind of particle collides with a gas molecule, if that energy is high enough, it will emit an electron, or an electron will fall off of the gas molecule. And now let's put this in an electric field, and that electron that got let go can drift towards an anode, and then that electron will be read out as a current signal. The problem with that is that just one electron is obviously not enough to see anything. So what we need to do is to amplify the amount of electrons in the signal so that we can actually read it out with our electronics. So the way that GEM detectors do this is actually, in the bottom left picture, you see a really thin mesh, and inside the mesh, on top of the mesh, you have copper passivated on the top and bottom, and then along with that, there's really, really tiny holes all throughout the mesh. And so what happens is when you apply a really high potential voltage across the top and bottom foil, it creates a really, really high electric field. And then this electric field allows those electrons to accelerate within the gas. And then the momentum and the energy gained from that acceleration can collide into other gas molecules, creating more electrons. And then you end up with something called a Townsend avalanche, or an electron avalanche. And then by the time it gets to the bottom plate in the top left picture where you can see the readout electronics, there's going to be so much electrons that you'll basically have a strong enough current to read out. So that's the idea. So that's how we're going to, when we have electrons and protons going through the gaseous volume, we amplify the signal and we get it out, and then we have our payload. So there is a lot of advantages to using gem detectors in particle physics, of course. One thing, they're cheap, they're durable, they last forever. They have such a high versatility. You can do a lot of things with them. Depending on the type of readout, you can do XY strip readout, which lets you get position data. You can put like a radiator in front of the window, so you can get transition radiation information. You can actually even change the type of gas that you put in to have photons emitted during the radiation process, and then you can put a camera underneath to see the actual the particle trajectory. There's a lot of things you can do with gem detectors, and that's part of the reason why we chose them. Another good advantage actually is that the effective gain of the detector isn't too affected by temperature changes or pressure changes. You kind of see near constant gain or during operation despite the temperature fluxes. So in the pictures we have here, you see an example of a typical graph or histogram that you would get from a gem detector data, and also in microbiology, or in biology, you can see imaging that can be done with the gem detector as well. And there's just more pictures of the effective gains of the different setups of the types of gem detectors that they have. So of course, gem detectors have a lot of advantages, but the fact that we're trying to put it in a CubeSat brings up a lot more problems than you would think. For one thing, reading out the gem detector, even though we're saying we're amplifying the signal so that we can read it out, we still need to amplify that signal even further for there to actually be something that we can make sense of. And the amount of power it takes for the readout electronics is a lot. Depending on how many channels you have, let's say you had XY strips and there's like about 250 strips to get a image, right? But you have to amplify every single strip by like 1,000 or so, and that takes up a lot of power. Another big issue with using a gem detector, right, is we need to keep the gas in there as long as possible. Things like that are prone to gas leakage. And then one last problem is the amount of data that this thing produces, because it's such a high flux, it would be too much to send down, and the downlink speed is only like 4,000 bits per second or something like that from our ground station. So yeah, there's a lot of problems that we had to solve trying to put this detector in a CubeSat. But the good news is that they are cheap and they're durable, and also that they're also radiation hardened. So it's almost perfect for the space environment. So to solve this issue, actually, we still want to get some directional information. However, we can't afford to have the XY readout and get fancy positioning data. So what we did was we constrained the entry window that the particle can go through. Effectively, it only accepts particles that can go straight through the window in the payload. So in this sense, as long as we know the orientation of our satellite, then we can kind of more or less say that, oh, this particle came from that direction. And then we can count the amount of particles in the flux, and then we can get the energy out of it from the signal. And that's how we will operate. On the right side, you can see a picture of the foils that we designed for this specific design. We ordered them straight from CERN. However, in the future, we plan to be able to create our own foils for the detector, which is a whole project in itself. And then on the bottom, you can see actually how small the holes are uniformly spaced in the mesh. So now I'm just going to talk a little bit about the design that we have for the current payload. So commonly, what's common in gem detectors is that you have frames which the foils sit on, and then you glue those frames together, and you house those frames in a giant case that's sealed and the gas stays in there. Typically, you would have gas being flowing in and out to just keep the gas fresh, but because we're in space, we can't really do that. So we need to make sure that it's tight and that the gas can stay in there, which shouldn't be too big of a problem. I mean, Geiger-Muller counters did that way back then, so they can do that. I'm sure there's a way. So yeah, that's the typical idea. The gold or copper-looking piece you see there is a check valve, so that's where we put the gas in. And then I didn't add it to the current design, but on the right is a temperature and pressure sensor, a really small one that we're going to put in so that we can monitor the temperature so that we can actually see, calculate the effective gain of our detector at all times. This is just a further image of what the components look like altogether. And here's a good diagram of how the gas chambers will work. So the green rectangle is where the actual radiation detection is happening. So that's where the foils sit, and that's where the avalanche happens, the electron avalanche happens, and the signal gets read out there. And then the blue chamber is just a subsidiary chamber for the temperature and pressure sensor.
Awesome. So moving forward, I know we mentioned that we said we had ordered some foils from CERN, and we have done that. However, we only have a very few amount of these foils, and to be able to produce multiple different types of prototypes, and if we make any mistakes, we'd like to have some backups. So we are manufacturing our own foils in-house, and in order to do that, we need to use different types of photolithography and etching procedures. Looking at the substrate pictured on the top, you can see what we're working with. So there's a copper clad on the top that's 5 microns thick, followed by the Kapton polyamide, and then another layer of the copper polyamide, or sorry, the copper. And so the shape of the holes is called biconical. That's the type that gem detectors have, and so that means that the diameter at the bottom is larger than the diameter in the middle. And then those holes are separated by about 140 microns. So it's all really, really small scale that's necessary to get that amplification for those electrons. And so in order for us to manufacture these foils, we will first spin coat them with a photoresist. This is part of the massless lithography procedure. And then we hot bake these foils. And once we put them in this MLA 150 machine, it's able to use a laser to put a design on that foil. And so we do that on both sides, and then we develop that photoresist, and so we have a nice design that we can actually etch through. And so for our foils, we're using ferric chloride to etch the copper, and then for the Kapton, we use a monoethanolamine and potassium hydroxide solution. And then for our satellite design, this is kind of our preliminary design that we have right now. You're going to notice at the bottom of the design, there's a section that says Artemis Kit Subsystem. So the Artemis Kit is something that's manufactured at the University of Hawaii, part of the Hawaii Spaceflight Laboratory. It's essentially a 1U CubeSat that is able to fly. So it has 2/3 space for all the subsystems and then 1/3 space for a payload. And since we won't be using that payload, we're just going to take out all of the bottom subsystems that have like communications, our EPS, OBC, everything that we need for the satellite to fly is in that Artemis CubeSat kit. And then in that second U, we have all of our electronics for our payload. So we're looking at our high voltage power supply that we need for our gem detector. We have our different amplifiers, which we'll go into detail about as we move forward. And then we also have moving up our high voltage divider and our payload in that top section. You'll notice that there's a lot of space in the CubeSat right now, and that's just because we do have more electronics that we need to add in, so we're making sure that we have ample space for that. And if we do end up having enough space, we plan on adding potentially more ADCS controls. Right now, our ADCS are going to be torque coils that are embedded within the solar panels. So it's not much control, but it'll help us minimally with our pointing and stabilization.
So one final remark about the problems that we face trying to put this detector in. It's the readout really that causes most of the problems. So of course it's a high flux situation. The readout electronics need to be able to handle that, and also the onboard computer would need to match that as well if we wanted to get accurate data out of it. So the way that the signal comes out of the detector it's a current that can be sensed, or that can be read out, and that current needs to be turned into a voltage signal so that we can bin it and then make a histogram out of it. The way that we do that is with 2 preamplifiers. So in the picture here, you can see the Cremat amplifiers from Cremat. So the first one's called a preamplifier. So basically what it does is it takes a current signal and then it turns it into a voltage spike. And then as you can see, there's the bottom picture, right? So that the green line is the voltage spike that you see, and it has a long tail. A common problem in particle detection is that because we have particles coming in so fast, while that tail is still dying down, you'll have another particle come in and it spikes it up again. But because it's riding on that tail, it'll spike it up longer than, it'll be a higher voltage spike than it was supposed to be. So the whole problem is or the whole idea is to shorten that tail in the signal so that we can have a higher flux or have a higher rate of, a higher sampling rate. So we do that with another amplifier called a shaper amplifier. So what it does is it turns that green line signal with the tail into a Gaussian signal. You can't really tell from the picture, but this is zoomed in really far. So that Gaussian shape at the top that you see in the right picture, you can kind of tell that the tail has been reduced because now it's a Gaussian shape instead of the tail from before. So on top of it shaping the signal and turning it into a voltage signal that we can read out with our onboard computer, it also amplifies the signal like we said we had to do. So it goes from, I think the current that comes out of the detector itself is around less than a millivolt. And then with this setup, with these two amplifiers in sequence, we can amplify the signal by about 1,000 or so to get millivolts. And then the onboard computer will process that information, and then we'll get a histogram of the energy bins, of the particles, and then the counts of all those bins. So that's how we plan to operate in our mission.
Awesome. And that's all that we have. So thank you to our sponsors and our mentors, and thank you all for listening to us today. Let us know if you have any questions. All right, go ahead. We have about 5 permanent members, and then we get occasional volunteers. So there are 3 other members that would be here that are like definitely part of the project, and then a few others that kind of just help out. Yeah. Mm-hmm. Yes. We have not yet, but we're in the process of that. So we actually had previously manufactured foils with a different chemicals that we used to etch, and those foils did not perform well. So we're doing a round 2 with kind of new chemicals that we intend to use. We actually had the opportunity to go have a workshop at CERN. So we spoke with some of the people that are in charge of manufacturing their foils, and we were able to get some insight on their procedures. And we're still looking to do something a little bit different, but we have that insight. I think we'll be able to do better now. But yeah, not yet. All right, if there's no further questions, thank you so much.
All right, next I'd like to welcome Victoria Paget from Georgia State University.
Good afternoon, everyone. My name is Victoria Paget, and I am a computer science master's student at Georgia State University. Today, I am very excited to continue and share again the work that we've been working on for our CubeSat. It is currently titled CCBE a cosmic climate cuboid nanosatellite for monitoring above Earth activity. And so what we are trying to do with our CubeSat is focus on capturing an overview of primary cosmic ray radiation as it interacts with Earth's atmosphere. And so we have primary cosmic ray particles that will make their way into the solar system and then make their way into our atmosphere, where they then are influenced by the sun and the atmosphere and produce these secondary cosmic ray particle showers. These secondary cosmic ray particle showers are often made up of mostly muons, and when you look at the muons within Earth's atmosphere, you can really get a picture of space weather and the atmospheric profile at that time. One really important thing to note is a CubeSat launched inside of LEO would not be capturing muon data at that point. We would be capturing protons and neutrons. And so we really want to use our CubeSat to begin capturing this space weather effect to then remove it from any kind of ground-based sensor readings that we would have to get a better state of just the atmospheric effect. Currently, there is a project running at Georgia State created by the Nuclear Physics Group to offer ground-based telescopes specifically for muon analysis. And so each of these ground-based detectors offer a stacked platform of 3 20 by 20 centimeter scintillator tiles. They're stacked about 13 centimeters apart. And what they are doing is they are capturing muons interactions between these scintillator tile plates to kind of give us an overall atmosphere of what these secondary particles are looking like at Earth's surface. And because of their low cost and portable design, we are able to install these detectors around the globe. But we still need a CubeSat. And the CubeSat, like I said before, is to gather a better understanding of the space weather and how this effect can be taken out of our terrestrial effect in the atmosphere for these particles. So we want to build a CubeSat to complete this solution and to be able to gather the primary cosmic ray particle data from LEO to then build a prediction model where we would subtract out the protons and neutrons we'd see from the CubeSat from our ground-based detector readings and begin to predict weather real-time through these interactions due to their closeness together. The way we've begun to design to do this is we've built a 1.5U CubeSat. It has been 3D designed. The chassis has been 3D printed currently, but we would switch that to aluminum as we continue forward. Where we currently host a Raspberry Pi 4 as the CPU and use a lithium-ion battery pack to run the detector. The sensors that we have are 3 9x9 by 1 scintillator tiles that we stack about a centimeter apart in order to begin to make sure that we see the particles come through 2 plates, so long as they are able to make that. The other thing that we've been experimenting with is using LoRa, so low power, long range wireless communication, to transmit our data from the CubeSat to our ground station. It is being tested currently within the system, so there's not a lot that I will be able to talk about with it today, but our goal is to use this on the 915 megahertz band to continue to communicate data to our ground station from our CubeSat. For this, we wanted to make sure, just before we started to put this up into the atmosphere, that we had consistent data collection on the ground with what we anticipate based on the ground-based detectors. And so we took our CubeSat and we left it for about 2 weeks in a spot to just make sure we weren't seeing any noise within our data. And then we left it again with a ground-based detector in order to compare the results. One thing that we did do was place a small addition inside our detector right over here to help prevent noise within our experiments, and that's going to stay in some of our designs. But these wires connect the Raspberry Pi to these scintillators. The first test was to make sure that we were receiving consistent data. This graph shows the % change in the amount of muons that we were seeing during the analysis, so whether they were increasing or decreasing. And what we found was very good. We want to see anti-correlation in the amount of change we're seeing, this percent change. The percent change should be higher as the pressure goes lower. And in, as well should go lower as the pressure is higher. This is a very important anti-correlation that we wanted to see within this data. We then, like I said, we left it with a ground-based detector. And so the CubeSat version that we have currently receives, due to the sizing of the scintillators being about half of what the original base detectors were, about 1/3 of the amount of particles that we see. With that 1/3 loss, though, we still were able to, after leaving the detectors together, have a very similar set of data where we can very much see the same anti-correlations. And comparatively, when we put this data together, we have about a 90% correlation between both detectors right now. The same anti-correlation can be seen at the beginning of the data, as we can see in the middle right here. And so this gave us really good proof that we had designed our detector to be able to work very well with our, within the ground-based system. So now we want to get it in the atmosphere. So the first thing we did was we began taking the detector on airplanes. And so we packed it into a personal item, and we're able to take this personal item onto the plane and leave it within the cabin under the seats. During this, we began to gain a better understanding of the relationship between what we were seeing on the ground and then what we're starting to see in the atmosphere. The flight-based testing really became an essential form for us to begin starting to unravel what we might see once we put this in LEO. So this is one of the flights that we took our detector on. It was from Atlanta to Mountain View. And during this, you can see a very clear point where you can see the ascent of the airplane when we were in the atmosphere, and then the descent back to ground level. And you can see it for all of the flights. Like, we can see a very clear ascent. We were seeing on a per minute basis about 30 times the amount of counts that we would see on a regular basis. So typically, like we saw in the last image, we'd see about 50 strikes on our scintillators. We then saw that go up to close to 1,500 and above during these flights. We wanted to repeat this. Oh, there's one more thing I wanted to draw attention to here. This spike in the middle, that is actually from a drive that happened during this time around Half Moon Bay. And so during this, you were driving in the mountains, and we can see this very clear spike from the altitude as well right there. We did this another time. We've actually done it a few times since then, but I just wanted to share this set as well. We also still see that very clear ascent and descent from each flight, and you can tell even where the layovers are within this data collection. We still see about the same rise, where there's about 30 times the amount of data that we are seeing and 30 times the amount of particle interactions that we're picking up during this. So again, same thing with the second flight after the layover, we get that ascent and descent again. Just this past weekend, we were able to launch our detector on a high altitude balloon. This is very preliminary testing. We did this last weekend and just got the data back, so we wanted to include it to share. That launch was done in collaboration with Middlebury College, and they're located in Vermont. We partnered with Launch for Us to use one of their high altitude balloons, and we're able to send it up to roughly about 35 kilometers above the Earth's surface, so we could really begin to see what kind of data we've got going on as we reach closer and closer to the upper limit of the atmosphere. This is the very quick plotting of that data that we received back from this high altitude balloon test. And so you can kind of see the points in time where you were on the ground in the building, and then when the balloon took off. And one thing that we wanted to point with this is we were seeing a lot of higher particle interactions as we went even higher above the altitude of where commercial flights are. So we were getting almost in a per minute basis about 4,000 particle interactions within our scintillator tiles. You can also see the point, this spike right here, that is where the balloon popped as then we launched the parachute to bring the device back down. So you can kind of see as that altitude changes again throughout there too. We're still working on analyzing this data further as we have some more data from the balloon that we're still taking a look at. So we'll hopefully have those results throughout this week to continue to talk about if you have any other questions about it. So one of our big things for our future outlooks is we do really want to get this launched soon in order to begin really gaining an understanding of what we will be seeing outside of the Earth's atmosphere so we can begin building these prediction models. So we're really hoping to launch all of these CubeSat, or well, at least one right now, but hopefully multiple in the future, to begin this data collecting. We do want to begin building our prediction model as well, like I mentioned, so we can really start getting a look at what weather we might be experiencing based on the interactions that we're seeing from space weather in our atmosphere. And then it would be a future goal of ours to also have this be a little more like a constellation, have a couple more CubeSats out there so that we could have different points of the atmosphere or in orbits being covered at once to compare to the global detector network that we're starting to build. This CubeSat is part of a larger project at Georgia State University, the Global Cosmic Ray Detector Network. So those ground-based sensors, like I talked about, have begun being placed globally, where we are starting to see the interactions across the globe, different altitudes, different kind of particle interactions throughout. And so we are wanting to continue this work because it's also a good tool for education for students. So I have a student who's been working on this for 3 years now, and I have learned so much more by beginning and starting a CubeSat and working through it about how to put together all of this. And so we want to continue this educational opportunity for students as well, both with CubeSats and with the ground-based detectors. And if you want to know more about the overall project at all, me and my advisor will be at the conference all week, so please come ask us questions and we'll be happy to further talk about it. And so I just want to say thank you for your time and for the opportunity to present and share our research with you and open up the floor to any questions. Yes. So the balloon that we used was rated to go up to 35 kilometers. Part of the data that we're still collecting and still getting sent to us from the launch facility is the altitude, how far the balloon went up. So I will have the exact number a little later this week. I'm just waiting on that email to be sent to me. Right now, it is, looks like it's scaling linearly, but I think it really depends on where the secondary cosmic ray particles, because we're still stuck in the atmosphere right now. We haven't gotten the launched CubeSat yet. Within the atmosphere, the secondary cosmic ray particles break down from the primary cosmic rays at like a maximum point, which is roughly about that point in the atmosphere where this, like where the balloon, where the balloon went to, right? And so that's where we're seeing that really high particle breakdown within there. So that's where we're going to see the most. And then they have very short half-lives through that. So you will see a decrease as it gets to the ground, though linear would just depend on season and more scale factors that we'll continue to look into. Yes? Mm-hmm. The peak afterwards? That was as the parachute deployed to bring the detector back down to us. So when it deployed, it pulled it back up a little bit after the balloon popped. So as we saw that altitude increase again from that, it started to decrease again. So we have looked at shrinking that from like a full Raspberry Pi to a smaller version of it or a different microcontroller. The reason we wanted to stick with the Raspberry Pi is it was very similar to what we had done before in previous experimentation, but it is a full computer system. And so we're looking at shrinking it potentially to a 0 or a Pico. Okay, thank you. I will actually probably ask you more questions about that later. Yes. So the 915 megahertz is offered as the LoRa standard for their communication. It's not a regulated license for that communication wave. So you can, if you are operating in the LoRa spec, you can continue to use that. However, I know as we continue to move forward with satellite development, we will have to start that licensing and things like that. All right. Well, if there are no further questions, I want to thank everybody again and enjoy the rest of the conference.
Thank you.
Hello, everybody. Thank you very much for the introduction. So, as said, my name is Thomas Schwarze. I work at the University of Florida in the group of Dr. Conklin. And I joined 1 year ago. Actually, also, it's my first entry into the world of the small-sat community. Before, I was working most of my professional career in Europe on the LISA mission, hunting gravitational waves. But today, I want to talk to you about the CLIC mission and specifically the contribution of the University of Florida, namely the TDC-based data and timing transfer scheme. So let's dive right into it. So first, I want to give you an outline of my talk. So I want to start with the CLIC mission description and the motivation, specifically describing that this is like a two-step mission, so with the risk reduction mission called CLIC-A, and then finally CLIC-BC. Then I want to go into details about the TDC receiver and transmitter for the SAT data transfer scheme. Then finally, I want to show you our flat set testbed, which we use to test the system in electric loopback tests so far. So CLIC, what's CLIC about? CLIC is a tech demo for a laser crosslink with low swap. Then we can ask why lasercom. So when we compare to classic RF communication, first thing is, of course, way higher frequency. So in our optical wavelengths or frequencies, we reach up to terahertz, while we compare to gigahertz for RF bands. That means we have the possibility of way higher modulation rates, meaning also higher bit rates. And on top, we have, with a focused laser beam, we have less divergence, which is good in the sense that we don't lose power, that we just put it everywhere. And particularly also that not everybody can listen in on our laser beam. So the goal for the future, or honestly also for present constellation, is to achieve gigabits per second full duplex crosslinks. Oh, actually, I have a screen there, it's more convenient. So I have to have gigabits per second full duplex crosslinks, including precision ranging and timing transfer. So let me read the mission goal out to you. So the mission goal of CLIC is to demonstrate a low swap, full duplex, high data rate laser communication link, including timing transfer and ranging between two 3U CubeSats using commercial off-the-shelf components. And as mentioned, we had already one risk reduction mission, CLIC-A, that launched in September 2022. and basically showed it was a single satellite and showed the downlink to Earth. And what was tested were successfully the MEMS fast steering mirrors and the pointing and acquisition and tracking. So we were able to derive some pointing error data there, and additionally also test some of the bus infrastructure, so the spacecraft bus hardware, the software, the ground support system, and yeah, as also shown here, the optical ground station. And then the final step now that we are working towards is to go for the ClickBC crosslink. So to have the communication, oops, that was not the pointer. To have the communication in both directions, so full duplex between the satellites. And we hope, or our goal is to launch this in the early 2025s. So now I would like to focus specifically on the data transfer scheme. And in Click, we are aiming for pulse position modulation. And the way it works is shown here schematically. So we use a fixed set of bits. In this example, we just pick 2 bits. So we have a 2-bit word, and with 2 bits, we can describe 4 different possibilities, right? So 00, 01, 10, and 11. So, and we have used these 4 possibilities to put them into 4 time slots. Once again, wrong button. So we see here in this example, we have 4 time slots plus some guard time. And so if we have 0, 0 as a bit combination, yeah, we will put it into the first time slot or the 0th time slot if you want. And for 10, for example, which would describe a 2, we will put it in this time slot. In this way, we derive the data that is transmitted. Additionally, you can see this pulse is slightly offset to the center or to the ideal center of the slot. And that's intentional because with the slight deviations, assuming that those deviations are only caused by differential clock noise, we can actually derive this clock noise. And that's the basic idea of the timing transfer. So in Click, our goal would be to go for a max speed of 50 megabits per second for the 4 ppm scheme. And this depends on the distance of the 2 satellites. So when the satellites are further away from each other, we receive less power. So we need more power focused in the single pulses. So we need to go higher to higher ppm schemes, which in turn reduces the data rate. And for the timing that I just described, we are aiming for a resolution of 200 picoseconds. So this, just to give you an overview, is a picture of the payload. You can see all the optical devices, so the pad for the optical bench, including the pad mechanism, fiber raceway, more optoelectronics. But I would like to focus on the electronic stack here, which includes the main avionics to also compute the data transfer. And this is the board close to my heart. So this is where the magic happens, the FPGA board. So let's take a quick look. So as a main processor here, we have an FPGA, in this case, Smart Fusion 2 device by Microsemi. Then we have a GPX TDC, so a timing to digital converter. And here also an ADC. I will go into detail about that later. And on top, a SerDes interface. So it points here, but I mean, the SerDes interface is strictly speaking on the FPGA, but this is our output here. And then our goal is to use our TDC, which comes with 4 channels, and use those 4 channels to characterize the laser pulse at 4 different points in time, just to get more precision than just with simple 1. Those 4 pulses, or those, the timestamps of this pulse will then be averaged in the FPGA and then fed into the PPM decoder. And how those things work, I will go into detail on the next slides. Just for completeness, so we also, besides receiving the data, we also need to generate it, right? So this is where the SerDes comes into place. So it's also the job of the FPGA to use the raw data and generate like a pulse timeline for it to feed it to the SerDes. And finally, for completion, I wanted to mention that we also have this parallel ADC receiver chain. So basically to have 2 different systems to do the data transfer. But for now, I don't want to go into detail about that. Just let's focus on the TDC chain. So as mentioned, we have 4 TDC channels, and the way we achieve or to get our sampling points of the pulse, it goes like follows. So we receive our optical signal from a photo receiver. We go through some analog conditioning electronics, and finally feed the signal
to two comparators. And the two comparators can be fed with two different thresholds, and basically corresponding to those lines here. Finally, the output of the comparators, they go to 4 latches. 2 are triggered on the falling edge and 2 on the rising edge. Hence, we get these 4 points characterizing our pulse with high precision. So once these pulses go into the TDC will spit out 4 timestamps, which we can then process with the FPGA. And this is basically the heart of the decoder. So assuming we get our input timestamps in here, so the problem is our local decoder, it doesn't know the T is 0. So what is the first slot? It just can't tell from the beginning. So the idea is, for example, in this, we can see we would have our initial incoming pulses and the local idea of how the slots are arranged. And we see this doesn't match. So one of the pulses falls into the guard time. So what the slotting tool would then do, puts the pulse into the next slot that actually makes sense. So in this sense, it would move back and put the pulse in this slot. That means we have now an assumed slot and the actual pulse. And from that, we can compute a difference. And this difference we use as an error signal and feed back to our TO computation, so to say. Meaning that with time, the T0 will be shifted until we go from here to actually the fitting slots. And once we have the fitting slots, we can decode the data from that. As a matter of fact, before we start actually transmitting data, we will add a preamble to train this whole machinery so that once the data flows, it actually is already set to the right slots. On top, so even once we are locked, we might still get a small difference, so a deviation from the perfect slot position. And as mentioned earlier, this we can use to derive we can use to derive the differential clock noise and compute the timing transfer. So with that being the heart of the system, we also need, as mentioned, the transmitter. And the way it works is pretty simple. So we have our data that we want to transmit stored in DDR memory, and we pass that to some custom FPGA logic, which then takes care of dividing the raw bytes into PPM symbols. So in this example, we would have here the series of raw bits, or if we want bytes, 2 bytes. And let's say we set our parameters to PPM 16. It will translate those raw bytes into the PPM symbols and then generate the pulses from that, and sampling with the 30s with 2 gigahertz, so 500 picoseconds bin width. So that's the general description of the system. And now I would like to talk about our flat set and our initial testing of those systems. And the basic idea, once again, it's simple. So we start with some data in our DDR memory. We put it through the TX modulator, which generates pulses. We send it through a cable all the way back, so hence loopback, to our TDC chain. We sample our timestamps. We go into the DDC decoder, which will derive the modulated data, and we write that back into the DDR. And ideally we should then have 2 chunks of data that match. So that's the basic idea. Reality is like this. So at the moment, we have our TX modulator working, so we can see we can get some nice pulses out of there. In this case, there's no data modulated, so the distance here between the pulses is all the same. Additionally, we have the limitation that the DDR interface that we are planning to use is not working yet. So instead, right now, we use a 2 kilobyte FIFO that we fill with some random data and loop infinitively. So instead of a long data set, we get a shorter set that is with high periodicity, but it works for our initial testing. Same issue then on the receiver side. So with no DDR interface, we need other means of reading out the data. Once again, we use a FIFO, which we then read out with this JTAG-based smart debug tool that comes with the FPGA. And on top, right now, we're only using a single TDC channel, so we're not using the 4 points characterization that I talked about before, but for simplicity, just use a single channel. So to put it all together, that will be then our system. So again, our TX transmitter generating pulses, feeding them back into our TDC system. And we split the testing into 2 steps. So the first one would be to check
if actually the timestamps we can compute or that we can record, if they are sensible. So test, meaning we would test this part, and our pulses would go to the TDC interface, and we would tap the data out here and see, yeah, do those timestamps actually make sense? Once that's achieved, we then go further into the PVM decoder and tap our data here again. And so let me go through the results of our testing. So this is rather pragmatic, so bear with me here for a second. So our testing signal is composed of just pulses with equidistance of 320 nanoseconds. So why this value? The reason is that on our receiver side, we have a resolution at the least significant bit of 4.88 picoseconds. And now if you crunch the numbers, we can find out that with this data rate, we would expect the 21st bit of every 16th timestamp incrementing by 1. So why those numbers? Again, for pragmatic reasons. So down here we see the readout from our smart debug FIFO, and we see 16 samples in one row, meaning if we jump one column, we would actually see every 16th timestamps. So, and now taking a closer look at those, we can count now the bits. So those are hexadecimals, so 1, so like 4, 8, 12, 16, 20, and that would be then our 21st bit, and we see it actually being incremented by 1. So meaning our timestamp capturing works fine. So that's good. And with that, we can go further and also then modulate some data onto our pulses. Again, we went for easy target, so OE in this sense. The additional zeros here, they come from the padding we do. And once again, we see the readout of our smart debug data, and we see the pattern we detect. It's close. It's not quite there, so we have OD. So we have an offset of 1 in the data capturing. And we did some further testing, and it's always this deterministic offset by 1. So yeah, we have to still do some digging, but still we're confident that it's a solvable issue. On top, however, we also have occasional bit errors here. You can see here we detected an F. So yeah, there's still some work to do, but we are happy about this first data contact, so to say. So what are the next steps? So first of all, yeah, we got to fix the DDR interface, not only for flight, but also because it makes the debugging way easier if you can just write to the DDR and check the data immediately. And that turned out a bit harder than we thought. So main issue here is we have several clients on the FPGA side that want to use the DDR memory. We have our TDC raw timestamps, so we have the TDC actual data. It's the same we have for the ADC chain that I mentioned earlier, and also we need to write our transmitted data to our logic. So our initial plan was to just connect them all with one XE interconnect and use this XE interface to write to the DDR interface. However, it turns out the IP that is delivered with the FPGA or the FPGA library is not fast enough for our targeted 150 megahertz bus speed. In this 150 megahertz, we actually need to shovel the ADC data with full data rate into the memory. So what we did is to write our own interconnect. So we have now a simple round-robin interconnect that goes through the different buffer FIFOs of the clients. We have an address manager that takes care that the data is put to the right points in the memory. And finally, we have an AXI master that is responsible for piping the data actually to the DDR. Turned out there was an additional issue, namely with our bus speed at 150 megahertz and 300 megahertz DDR interface, we got some strict timing constraint between the AXI master and the actual DDR interface. And in order to solve that, we were doing place and route. We want to have the AXI master as close to the DDR interface as possible. Means we put all the stress of the timing constraints on the other part of the design. And in order to relieve this from the higher timing constraints, we implemented some skid buffers. So why skid buffers? Well, our interfaces have bidirectional handshakes, so we cannot just simply add some registers to relieve the timing. And all in all, that's what we're working on the FPGA side. On top, in parallel, we are working to improve our flat set towards an optical setup. So right now, we just have the simple electrical test, but ideally, we want to have also an optical loopback or even not just a loopback test, but to have a transceiver or a transmitter and a receiver, both dedicated. For that sense, we would add a CPU board, which controls the FPGA board, and the CPU board comes with a CSAC, so a chip-scale atomic clock, as a reference. And then we would use our TX modulator on one side to drive an SOA, so an optical shutter if you want, to generate those pulses in the optical domain. Then in between, we have a variable optical attenuator. So this is meant to emulate or simulate the distance between the spacecraft. So the further they are away, the less power we get. So, and we can adjust that then with a VOA. Then on the receiver side, we would start off with our photoreceiver board and then have our RX board, which now only computes or only does the data decoding. And once again, that would be driven by another CPU board hosting a second CSAC. So with that, we could not, or we are able to test the data transfer in the optical domain and also do a computation of the differential clock noise between the two CSACs. So that would be our final goal. Yeah, and that brings me to the end of my talk. So let me quickly summarize. So the ClickVC mission is a CubeSat mission with low swap and a commercial off-the-shelf component. We're aiming for full duplex, high data rate, laser comm, ranging, and timing transfer. In this talk, I specifically focused on the TDC-based data and timing transfer. So I told you that we have a 4-channel TDC that is used to sample our pulses at 4 different points in time. I told you about the tracking loop that implements the PPM decoding. And then I've shown you our first testing in our flat set in an electrical loopback test. And finally, I presented our plans to extend this testbed to the optical domain with independent clocks. And last but not least, ClickVC launch, yeah, fingers crossed for early 2025. And with that, I would like to thank you for your attention. Yeah, any questions? Yeah, over there. So the question is about the expected power loss from the laser. Yeah, that's a good one. I don't think I have a number on the top of my head, actually. I would, but if you fire me an email, I'm happy to get the data and send it to you. Oh no, so in the BC mission, actually it's supposed to happen, yeah, on flight, so to say. So that's why we needed FPGA to have the fast processing capabilities on the CubeSat. Yeah.
Is there an advantage to doing it, like why not do it at the ground station? Like why do it up the CubeSat?
Well, I mean, you want to demonstrate that you can have this inter-satellite link, right? And later on, if you have, I don't know, maybe some relays, you want to jump from satellite to satellite and not, yeah, so.
What level of pointing performance do you think would be necessary to support the satellite-to-satellite optical links?
Another good one. Yeah, actually, yeah, I have to admit right now I'm focused on really the FPGA logic. So I'm not completely familiar with all the values, but once again, shoot me an email and I'm happy to get you the data. Yeah, there's another one.
How do you plan on interfacing the FPGA with your CPU?
What was the second part?
How are you planning on interfacing the FPGA with your CPU and the board?
Ah, gotcha. So in principle, this connection, right? Yeah, so that's, we use a simple SPI connection. We started off with some USB, but it didn't play that well. So yeah, we went back to the simplest that we could get, and actually, yeah, SPI was sufficient then. Yeah.
Your PPM coding, are you incorporating any data correction and detection, or is it just raw data?
So at the moment, it's basically raw, so no additional data correction.
I mean, I mentioned this preamble to train the decoder, but that's pretty much about it so far. Okay, I think we have no question, and actually out of time. Yeah, so let me thank you again for your attention. Yeah, see you around.
All right, everyone, please join me in welcoming our next speaker, Raj Raghulan from the United States Air Force Academy.
All right. Awesome. Awesome. Thank you so much, Devlin. All right. Good afternoon, everybody. Hope everyone enjoyed their lunch. My name is Cadet 3rd Class Raj Raghulan. I'm representing the United States Air Force Academy, and today I'm going to be presenting on Falcon Rad, our Falcon satellite payload that records radiation. So, you're all going to be asking, why do I need to hear about this presentation? I'm going to tell you about the South Atlantic anomaly. Now, we have a room full of smart people, so I'm sure you've already heard about this, but the South Atlantic anomaly is one of the major reasons why satellites that travel through this area of low Earth orbit have misalignments or data problems when traversing through this area. Basically, it's due to satellite space charging, due to high electron flow, due to the low amount of radiation that allows more radiation to come in from the Earth's into the Earth's atmosphere from space and causes satellite charging. Now, what does this entail? This entails our satellite data that's collected over this specific region to either have problems or not be calibrated correctly or some other form of issues that may affect your future satellites when flying through this specific part of the world. Now, the component that we made is actually the trailer in the Navy Talks tractor trailer analogy that they brought up before. There's a great explanation of exactly what our payload does. Our payload will exactly fit inside the Navy NASB bus trailer tractor component, and this trailer component records the amount of radiation that occurs in this area. So you can obviously tell by the size, we're within the 0.4 U of the CubeSat payload module that we were allocated. And these are the components that we used to develop this, this payload. So we see an Adafruit Feather M0 Adelogger. This was our major processing unit for our payload. We ensured that our component was programmed and was able to communicate with the PIB. We use a Teledyne commercial off-the-shelf microdosimeter to measure the radiation over the specific area. And we also had a temperature sensor, which was to ensure that the dosimeter was actually acting in the correct capacities. So in the case of our dosimeter maybe having a miscalibrated temperature, we were able to track that using this temperature sensor to be able to ensure that the data that we're collecting was in fact correct and useful for our payload. Now, a little bit about the electrical overview. This diagram explains exactly how we interacted with our electronic components, but what this doesn't show are the hours spent of naval and USAFA cadets going through each component, trying to understand how they connected with each other and also how they worked, because this was a much needed learning project for a lot of us. So we saw that the feather board was used. This was actually an iterative design. We started with an Arduino Nano, and we realized that that had specific constraints, specifically due to the memory allocation that Arduino Nanos couldn't support, and our feather board needed to be used to store that data when transferring it back to the PIB. We had to implement noise filters, DC to DC converters. We had to learn about voltage conversions to make sure our dosimeter was working correctly. There was a lot of learning that occurred that isn't shown on this diagram, but this was the end result of a lot of research and finalizations for our presentation. Now, this prototype testing board, if you saw Navy's presentation before, you'd understand that this is very similar to exactly how they wanted our payload to look. Specifically, with that right side indent or cutout where we were able to run wires from the bottom NASB bus up to our payload. In the bottom left, you'll see our feather board with its correct pinouts and exactly how we transfer data through RS-232 communication. In the top left, you'll see where our dosimeter will go. Obviously, during testing, we didn't want to use a real dosimeter because college students and $1,000, $2,000, $3,000 dosimeter don't work well together when we're angry about programming. So we used a bunch of voltage dividers in the middle to be able to simulate the amount of data that we're trying to collect through the dosimeter, so that when we do in fact finish our data collection with our voltage dividers, we're able to just plug in our dosimeter and use the data collected from that, and it'll work perfectly. So, communications protocols, and this slide also doesn't show the story that happened with the communication learning opportunities that I would say we had in the past weekend and past 2 semesters with the Naval Academy. What this shows you is the goal of how we wanted to communicate with the Naval PIB, or Program Interface Board. What this doesn't show is the amount of times that we had to verify checksums, ensure that we're talking through the same UART and RxTX communication signals, make sure that those signals are going to the right spots, validating the signals that were being sent, and also validating the data that was being sent. But the goal and end result of what we actually accomplished was that Naval PIB would receive a GPS timecode from its bus that would travel through RS-232 UART communication with that GPS timecode to our payload. Our payload would then verify that checksum that's associated with that GPS timecode. It would then ensure that that data is collected properly with that dosimeter attached to it, and it would send that instrument data packet straight back through RS-232 communication. And that PIB would receive that data, verify that it is indeed the data that they want, and send it, or store it and send it down to their command center. Now, lessons learned in moving forward in the way that we wanted to see this project progress is we saw this as a learning opportunity for integration challenges. So it is very simple to build a payload when you are the only one that you're interacting with. But when the team that you're interacting with is across the country, there's a lot of concerns in terms of how do we agree on the right dimensions, how do we agree on the right communications protocols. These are all challenges that we face, and while they may seem small for major CubeSat developers, for us as a team that's learning how to develop CubeSats, these are major challenges that we had to come across. We'd had to focus on the ICD, or the instrument control document, that ensured that we were working together and that we were on the same page for a lot of these components. Regular communication was a big challenge that we had to face, especially with cadets and midshipmen and tough schedules, but we were able to overcome a lot of those challenges and create a working test demo over this past weekend. So all in all, we documented, we learned about our experience, we learned about the ways to communicate through UART communication, we learned about what a dosimeter does, how it should be integrated, and we also were able to integrate with a real bus. So all in all, I think it was a really good project, and we learned a lot. Sync Navy. The last part of where we want to go with this project is specifically test our calibration at Kirtland Air Force Base. This will basically be us putting our real dosimeter payload under radiation testing, so that we're able to see how it holds up in space. And so while a lot of concerns may go around in terms of radiation hardening and why aren't you ensuring that your payload is properly calibrated for the amount of radiation that it's going to experience, we've already tested this exact payload system before in a similar project called IMESA. And so we are pretty confident that this payload won't be affected by the lack of radiation hardening. And so the data recorded will obviously help us determine whether all the instruments work, and it's going to produce calibration that we can use moving forward for all of our other projects. Any questions? Oh, yeah.
Do you do any software-based analysis for how rad-harded your components would need to be, beyond obviously looking at documentation and looking at that kind of basic?
Right, so the basic understanding, if I understand your question correctly, is you're asking, did we have any verification for, in a software side, for the radiation? Right, and so the way that I would answer that is, the way that the dosimeter works, at least the one that we have, it's not the most expensive dosimeter ever. It essentially collects data due to different, we call them cutoff voltages. So we're able to determine how much voltage it outputs based on the amount of radiation that it's collecting, and from that we're able to determine not a specific amount of radiation, but a kind of guess of, hey, this is the level that it's hit, so it's going to hit the next level at this point, and so on and so forth. So we have 1 through 5 levels, and that's the closest that we can get to determining the amount of radiation. But of course, that'll be, that there are better dosimeters that we could have used in the future that give exact values and are rad tested. So there isn't a software side of it, it's more just the hardware that will provide general guidelines on what answers we're looking for. Any other questions? Awesome, thank you so much. Appreciate your time.
All right, everybody, please help me welcome our next speaker, Marcus Murbach from NASA Ames.
Testing. Good afternoon. Hello, everybody. My name is Mark Murbach. I'm from NASA Ames, and I appreciate the brief introduction. So it's a pleasure to be here. This is an annual trip for us, and so in previous years, some of my esteemed colleagues from my team have presented. So this time I get to do it. Malachi may be in the audience, and if he'd shown up a little bit earlier, I might have had him do this. Again, I'm Mark Murbach. I'm the originator of this flight series called Nano Orbital Workshop, cleverly disguised as the TechEdSat series. This is I'm going to talk about a very unique experiment that we're proposing to fly, and it requires a cryocooler, et cetera. So we've gone from a simple 1U CubeSat all the way to a very complicated 12U that we'll talk about. It's supposed to work. They promised me. Okay, outline. Oh, we have an outline. Wonderful. So actually, it was a real pleasure to meet Jordy for the first time this morning. Of course, I've known him, and also his colleague, Bob Twiggs, whom I've known for a long time. So the two of them invented the standard, which is why we're here every year. And I really enjoyed his perspective on the importance of and what all of this activity has catalyzed. Okay, this is a great example. Previously, I was flying sounding rockets, so I had to have a series called SOREX, suborbital aerodynamic reentry experiments, interested in hypersonics, et cetera. This is still a viable program. And about 11, 12 years ago, I was offered a flight on, but the trick was that we had to fly to the ISS. And so I thought innocently at first, oh, this is great. This is a CubeSat. What is it? It's a long duration sounding rocket experiment. And that's how we treated it. A lot of other colleagues, having built larger satellites before, approach it from a large satellite perspective. And then that's probably not the way to proceed. As is pointed out, this is really highly experimental, risk tolerant, and this is how we advance technologies and make small corporations, et cetera. And then that's a representative of our 3U. We started with a 1U, managed to eventually, I'm not sure this is discussed during this session, but the ISS has become a lot more nanosatellite friendly. We were the crash test dummies, and it was painful the first time. Now it's actually, for us, it's almost a competitive advantage because we understand the hazard system. What we've since done is basically build our satellites to the safety standard of the ISS. And then if that's the case, then launch vehicles embrace us, and that's been very, very helpful. Anyway, the Nano Orbital Workshop, the TechEdSat series is what we're discussing. We propose this as test 17. Actually, is it tomorrow? The next day we go to Vandenberg and actually integrate number 11, which is actually delayed. We've already flown 15, so these things get out of sequence. But the whole idea was to make a variety of slots that we could then take advantage of and then keep on advancing the experiment technologies. I'm going to talk about this Doppler wind and temperature sounder experiment. That's the focus of the presentation. And again, it represents a complex system at the 12U wide. It requires a cryocooled experiment, a subsystem that requires a lot of power, generates a lot of data. So this is really the apex of a little bit about what we were talking about this morning, how we started off with a single U CubeSat. It could barely do UHF, and it advances to something that has a lot of onboard capability, 300 watt hours of power, and then we're also doing a lot of other interesting things in terms of onboard processing. So again, I mentioned who we are a little bit. I'm the fine gentleman up on the left, and then in the middle, I think there's a pointer here. Let's see if I don't bollocks this. They promised me there's, there it is, okay. So this is actually one of our previous Firefly flights, and was our core team plus some stragglers, so it's great. Our effort is a lot about education as well, exposing both young and older and medium professionals to this because it's very healthy. Also, I'm an adjunct professor on the side, and so it's fun to teach. Oops, I didn't want to do that yet. Let's back up. It works. Work? Okay. And that, you know, at every opportunity to try to, you know, remind people of this wonderful legacy that we're inheriting, right, including CubeSats. So this is our 1959 Titan 1, from which we can actually extract a lot of very useful information as far as a propulsion system and how they advance. So I like that. Okay, our key innovations were our Test 11 satellite has to do with a cognitive engine. We do, we're developing these autonomous communication systems using various different frequencies. Earlier on, we pioneered the use of L-band Iridium for quick command and control, which we found a lot better than UHF. So we pioneered that with some effort, and we don't fly without it. And then all the way to S, and then next flights X-band to the ground. What we're doing on this one is starting to set the precedent for a user-initiated service. So we turn on the system, the user, and it will negotiate with the Amazon Web Service ground stations, of which there are almost a dozen, that on a particular flyover, we'd like some time. If we can negotiate, it negotiates it automatically, and then we're able to download the data that this thing is going to produce. We're interested in lunar Mars missions, also the exobrake, which we discussed last year. We fly these both for controlled and just disposal reentry or deorbit. And then the what we call a brain stack, so we reported on that last year. This is evolving, so it's a set of GPUs as well as the first flight of a neuromorphic processor. So we have one already flying right now, the Test 13, and then we want to use that as a collaborative laboratory for a lot of interesting experiments that we can't even imagine yet. Okay, so what's the DWTS? So it's really cool. It's a Doppler wind temperature sounder, as I mentioned. It's built around, I think there's a pointers here. It was there. There's a pointer. It's a military grade infrared detector for tactical missiles. So it's already military grade COTS, if you will. And then the idea is you put this gas filter, low pressure gas filter on the top of it. And if you run the system at orbital velocity, it'll create a Doppler effect that will allow you to extract a temperature profile and wind velocity profile in a rather unique way with a fairly simple system. If we can get it to work, it may be groundbreaking. Okay, that's what, again, in the spirit of what the nanosatellites are about. So, so actually, we want to test this in orbit first, and eventually at Mars. With a version of this, then it has a different gas cell, then we can extract a lot of very useful information from the atmosphere itself and understand the dynamics of the global circulation, put these into the global circulation models, and have a order of magnitude better understanding of Mars. Well, how I found out about it was my colleagues at NASA Ames, Tony Colaprese, wanted to do this first, and I said, well, Tony, this is kind of interesting, but don't we want to prove out the technique first? So the proposal that we're developing is called Aeolus. Aeolus is the god of wind in Greek mythology. And so I thought, well, we should do a Aeolus Earth first before we do Aeolus Mars. And so that's what we've been doing for about a year and a half. Makes sense, right? So, I mean, if this is going to work, it can only work in orbital velocity. Build a cheap, quick instrument to be able to do that, and that's been the cadence. Okay, so here, the Doppler modulated gas cell correlation is what we use. And then what's interesting about this is the following, is if we're able to get this to work, then sorry about that, I had my glasses off, and so you were all these friendly blurs over there, but at least I can see this. These are some of the other atmospheric or orbital instruments that we see there in comparison to if we had a DWTS sounder in orbit. So you see that it works day or night. I think, I can't read this now, but also it does both wind and temperature, starting with the lower thermosphere all the way up. Some of these are also very expensive instruments. So if we can get this working, it's this classic Silicon Valley, smaller, faster, cheaper, et cetera. So that's what we want to try to test, the hypothesis to see how it works. So we want to start off with a rapid technology demonstration mission. Again, looking at these two bands, we would use a single gas cell, so therefore a single crowd cooler and lens assembly. And just with this nitric oxide, we can do a lot of work. If successful, then we would add two more apertures with nitrous oxide and a isotope of carbon dioxide. This will give actually more thorough coverage all the way through that. And if this works, then actually you would probably want a constellation of these things. And then with the advancements that we're seeing at NASA and industry, so we're involved in the CSP project, at the small satellite scale, then we could actually have a Starlink terminal on board the small satellite, and you can get all this information in real time. So it could be a potentially revolution in modeling and climate change and atmospheric prediction. Okay, so moving on. Also, it's really cool. This is an orbital depiction of the gravity wave effects that happens at the lower thermosphere. Well, actually, much low. But the whole point of this is that by understanding what's happening at these altitude bands, you can better anchor your calculations. So right now, in terms of wind profile prediction, it's not very good. This is what was currently available. And then the suggestion then is, actually this was done by a colleague, David Fritz in Colorado, that showing what happens with these gravity waves as they go over the Andes Mountains. Very interesting publication. So what happens is that this is what the sensor would do in comparison to what the real effect is. So you see this tremendous acuity that we just simply do not have right now with this instrument. Okay, so who else is flying cryocoolers? So these have attracted attention. Here's a short list of both us and a few other very ambitious payloads or missions based on the 6U, including our colleagues at the University of Hawaii that have flown the HiTi mission. And this is the second column that you see here. And what's interesting about this is it's going to, again, a very similar theme, using a different science, but it uses the same cryocooler. So we're paying careful attention on how it works, et cetera. And the idea is if this works, they prove it out, then you'd want a small fleet of these, and they would be able to monitor volcanic activity in far-flung places, and understand the effect of the aerosols in the atmosphere. So again, it's fairly complex. It's really challenging to put all this into a 6U box. One of these missions has had great difficulty. So the nominal required power is this, but when we're trying to cool the thing, then it could be up to 60, 70 watts continuous for a period of time. Okay, let's advance this. Again, we want to test the hypothesis, and then again, the objective is to get this up there as soon as possible. Even if we have to relax some of the initial science requirements. Okay, what that would do is that the measurements or the data reduction that we would get would not be in the same precision as a science mission that we would want to fly later, but it would show validate that the technique is working, and that's what's important. Okay, even if it's a short duration mission, this is actually in spirit of the things that we want to do with nanosatellites. Really quickly, of course, a block diagram. The optical instrument is this, but it doesn't live alone. It has requires a fairly complex interface system that actually makes it a orbital imaging system, and that's what we've been developing, which we can do at TVAC systems, et cetera. And then how we link this to our TESN core avionics, also the new operating system that we've been developed can accommodate this readily. And then just the power management, how we do all this is advancing rather well. Again, it's about 40, 50 watts during operation itself, a little bit more during the initial cool down period. But the interface is just challenging. We think we understand it now, and we should be able to build this one within a short order. Okay, and then this is what the orbit would look like on a first test. So here's a 12U. Why a 12U? We did look at building this into a 6U, as I mentioned, but it turns out that it could have required years more in order to do all the development that squeezes us into yet a smaller box. So at some point, all this is advanced. 12U slots are now available, and this comfortably fits into a 12U slot with a 300 watt-hour system, and that's what we're doing. So as this is flying along, the idea is we've looked at a variety of different orbits, but this is canted at about 25, 24 degrees. So we're looking at the limb as we go. We collect the data in 2-minute chunks, store it, and then use our cognitive engine in order to download this torrent of data in anticipation of something a little bit larger and better later on. Nothing really new about the ADCS. The pointing doesn't have to be very much, but what's important in order to reduce the uncertainty is the entire thing has to be synchronized with the PPS that comes from the GPS unit. So we have to know exactly where we are, exactly what we're pointing at. Within a degree precision is fine. We don't need arc seconds, so it's not. You don't have the precision required, for example, for optical communication. Again, and this was comfortable. It's still challenging. There's a lot of things we have to master so far, but the DWTS actually fits into a 2U size, which is really convenient. And then we build the rest of the systems, ADCS, around that, and that seems to be the way we want to do that. At the end, we also have room for an exobrake so that in these higher orbits, we can be good citizens and do a rapid disposal with a disposal exobrake, exo-atmospheric braking device that we've reported on before. Focal plane cooling, this is one of the challenges, is that because of the gas filter, you need to have that cool. If it's not, then what happens is it really distorts, it smears your uncertainty on the data that you're gathering. And so we're cognizant of that. That's one of our key thermomechanical challenges. But I think we can actually extend the cryo system so it's actually providing cooling on the filter, okay? So those are the level of details that we're looking at. Right at the first pass, we want to do just simple radiative cooling. That's going to be sufficient to get it down to the required lens temperature in order to, again, get reasonable data for it. But again, the spirit of the first one is to understand how to fly that so that we can turn around within 12 and 24 months and build a science one with more capability. So the first one, relax the requirements a little bit. As we advance, we'll know more of what we're doing. Okay, and then the thermal modeling. Again, we've done this quite a bit for different orbits, but this is one of the runs, for example, where we start this, and several orbits later, we're within the desired lens temperature realm. Again, this is a little bit idealistic. Even if we started over here, as I say, 220, 250, it would be fine because we could validate the hypothesis regarding the Doppler wind data manipulation and analysis. Okay, so that's where we are. So our TechSat series, our nano-orbital workshop, is we're developing this as a good example of an advanced payload now, as we've evolved from 1U from 12 years ago to 16U. And then it involves the advances that we've seen in our power capability. Our comm has dramatically advanced through different RF wavelengths and channels, and also be able to do eventually a lot of onboard data processing and actually train it with this AI/ML lab that I mentioned. So that's kind of exciting. The use of the tactical cryocooler combined with this IR imager enables a lot of different missions that we have not even thought about before. So I showed you an example of about 4. We'll see more of these. And it turns out in about a 12U, this is very doable for this initial kind of demonstrative work. And I think that DWTS, it's a mouthful, but if we can validate this, again, will go to a triple aperture, then a small satellite with a lot more capability, and eventually a fleet. And then, out of the kindness of our hearts, we'll send a couple to Mars. So that's a good example of how to do this rapid development, raising the TRL very quickly as we can. So this is pretty happy about the advance. And then this, again, I mentioned the AOLS Earth. This would be the Test 17 would be the first in the series. And then followed by the AOLS Mars. And so this makes kind of a nice full story. And again, why we're doing it all, and how it's a nice confluence of the various different work and evolution of all these capabilities that we've been doing for the last years as a community and also as our team. With that, let me open it to any questions you might have. Now I can see you all, okay. Yes, sir. Yeah, actually we lied a little bit. It's probably mid-wave infrared. It's actually tied to this particular experiment is really, this is a nice, nice confluence of technology for the science we're trying to develop from it. But yes, as you point out, there's lots of other opportunities to fly cryo-cooled infrared detectors looking at a variety of different science, both astrophysical or Earth. So it opens it up, and you just basically need a lot of power, a lot of data control, and then you can do this in a 2U compartment. Anything else? Okay. Well, I'll be around for a couple of days, so thank you very much for your kind attention. Thank you, everybody.
All right, everyone. So we will be taking a short break, and we will be coming back at 3 o'clock. All right, everyone. I hope that you all had a nice break. And I would please join me in introducing our next speaker, Tristan Madison from the Aerospace Corporation.
All right. Good afternoon, everyone. I'm Tristan Madison, member of the Thermal Control Department at the Aerospace Corporation. And today I'm going to be talking about a small satellite deployable radiator study that myself and some colleagues have been working on for about six months here. So to give some background, we're seeing a trend in the industry across civil, commercial, and defense sectors, where we're seeing smaller satellites with increased capabilities. We see this sort of in the NASA smallsat CubeSat fleet. We're seeing this in commercial space with the rise of Starlink and the multiple missions that are going on with SpaceX. And then also, I have a link or a snippet from a Space News article from October showing that the Space Force is looking into small GeoSat communication satellites. The issue with this is that with smaller form factors and increased capability, we will eventually have larger or warmer temperatures in our spacecrafts. And this can lead to challenging thermal management issues and the need for deployable radiators. There we go. And then so to make the case of why we might actually need a deployable radiator, if you didn't believe me just from that one slide, we'll do a little bit of math here, a simple energy balance of a spacecraft. So the energy balance is basically your environmental loads, albedo, solar, planet shine, plus your generated heat load, must equal your stored energy and your radiated energy out to the environment. Your radiated energy is related to the radiator area, your emissivity, Stefan-Boltzmann constant, and then your radiator temperature and your sink temperature. To a thermal engineer, when you hear the phrase increased capability, you automatically think increased heat generation. And so if you kind of extend this heat balance, you're going to get this sort of relationship. And when you look at the environmental loads, your environmental loads stay the same. Your internal heat generation now increases, and then your stored energy remains roughly the same. So the only thing that can change really is you have to increase radiator area in order to keep up with this generated heat that's generated inside your spacecraft. Provided that you're basically at a similar temperature that you're radiating at. So increasing the deployable radiator or having a deployable radiator is all part of a way to enhance heat rejection in small satellites. And there's several metrics that you can consider when looking at these deployable radiators. The first is just raw, The first is just raw, the total radiator area. And you might want to look at metrics such as how much area per unit volume, essentially how tightly packed can you pack that deployable radiator. And you also might want to look at the total area per unit mass, making sure that's not prohibitively expensive from a mass perspective. And then as well for your specific mission, you might want to look at the specific operating temperature and make sure that your mission can then work with that deployable radiator. And there's some common design choices to increase the total radiator area. Traditionally it's just a deployable radiator itself provides that area, but also you can look at alternative form factors such as DISSAT from the Aerospace Corporation and a joint project with Aerospace and NASA as well. The other thing that you can look at is radiator efficiency. And typically this might look like the ratio of the net radiated power to a black body perfect sink, or you might want to look at how isothermal your radiator surface is in order to sort of understand how that efficiency plays out. And some of the common design choices for these types of systems are high conductance interfaces as well as coatings. And the last knob that you can turn is conductance. And that typically refers to the conductance from your bus to your payload, to your radiator. And that's typically measured in watts per Kelvin. And again, when you look at some of the common design choices for that hinge and that interface, you're looking at high conductance materials as well as two-phase heat flow options such as heat pipes and oscillating heat pipes. But what's important is that any sort of integrated design strategy will have to use all three of these in order to come up with a full solution. And so it kind of brings us to understanding and kind of the motive for why we conducted this deployable radiator study. Our objective is to be able to survey the existing landscape of deployable radiators, understand what's out there currently, and what are the performance metrics that each of these systems are presenting. We can sort of develop, we want to be able to develop sort of useful metrics ourselves, as well as propose sort of technical performance targets. Our approach, we did a literature search. We also interviewed industry and academia on their specific systems in order to understand how these systems work. And then perform some independent calculations ourselves to understand and compare and contrast some of these systems. The overview, we interviewed over 11 different companies and universities and different ultimately leading to 14 different technologies with a wide range of technology readiness level, from 6 down to 2. Not working. So the next few slides will just kind of give a pretty high-level overview of each of these systems to describe kind of what is currently available and out there. So the first two are kind of canonical examples of what a deployable radiator are. When you think of a deployable radiator, you think of a panel that can just extend from your spacecraft. And Redwire, as well as thermal management technology, each have a system that looks like this. The Redwire system is a purely conductive system. It has a high efficiency thermal hinge and then a conductive interface across that hinge to help move heat from the acquisition plate to the radiator panel. Thermal management technology similarly has a heat acquisition system in this bar here that can then open up and deploy into their radiator here. And this radiator is a high efficiency radiator but uses embedded heat pipe technology. So what we're seeing is that industry technologies consist of both a sort of classical conduction approach as well as the integration of two-phase heat transfer. Thermovant is also getting into the game of deployable radiators. In particular, they have two technologies that they have been developing. The first of which is what's called local plastic deformation, utilizing their oscillating heat pipe technology. The OHP integrated deployable radiator for the local plastic deformation effectively uses plastic deformation of the panel itself to deploy and then make sure that it stays deployed. And then that hinge is made out of the same material as the radiator itself. A different concept that Thermovant has been working on is using those oscillating heat pipes to then roll up and create a cylindrically stowed radiator that can then unfurl and create a large amount of area, or display a large amount of area for heat rejection capabilities. And again, both of these also use oscillating heat pipes, which again is more of the two-phase flow, a two-phase heat flow that we're seeing. Looking over into academia, we're seeing a range of novel solutions, some of which some of you in the room are probably very familiar with. BYU is looking at triangular fin deployment as well as radial fin deployment using a bimetallic coil. The idea behind this type of radiator system is that the bimetallic coil gets warm, it deploys the radiator, and then as the coil becomes cool and you've rejected the heat from your spacecraft, those bimetallic coils contract and then undeploy the radiator. So you get a switching and a sort of a variable heat rejection capability for these types of systems. Similarly, for the BYU radial fin, the fins are actually inside the spacecraft and then extend outward and then retract in. Similar bimetallic coil system, but a different form factor and can help with sort of switching capability, so a slightly different application. The JPL Cal Poly project for AmDrop uses additively manufactured heat pipes, or oscillating heat pipes, and again, is a sort of another example of how we're starting to see more of these oscillating heat pipes, more of these heat pipe embedded technologies in these small spacecraft radiators. Another example of a fully fledged deployable radiator system, but deserves sort of its own slide here, is the active thermal architecture. And this active thermal architecture from Utah State is effectively its own subsystem. Heat goes in to a sensor that is connected to a cryocooler. That cryocooler is connected to a pump fluid system that is then connected to a rotating fluid joint. There's feedback from this motor that's connected to that joint based on the temperature and the pump fluid loop. Sorry, the pump fluid loop there. And then that dictates in turns the deployable radiator, so that you get variable heat rejection capability for this type of system. Continuing on, we're also seeing, in terms of actuation of these deployable radiators, the increase in shape memory alloys. The first technology on the left is from NASA and Texas A&M, using a shape memory alloy morphing radiator. The principle behind this radiator is that it's initially cylindrically stowed a single panel. There are 2 shape memory alloy wires that connect diagonally across that radiator panel. As that shape memory alloy increases in temperature, it pulls apart the radiator, and then again, as it gets colder, it can then start to push the radiator back into its original shape. Additionally, JAXA has also used shape memory alloys as a means of actuating their redeployable radiator, where the shape memory alloy increases in temperature. It uses a bias spring to then open up their deployable radiator, and then as that radiator dissipates its heat, gets colder, it can then sort of has some hysteresis where it can come back to its deployed state. And then we're also seeing other means of actuating their deployable radiators. For example, Pumpkin has a rollout deployable radiator where a vapor chamber can be heated up. As the pressure in that vapor chamber increases, this rollout deployable radiator begins to unfurl and then acts as sort of a heat pipe type system to then bring heat back into or to dissipate its heat and then bring liquid back to the vapor chamber. So when we take a look at all of these types of systems and look at what are some of the performance trends that we're taking a look at, the first thing that we see is that the max TRL is around 6 or 7, and the minimum TRL is around TRL 2. We see a radiating power for most of these systems, a radiating area, up to about 1 meter squared, and then a radiating power of about 100 watts on average for most of these systems, as sort of what the current state of the art is. The operating temperature range tends to be application or fluid specific, depending on if there is two-phase flow or not. And what that really means is that customers have options depending on what their specific mission application is. And additionally, what we're seeing for deployed area to stowed volume ratio is that the conduction-dependent radiators tend to have the highest values for stowed volume or deployed area to stowed volume. And what we want to be able to see is low areal densities. But ultimately, the solution space for deployable radiators in small size is vast, and there's many different options for customers in order to find the correct fit for your specific application and your specific mission needs. So if we can plot the mass versus the radiator area for each of these systems in order to get an idea of what the areal density of each of these systems is. And the NASA Space Technology Directorate identified that the current deployable radiator technology has areal density as 19 kilograms per meter squared, and then further identified that getting below 6 kilogram per meter squared in your areal density will help enable lunar missions and beyond. And a quick look at this graph shows that most of these systems are already below that 19 kilogram per meter squared threshold, and many of them have already hit that 6 kilogram per meter squared benchmark. Ultimately, what this really says is that we need to continue TRL advancement for these technologies to allow for further mission capabilities and mission opportunities. If we take a closer look at the deployed area to stowed volume ratio, we can kind of set theoretical performance metrics for both an externally mounted panel radiator as well as the cylindrically stowed radiators. So for a externally mounted panel deployable radiator, that radiating area to stowed volume is equal to 1 over the thickness, assuming that you have no structural components that offset your panel, and that your panel just is right up against your spacecraft. So this effectively acts as a maximum value for your panel radiator. For cylindrically stowed radiators, your radiating area to stowed volume, provided that your structural support can fit inside this sort of prism that I've drawn, you get a value of pi over d. But that represents a minimum value for cylindrically stowed stowed radiators, because effectively, if all your structural support can be in this prism, then you effectively can get more area by increasing the number of turns inside that diameter. So you get a benefit by increasing the radiating area here, and therefore this ends up being sort of a minimum for these types of systems. And we can take a plot of these ratios, the stowed area or deployed area to stowed volume. This line here is the area when the area to volume ratio equals 1 over thickness. And we see that many of these systems, these conductive type systems, are either on this line or slightly below, and average about approximately 100 to 200 per meter for that metric. This provides an opportunity to look into alternate ways that we could increase that deployable area, and why the sort of evolution to roll out radiators is kind of what we're seeing in the industry. For the rollout radiators, we have area to stowed volume versus pi over d. And we see that even though they, in terms of raw value, are a little bit below those conductive and panel type radiators, we see that they're still pretty far away from that theoretical minimum, and there is opportunity to grow and continue to increase that value so they're comparable to the panel mounted radiators. So just to quickly summarize, so we're observing a need for increased heat rejection and deployable radiator area for small satellites. We're seeing technologies currently being developed that already have low aerial densities, and we need to continue to show development and advance the TRL in these technologies, which means that we kind of need to collectively look for more flight opportunities for these systems. We're definitely seeing more two-phase heat flow options. Embedded heat pipes, oscillating heat pipes provide high heat transfer and improve the heat transfer from the bus to the radiator, making a more efficient system. And then lastly, some of the options are, so there are some options available to increase raw area, and the rollout radiators that can provide more of that radiating area in order to help increase the heat rejected. But there are still challenges that these systems still face. So, and with that, I'll take any questions. Yeah. Sure. Right. That's a good point. That's one of the reasons that we're probably seeing those rollout radiators be coupled with oscillating heat pipe technology as well as general embedded heat pipe technology, because that helps transfer the heat for further lengths. So if it was just a panel that opened out, the answer would be yes, and then Q, two-phase flow.
All right, sorry about that, but we're all out of time for any further questions. With your help, please join me in presenting Soo-Jong Park from Kyunghee University.
Hi everyone, my name is Soo-Jong Park from Kyunghee University. I would like to present our linear astigmatism-free 3-mirror system that is very good for EOIR camera onboard CubeSat. There are so many people in this conference that are from various backgrounds, so I first have to introduce myself. I'm an astronomer and specialized in optical and infrared. And I have been developing ground-based and space-based telescope and instrument for 30 years. We astronomers are very familiar to use electromagnetic wave. I have to define what infrared we are using. Infrared is very wide range, but short wavelength SWIR is not my goal. We try to use MWIR or LWIR because that is what we can observe from in the night, or in other words, it's a summer radiation. In astronomy, my research field is to observe star-forming molecular cloud, and you can see there is a dark shadow in nebula where stars are forming. You can see in optical band. If you do in infrared, this dark shadow becomes very bright because that emit by itself, and both EO and IR can give very good information when you study this star-forming cloud. We can also look down from the space to the Earth. So in case of EO, it's a reflected light from the sun, and this you can see the coastline of EO image. If you use IR camera, you can see very different view in the same scenes because infrared is from directly radiated by itself. For CubeSat, the EO camera is very popular these days, especially Planet Labs make several hundred EO camera on board, and now it's orbiting and observing the Earth. But I don't have any information of their camera system, but based on their pictures, I expect their camera or optics is catadioptric system. Catadioptric system is on-axis reflective with refractive, so lens correctors. So that is very efficient for space application. However, both on-axis reflective and refractive system is not really appropriate for infrared. So we don't see many infrared camera on CubeSat. I can briefly explain why, and we can see what is the nature of infrared. I can compare with just the EO camera case. These days, you can buy very nice smartphone with 5 lens modules, and you can just take picture in EO. That is same, so you don't have to worry about anything, just buy one smartphone and just use. If you do more serious about your pictures, you can buy like a DSLR camera, and in this case, you can also select body, I call sensor and lens. So lens is very expensive. The reason I have to classify the sensor and optics is infrared camera is mostly developed by electric engineers, and electric engineers usually do not worry about or are not interested in optics. So infrared optics is underestimated for their use. But what required for infrared optics? That infrared, you need large aperture because the longer wavelengths has large diffractions. Also, infrared, you need, the signal to noise is very low, so you need fast optics, very bright lens. So optics with large aperture with short focal length is very difficult to make. This is one example made by Korea Astronomy and Space Science Institute for survey of the whole sky in infrared. So one of the good solution is to make this refractive optics. Of course, this camera is not for MWIR. It is short wavelength, but it is very successful mission. However, infrared camera with a refractive lens. It has good advantage, but it has a problem in choosing lens materials, which is very limited. And also, lens is very heavy. You can have very good optical performance, but it is heavy, and also optomechanical structure becomes very complex. For space, people also use on-axis reflective telescope, which is, we have been developed on-axis reflective telescope for several hundred years. However, this on-axis telescope has central obscuration by secondary mirrors, and infrared need a short focal length, so it should have a very big secondary, and the secondary mirrors degrade the optical quality. People use off-axis reflective telescope, so that is possible, but the problem is this off-axis reflector has very strong linear astigmatism. So our work is the design which there is no linear astigmatism in off-axis reflective system. This is a theory based on Professor Seung-hyuk Chang. He had a series of theoretical work to study the geometrical optics, and he found solutions where there is no linear astigmatism exist. So this is simple comparison of our optics. So we sometimes call Chang, because Professor Seung-hyuk Chang made this, so some people say just the Chang theory for off-axis. This off-axis is confocal, and traditional off-axis is coaxial. So coaxial is use the same optical axis for primary and secondary. And however, confocal off-axis do not share the optical axis. Instead, they just share the focal point. In this configuration is different from previous development. And his theory starts from this vortex equation. Usually, when you take geometrical optics class, you first have to learn this vortex equation and have to solve equations. Professor Chang's theory starts from localized regions because we use off-axis, so vortex equation becomes different at the beginning. I don't go deeply on this theory, but when you derive these aberrations, there is a linear astigmatism terms and comma terms. It is interesting that off-axis comma is same as on-axis comma, and the linear astigmatism term is eliminated at special conditions. So when you design the optics and you follow these conditions, you can have optics without linear astigmatism. So the coaxial off-axis is traditional way of using off-axis, and you see very strong linear astigmatism. Confocal off-axis, the new theory, has no linear astigmatism, and only comma aberrations exist, which is exactly same as on-axis telescope. So this is the theory we use. Professor Chang also extend this theory to multi-meter system, so we can make 2 meter, 3 meter, 4 meter, but you can compare this 2 meter system and 3 meter system, because if you have a 3 meters, you can have more efficient way of reducing aberrations, and also it becomes more compact. So we use this 3 meter system. However, I have to note that our 3 meter system is different from TMA. People use TMA these days, but TMA is based on confocal, traditional confocal of axis system, and our LAF TMS, TMA is based on coaxial system. Our TMS system is confocal, so coaxial and confocal is completely different optical theory. So our system is different from TMA, so we call this is TMS. So we had a design for Messier project, that is a low surface brightness galaxy surveyor, which we are proposing with France. And the left one is traditional TMA design, and the right one is TMS. You can see the size scale that our TMS design is about 40% of the weight of TMA design. So if you use this technique, design technique, you can have more compact and much better with much better image quality. So we use this technique, design technique, to apply several development. Before that, we also have to develop the freeform mirrors, because our the TMS need freeform mirrors, and we make this in aluminum. So if you make mirrors in aluminum, there are a lot of advantages, but it is a little difficult to make. So we spent about 10 years to make these mirrors. Finally use diamond turning machine and MRF. That's one of dissertation project of my student. We made a proto-model space infrared telescope that didn't go to space, but we can test our design idea with a real telescope. That was quite successful. And we also applied our design to METS. METS is Swedish science satellite to observe the rim of the atmosphere. And that was launched about 1.5 years ago. And this is the first space telescope which has this designed by Zhang theory, our TMA system. And also that was part of my another student dissertation project. We also make MWIR and LWIR dual sensor camera for drones. If you make all the optics in reflective system, you don't have to worry about wavelengths. Any wavelength is acceptable. So dual camera or hyperspectral camera has very good advantage in reflective system. So this is the recent one, and our most recent project is EOIR onboard CubeSat. That is, we have a 3-meter system and share the same optical system for EO. So the green one is EO track, and red one is infrared, MWIR infrared. So we have a dichroic mirrors to split the EO and IR with the same optical system. So this is our current project to make, and I hope within a few years this EO/IR satellite will be on space. So I will summarize my talk. At the beginning, I said I had been developed astronomical instrumentation. So most of my technology is from astronomy background, and optical technology is very important in space missions. And we developed several technology to make the real telescope. Okay, thank you. Any questions? Yes, please.
Can you explain how you align the mirrors
Okay, you mean optical alignment? Yeah, I didn't say about optical alignment because that is the most difficult part and we spend most of the time. But the basic idea is as long as we make this in aluminum, we can just bolting the aluminum mirror very strong and safe. So once we aligned on the lab, and that is strong enough on the space. So the idea is to use everything in aluminum. So mirrors and optomechanical part are same materials. Of course, there is many difficulties. So alignment is the most difficult part of our project. Any other questions? Okay, thank you very much.
All right, everyone, please join me in welcoming our next speaker, Kelly Williams from Cal Poly Pomona.
Good afternoon, Cube Crafters. I am very excited to be here, and I'm very excited for you to hear my presentation. I am Kelly Williams. I am from Bronco Space at Cal Poly Pomona, and this is a preliminary architecture for a modular and scalable edge computing system for small spacecraft. So just some background on what we do over at the Bronco Space Lab. We have our two major projects that really closely relate to why we wanted to make this. So first off, we have Bronco Ember, and in this little video, you can see it detecting wildfires using autonomous edge computing to remote sense these wildfires at a distance. But we get a lot of false positives with this because it can be very difficult to regulate these machine learning models and make sure that they have good data and filter through those false positives. And then we have Moonfall, which uses a machine learning model to autonomously map precision land and do hazard avoidance. So this is just a 3D rendering of the system mapping the moon. And just in general, we do a lot of different kinds of CubeSat development, and we really focus on our CubeSats being open source and utilizing the open source community. So that's something that we really prioritize in our different designs and integrations in the lab. So here's our top 3 that we really consider to be industry standard kind of open source CubeSat platforms. So we have Arsat, which was developed by Portland State University. I'll get into a little more detail of that in a second, but we also have PyCubed, which we use to develop our Prusa system, which we have another presentation on during this conference. And we have the Artemis CubeSat, which is what's most commonly used, we think, and it's pretty traditional. So going into more detail about the Arsat, this is the C3 card that they put in the system. So we believe that this is a really good single solution, single board solution for a flight computer. And it's really interesting to us because radiation tolerance is really an issue with hardware. And this presentation is really the hardware focus of our project. So they have a radiation watchdog scheme that they implement in the board that makes the components in the board a little more radiation tolerant and protects them from that space radiation. So that's something that we're going to try to implement in Scales and kind of use this as a springboard in our design. So what is Scales? Scales stands for Spacecraft Compartmentalized Autonomous Learning and Edge Computing System. So the question we're trying to answer with Scales is how do we create a platform and a framework that allows these AI models and machine learning models to play around and learn and collect data in such a variable environment without it breaking the system, and making sure that this framework is really easy to adapt and change and can auto-regulate. So to answer that, we're thinking of making a hardware software integrated system that makes that reusable environment to let those models play around and collect data. And we're really prioritizing using commercial off-the-shelf components to, again, emphasize that accessibility. and to enhance on-orbit computing and like enhance the kinds of options that you have during the open source community to implement these models in a low-cost kind of way. So in the industry, there's like, you can categorize it based on hardware and software issues, and again, I'll mostly be focusing on the hardware, but we know for, more traditional CubeSats, microprocessors are traditionally used for the flight controller, but for something that needs a high computing power, like using AI and machine learning models, usually FPGAs are used. But the issue with FPGAs is that, yes, they are incredibly specialized, and they're very, very good at what they do, but they can't really be changed very easily once they're once they're deployed, and the up costs on them are kind of crazy, and they're very hard to manufacture and code because it's a very low-level machine language. But the issue is there's not very many radiation-safe hardware alternatives available off the shelf. And the software side, which Alex will be focusing on in his presentation tomorrow at 10:20, if you want to stick around for that, the AI models only have about 85% accuracy on Earth, which is like okay, but when they're in a space environment, the data is such a huge variable and it's not consistent enough for them to be reliable. So it can become an issue when implementing them in a system because you can't trust them, and you'll again get a lot of those false positives. So here's one of our potential use cases that we're trying to think of with scales. So we're kind of identifying our potential use cases based on a couple of criteria. So we have a short description of what the use case would actually do functionally. So in this use case, it's a remote sensing satellite that uses an algorithm to process these images and, give an output of what it sees and detect and track what it sees. So scales would get the input, the output, and we categorize it also by a control request of like what the model wants from the system and the risk that we feel that control would pose with an unreliable model, and how we think scales should respond to that risk and how to like mitigate that to control the model and make sure that it doesn't go outside of the hard bounds and break the system. Another use case we have is a navigation system. This one is a little bit more strenuous and would be a little more devastating if it failed, if we got false positives with this. So the biggest risk is, since these algorithms are very unreliable in a space environment, those false positives can not only be a waste of resources like fuel and time, but potentially, if it's giving back a false positive, it can put the spacecraft in a dangerous situation. It could bump into something depending on where it is, or it could just completely go off course if it gets a false positive. Or if the algorithm is lagging, then the controls can be, kind of one step ahead. Well, the algorithm could be one step ahead of where the controls are, so that can also be a risk. So we're trying to think of different ways that scales could respond, and we're still kind of conceptualizing more responses for scales in different use cases, but just in general, we're trying to enforce those hard bounds to make sure mistakes don't happen. So here's our general architecture. The way that we're trying to implement these concepts is with two main processing boards. So we'll have a flight processor and an edge computing processor. And the edge computing processor will be more powerful and house those machine learning and AI models. And it will communicate with the flight processor to ask for those inputs and outputs and request, actions and movements. But using NASA's F-Prime software, which again, we'll get into more detail on tomorrow, it'll monitor the overall system health and decide if that action is viable and worth the risk. So in creating these hard bounds, it allows these models to play around and make mistakes without risking the vitality of the system. So more hardware detail, we have two main options for our flight computer. We're mainly looking into the Octavo Systems chip because it is used in the Orsat C3 card that I discussed before that we're kind of building off of. So for testing, we're probably going to use something like a Pocket Beagle that uses this same chip so that we can figure out how we want to implement it and make the two processors talk to each other. And then eventually we'll probably implement this chip into a custom PCB to make things a little more streamlined. For the edge computer, it's really important that the edge computer has a lot of processing power, but also a lot of usability for the open source community. And the Jetson Nano utilizes NVIDIA and uses CUDA, and a lot of people in the industry and in the community use CUDA for AI and machine learning development, so it would make it a lot more accessible, and it would make it easier for people to understand because they already have so many resources for it. So for interfacing and testing, how are we going to do this? That is an excellent question. So my main issue as a hardware intern is we're trying to figure out how to space-proof our hardware. And really, it all just comes down to testing. We don't have a concrete answer on that right now because we're still in the beginning stages of this project, but mostly we're going to be doing radiation and thermal testing on the hardware because those are the two biggest factors that we're trying to get over in the industry need. So there's always, putting different kind of radiation tolerant metals around the components. You could use aluminum, you can use stainless steel, or incorporating other kinds of radiation safe metals into the actual design of the PCBs and like covering those components to make sure that the vital parts of those processors are safe, and making sure that as we're doing these testing, we figure out why they failed and at what point the life expectancy starts to diminish. And again, on the software side, just touching on it a little bit, how do we get the two main boards to talk to each other? Hardware-wise, we also need to think about like how, not only how they're talking to each other, but how the sensors can be in that bridge of communication, because we want to make sure that you can put any kind of sensor into the system and it'll work and communicate with these two boards to make it fully modular. So optimally, we're probably going to design a custom PCB to interface these two boards together and manage the data streams and the ports of the new sensors. So our project timeline, it's a 2-year project right now. The first year is mainly going to be design and integration, and the second year is mostly testing and qualification. So these dates are a little off right now. We're going to push these back to give a clean start date in the summer. But this kind of just gives you an idea of the kind of tasks that we're going to be completing in each phase and how long each phase is going to last. So in the first year, this is essentially just like the main few points that we're going to be hitting. And I know the text is really small, but it's just mostly conceptual. And then moving on to the second year timeline, again, this is just conceptual dates, and I know it's really small, I'm sorry, but we have different kinds of testing that we're going to be doing and like when we want to hit those benchmarks for testing. And we're really looking to getting started, and we're going to earnestly start this summer, and really looking forward to giving you another update next year with more info and more progress. So thank you so much for listening, my little cube creators. If you have any questions, now's the time, or if you have a really long question, you can email me or find me after. So yeah, I open the floor to questions, if you have any. Yes. I don't have a concrete answer for that right now because we're still, again, in the beginning stages of development, but I would think that they would need to interface to work with our ground station to be able to send that data back and forth, but for other people to use it, it kind of needs to be left open-ended so that they can kind of plug in their own data and criteria to make it adaptable for what they want to use and like their own ground station, for example, if that answers your question. Okay, yeah, that's definitely, come find me after and we'll discuss. If there's any other questions. Yes. Where we're going to put the data to train? Well, a lot of it, you kind of begin the training for the AI models on Earth, so you kind of send them up there with this like preliminary ground of where they already stand, and then the accuracy will drop so much. So kind of the point of scales is getting that accuracy up in space and like getting the data and allowing them to retrain without risking the system, if that answers your question. Anything else? Thank you.
All right, everyone, please join me in welcoming Imran Farouk from Oklahoma State University.
Well, thanks for having me. It's great to see everyone here at CubeSat Workshop. This is my first time at the CubeSat Workshop, and I'm happy to talk to you about some of the work that we're doing at Oklahoma State University. Oklahoma State University is probably better known for some of our UAS work, you know, from the early 1990s design, build, fly work to the competition that we now host, Speedfest. And so these are gas turbine engine powered, rocket powered UAVs, and we'll be hosting that competition this next Saturday. And one of my contributions to that has been to start to understand how insects process information and how we can do aerial swarming in GPS denied and RF denied environments using insects as model systems. And so we have live insects. We study how they interact. And then use that to translate to UAVs. You know, getting into sort of more space-related topics, we have you know, a number of eclipse ballooning projects. Probably the last, you know, the most recent one was the eclipse ballooning project, where we started about 25 hours before the solar eclipse, which had totality in Oklahoma, and launched, I think, about 65 balloons. Oklahoma State does have systems that are in space right now. This active tissue equivalent dosimeter launched in December and is on the ISS. The previous version launched in 2018 experienced a percussive, an astronaut kicked it accidentally, and so the SD card was loose in there. So this is in a quieter section. And is gathering data. But what I'm here to talk to you about is orbital debris cleanup and active debris removal. So just some context on orbital debris, the orbital debris environment, and sort of the associated risk levels. We currently work off statistical sorts of models where every event in sort of that density flux is associated with a particular cause, a particular impact that has led to orbital debris proliferating. And so we basically take that and then map it out to, you know, what the debris flux, the orbital debris flux looks like in a particular orbit, an angle, inclination angle and altitude. And there are, you know, these are real events, right? That's statistical modeling, but we do see these, you know, a couple months ago, and we just found this out about 2 days ago, how close two satellites came within 33 feet of each other. That would have basically been another peak on this plot. And so it really got you know, NASA folks especially concerned. One of my grad students working on this, who's now at NASA Johnson, had some NASA folks leave during one of his orbital debris talks because the ISS had been hit recently. So this is kind of you know, this is kind of sort of the context. And so the first thing is, where is this orbital debris sort of concentrated? What is the highest risk area? And so where is it? You'll see that there's sort of a lot of orbital debris concentrated around sort of 1,000 kilometers, 1,000 kilometers AGL, about almost sort of near polar orbits. And so that's probably the first thing that we notice is where the debris is, and then we have to think about, you know, what is the risk level, right? So in terms of the size of that. So to do that, I want to look at basically the human space habitats, the upcoming human space habitats, and here's 4 examples of what that looks like. And basically where those are scheduled to operate. And they're all kind of at the 400 kilometer height, about low eccentricity, about 51.6 degrees inclination. And that's basically where ISS is right now. You really don't want to go about 500 kilometers for basically radiation reasons. And the other thing is basically as you go higher, this debris persists for longer, you know, centuries to millennia. Anything that is 10 centimeters and bigger, you can see and track from ground-based radar. So that mitigates some of the danger, but these are hypersonic, you know, 7 to 14 kilometers per second objects. Things that are below 10 centimeters per second are still a huge hazard, and we just can't see them, right? So there's a significant risk to human spaceflight. And then if we look at that polar orbit, where a lot of things are concentrated in that 800 to 1,000 kilometer range, there's a significant number of basically sun-synchronous orbits there. So a lot of NOAA imaging satellites that are there. And so that is prime real estate in an orbital sense. So if we just kind of compare those two orbits, right? So here we're looking at the debris flux, and here we're looking at the diameter, right? So this is a 2 millimeter particle. This is a 5 millimeter particle, and we're looking at basically, there's 1/10 the debris at 2 centimeters as there is at 5 millimeters, right? So it kind of rolls off. And the debris flux is about 10 times higher in that larger polar orbit, right? So there is more debris in that polar orbit. So we start to think about, what is this mission? And so about the time I was going up for tenure, Space Force started to get serious about orbital debris cleanup and saying, what could we do to actively remove things from orbit? And so we are working on a small sat phase 2 STTR that works on fielding an orbital debris deployable collector at really one of those two candidate orbits. And we're looking at how CubeSat, basically a demonstration mission to reduce some of the uncertainty in that larger scale mission, right? So we've got kind of these two orbits, the orbital, the 51.6 kilometer inclination angle one, and the near polar sort of larger orbit. So our overall workflow has encompassed several different things. The first thing is figure out, where do we actually need cleanup? Where are the target orbits? And then we actually have to design some kind of collector mechanism that will allow us to collect some of that debris, do some experimental validation within hypersonic ranges, and because we can't see this debris that we're going after from the Earth, we have to do in-orbit perception and really design the sort of overall launch mission. So the first part is really just in-orbit perception and control. How do we actually, interact with this? Ground-based radar, it turns out, is not really a great way to do this. We've had some experiments with that. I won't talk about that. I'll talk about optical, delta V from debris or momentum transfer, and then we're going to start to talk about some of the control approaches that we've been deploying, right? So first off, in terms of momentum transfer, we need to think about how much momentum is actually transferred with a small sort of centimeter scale debris item that impacts a satellite. And the biggest thing that we find out is that we're likely to basically be looking at head-on collisions at 14, 15 kilometers per second. That's basically the most probable scenario. And in the 800 kilometer polar orbit, it is about 10 times higher in terms of the number of collisions per year per unit area, right, that you're sweeping through. So it scales by the size of your satellite or your collector. And so the first idea is, can we somehow detect that we've been hit by the change in orbit? And so that hit should rob us of delta V and should change our orbit. And so we can go ahead and write the two-particle system and write those mechanics. And what we find is that even just from the vis-viva equation, you can see that the size of the orbit should change, right? So we're going to lose delta V here. We'll still have the same perigee, but we'll lose semi-major axis here. And we'll end up with a significantly smaller orbit, right? In this case, for the full scale, we're looking at about 280 meters. For the CubeSat, we're looking at about 28 kilometers, right? So this is a significant change in the orbit that should be measurable, right? And we've now gone through the detailed Gauss perturbation models and shown that basically this is higher than some of the other perturbations that we would see. So if we can set up this scenario where we see those. Okay, now that we've measured those systems, we need to maneuver and we need to somehow interact with them. And so as a way of getting some practice with orbital maneuvering, we entered the AIAA Kerbal Space Program Differential Games Challenge. And so this is a space environment built in Kerbal Space Program to allow you to kind of maneuver. There's about 6 different scenarios, but I'll just show you basically the orbital, the pursuer evader model with a non-cooperative evader, right? And so that's the case that we're seeing here. We got about 8 meters close, and we basically were comparing PID controlled traditional, what we teach undergrads, versus reinforcement learning with a double deep Q neural network. And actually the PID was outperforming the reinforcement learning well enough that I think we actually placed 3rd out of 25 teams in January. And really this just sort of shows that reinforcement learning works really, really well when you don't understand your physics, right? And your models. In this case, the models are sort of well characterized, and so PID control works just about as well. Okay, so we need some mechanism, some physical mechanism that will accept the debris at these sort of relatively high velocities. We went through a number of different configurations to really figure out what that would look like for a hypersonic impactor, and some of that had to do with just getting a feel for basically what hypersonic impacts look like. So we were able to use some tools from MMOD, micrometeoroid and orbital debris shielding, right? We were able to use some shielding systems, but the problem is that shielding work is very focused on binary. Did it penetrate the shield or did it not, right? So all of the analysis is either pass-fail, right? It's not a continuum that we would want. So here's some examples of kind of what you might find in the literature in terms of Whipple shields with a thermal blanket integrated, multi-shock systems and mesh double bumpers. So there's a variety of different things. There is a pass-fail criteria for these in terms of the ballistic trajectory, and so that's maybe the first thing, is that you end up with this sort of pass-fail criteria where if you're above this ballistic limit, now this is velocity and this is diameter of the debris, and sort of assumed aluminum density usually. And if you're above this limit, then you're penetrating, and if you're below this line, then you're not for the different cases. And so we designed for basically our small sat configuration and started to look at what we would look at. That is a handbook-based method. We had to extend it to get beyond the pass-fail binary conditions. And so we then needed to go into some numerical studies to look at, what is the detailed sort of debris cloud? What are the other physics that are going on in terms of the light, the heat, the smoke that's emitted at a hypersonic impact? And so this is about, simulated about 7 kilometers per second, and this is a multi-shock hybrid system that incorporates some aluminum and Nextel, but this is pretty close to what we want to be using. And so in this case, it's fragmenting the debris into smaller, less hazardous particles. And there's a collector medium that goes in between there to really be able to capture that. We're now in the process of doing some of the hypersonic ground experiments to validate this kind of system and understand basically how it performs in that context. And so that'll be with a light gas gun in the next couple of months. And so, this is basically what I've shown you is more or less for the objective aircraft, except that I showed you that the delta V caused by orbital debris ought to be measurable on a CubeSat, significantly measurable on a CubeSat. And so, here I want to kind of focus more on the CubeSat part of it. And so really we want to get two things out of this. One is we want to do in-orbit perception and really get better measures of what the orbital debris looks like. Most of the work that we're working with is statistical models that are inferred, and in fact, a lot of people don't have a lot of confidence in especially the smaller debris. We've never measured the debris below 10 centimeters because it doesn't show up on ground-based radar, so that's all inferred. And so the ability to go up and actually measure some things in that area would be helpful. And then the second thing is if we can actually interact with some debris, we'll have a better idea of how this hypersonic kind of system works. So going to the CubeSat mission, we had to change our mindset a little bit here in that, this relatively recent change to go from 25 years to 5 years means that probably a lot of our sort of legacy CubeSat missions, weren't necessarily compliant with this, right? So, if we're above 600 kilometers, we're probably, not compliant with a lot of missions aren't compliant with a 25-year lifetime unless they have some kind of deorbit mechanism, and now we're looking at basically 5-year mission times. So that was probably the first thing, is that, if we look at, and so these are basically typical CubeSat densities here, and we've plotted altitude versus deorbit time with some sort of basically assumed atmospheric density variation, right? And so we're looking at, lifetime with that. So from that, we derive some CubeSat mission requirements that basically say, here's our minimum, maximum, and ideal endurance, max size, mass. We're looking at a 3U to 6U satellite to be able to incorporate the sensor and also the orbital debris collector. And then the other piece that maybe is a little bit less traditional is we want to design for a specific number of debris collisions, right? And we have to segment basically based on size in order to identify the exact number of debris collisions there. But we want a measurable number, and we don't want a huge number. And so, we developed over the last few months some power and mass budgets for this. We're under budget with those, which is good because we have lots of room in terms of things growing. And this just kind of gives you an idea of basically the layout and the performance. Earlier we had some reaction wheels in here, and we're now using magnet torquers because we're operating at a lower altitude, and so that allows us to get some meaningful pointing accuracy. And then we have our optical sensor integrated with this basically deployable debris system. And so we can now understand this sort of design space where we're looking for a particular number of collisions and looking at basically the deorbit time versus altitude. And so there's a trade-off there where the more collisions you get, the faster you'll deorbit. And that, right now we're working at about basically 59 collisions per year at 480 kilometers, which is kind of about the number that we want to be. Now, most of those collisions are fairly small debris, relatively small debris. And so, they're not the centimeter scale debris that we're talking about, but it does give us useful information. So I wanted to kind of summarize where we are here in terms of the active debris removal satellite design that we're doing, which is the objective mission, and that's what Space Force is most interested in. And then kind of the smaller scale CubeSat mission, which really just basically perceives and measures the quantity of orbital debris on the desired trajectory. Allows us to start looking at some of those hypersonic impacts in orbit after we've done the ground-based experiments. So thanks again for your interest and attention here, and I'll be happy to stick around and discuss with anyone. I see a question in the back. Okay, so that's total. So a lot of those, so he's asking about the number of collisions, right? So that's total. So a lot of those are actually below a millimeter, right? So when we segment, above and larger than that, it actually gets a little bit harder to get some of those bigger numbers up, right? So most of those are small, right? And previous missions, NASA Stardust mission, some of those other missions have flown, orbital debris collectors. And what you find is you get a lot of these micrometeoroids, tiny paint flecks that are sort of 360 microns, these kinds of very, very small debris, almost dust, right? And that's kind of the dominant thing there. And if you look at any of the debris flux terms, you'll find, you'll see that basically as we go to the bottom end, those basically ramp way up, right? So this is a log-log plot. And if you look at as we go towards the smaller and smaller debris, this is ramping way up. So it is dominated by small debris, which is why we often basically segment out the smaller debris to be able to design theirs. So we have basically by size. Right. So that's a good question. Is there a lower limit to what you want to accept? A lot of thermal blankets can handle debris up to almost 0.4 millimeters, right? So the vulnerable region is really somewhere between 0.4 millimeters to 10 centimeters, right? That's the region that you actually want to protect against because you're blind to it, but it can still create a hazard. So the thermal blankets on most spacecraft can handle up to about 0.4 millimeters. And so we don't worry about really that small stuff. And so, yeah, there is a sweet spot. That's why we're focused on the centimeter scale debris. And it turns out that it has a significant amount of momentum and kinetic energy. So, great questions. Thank you. Yes.
I was curious about the satellite design itself. You have an impacting area and other parts of the satellite that you wouldn't want to be impacted.
Mm-hmm.
So you need active pointing, but also a larger, harmful piece of debris that would impact your satellite may not go through the center of mass, so it impart a significant torque.
Yes.
So how will you handle that so that you can set up the satellite for another impact if it gets impacted by a particularly large object?
Yes. Yes. And so what I showed you was basically the point mass kind of solutions. When we put the rotational mechanics in there, we've done that simulation, and we do get significant rotational tumble after that, and that limits the capture envelope because if we're relying on So there's two answers. One is the small sat, and the other is the CubeSat, because these are two different spaces, right? So for example, the CubeSat, because that's what we're here to talk about, is driven by magnetorquers, which have a lower actuation authority. So you're going to have to react much more slower. If we do hit, if we do manage to hit a smaller, a larger piece of debris that is off axis, we'll have a significant amount of recovery time before we can actually accept any other debris. That is from the CubeSat perspective, that's a cross-check on the amount of debris that we saw, because now we see an orbital change, and we also have a second way of estimating the size and the momentum transferred to that. So we see that as helpful at the CubeSat level, partly because it's difficult to get those collision numbers up for significant size debris. I mean, a lot of the debris is dominated by these small particles. And that's been a challenge, because as you go to higher altitude, when we get to that 800,000 kilometers, we'll have 10 times more debris, but we're also starting to run into mission times to say, can we actually deorbit fast enough, and does it make sense to launch to those higher altitudes? Thanks.
So you said you can't find the debris that you're looking for from the ground. How are you planning on finding that in orbit and then physically going to that debris?
Right, so there's, we've looked at optical perception and radar perception. Those are kind of the two ways to do it. Radar turns out to be somewhat of a challenge because of the power and the physics don't work out well, right? I mean, your range is governed by r cubed, effectively, or sorry, r to the fourth, because you've got r squared spreading going out and r squared spreading coming back. Inverse squared, bad, right? So you end up needing more power than we'd like on these small satellites. So we're mostly using optical. We're mostly relying on optical, which does mean that we have to model visual magnitude. We have to look at signal-noise ratios. I've got some slides on that I'll happily show you. And the other thing is that in many cases, this debris is subpixel. So we're looking at subpixel debris, and in that case, we're using some algorithms that we got from the insects, because insects have really bad eyes. They have fixed focus detectors. Everything's blurry out of focus, but they're trying to chase other predatory insects that are smaller than the pixel. So we're using some of those algorithms to recover some of that ability. Okay. It looks like 1 minute, so I'll say thank you. Maybe, yeah.
How are you going to manage your delta V if you're going to go out and perform these rendezvous operations with multiple pieces of debris and hit that target 59?
Right. Right. Yeah. So at the CubeSat level, we are losing delta V, right, and that becomes a life limit on our deorbit. So that is a form of deorbit. At this at the larger small sat level, it is a fuel consumption if we're actually doing these head-on ones. We spent some time trying to figure out if we could kind of cleverly recover the energy from them, to say if I encounter a piece of debris and I rob it of its momentum, it deorbits faster, and I can use that as a propulsion mechanism, right? And so far that that only works in some scenarios. So we basically have to plan that we will be using some fuel in order to recover these, because not all of the debris will be well positioned for that. So, all right, I see this is the end of time. I'll be here, so thank you. Thank you.
All right, everyone, please join us in welcoming our next speaker, Kalia Crowder from Cambrian Works.
Good afternoon, and thanks for waiting around till 4:20 for this talk. I appreciate it. My name is Kalia Crowder, and I'm here representing Cambrian Works. So we are a small startup focused on in-space communications, networking, and touch, which is what this presentation is about. But first, I just want to echo something that Jordy said in the keynote today, which is that even though we start from CubeSats and sometimes do other things, the CubeSats really have been this amazing building block. I remember walking around this campus 20 years ago and seeing a flyer saying, "Would you like to see your name in space?" Which, by the way, is always a really good way to get students involved, is to appeal to their ego. And after that, I got to work on the first generation of CubeSats here at Cal Poly, which led to my first job and 20 years of really cool tech in space, some of which I'm going to be talking about today. Or not, if my clicker's not working. There we go. Okay. So electroadhesive technology is a technology that has been researched for over 100 years, and it's had applications ranging from paper handling to wall climbing robots to tactile or haptic screens. But what I want to talk about today is why it is such a useful technology for attachment in space. In particular, it attaches to virtually any surface that don't have to be prepared. It's very low swap, and it's easily turned on and off and leaves no residue. We've demonstrated it successfully with all of these components, these types of materials, which include conductors and insulators. So when people first hear about electroadhesion, one of the first things is it seems too good to be true. How can you attach to both conductive and insulating substances? And the fact is that it happens through different mechanical principles, but both are okay. So for conducting substrates, because of the motility of the electrons and protons, they are attracted to the opposing electrodes in the electroadhesive pad, and therefore you get a very tight attachment. For dielectric substrates, the molecules are polarized, and so you can still get that attachment by causing the polarized ends to get closer to the attracted electrodes, but it's not quite the same mechanism, but they still attract. So one of the things that I think is most interesting is it was first discovered or demonstrated in 1920 by Danish scientists who were researching how to make a better telegraph, which I always think is interesting because all of the things we're researching now, who knows what they'll come up with as much more useful applications in the future. So the anatomy of the electroadhesive pad is pretty simple. There's a high voltage drive, a pad with interdigitated electrodes that generates the electric field, and then what we call the substrate, which is the actual thing that it's attaching to. So for the high voltage supply, you really want to get about 1500 volts or higher. And one of the things we've developed is a very low power voltage converter that can take 5 volts, which is compatible with most CubeSat power systems, and is able to take it up to the high voltage required for this system to work. One of the interesting things is the electroadhesive force depends on about 20 different parameters associated with the pad itself. And so part of this technology, the devil is in the details in terms of getting the parameters just right for what you're trying to attach to and the forces you're trying to generate. So I've got here a chart of electroadhesion features, which I'm not going to read to you, so you're welcome. But what I would like to leave you with is the things that make it really suitable for CubeSat missions are that it attaches to virtually any surface, including those that aren't flat or those that are non-planar. It's very low swap, and it's easily reusable because you can turn it on and off. It leaves no residue. So for those reasons, it compares favorably to a lot of other in-space attachment technologies, such as we have listed here. Now, I'm not going to argue that it's perfect for all missions, but what is key about it is that it has a very unique set of features that make it complementary to a lot of these other attachment technologies. And so it's suitable for a wide variety of missions that aren't covered by some of these other attachment techs. So one of the things that we've done here at Cambrian Works is we've conducted significant performance testing on what we're commercializing as the electrical thin attachment pad. We call it ETAP. So I may use that term in this presentation interchangeably with electroadhesion, but the principles are the same, whether it's the ETAP pad or electroadhesion in general. So far, we've been able to perform normal force testing in vacuum, force testing against multiple substrate materials, and then 1D and 2D off-angle dynamic testing. So I've got a picture here of our normal force testing setup. Upcoming, we're working on shear force testing and then the 2D dynamic air bearing testing, which will provide a lot more, I can't pronounce it, verisimilitude for on-orbit operations. But the key is that it's been designed from the ground up for on-orbit use, and then we're validating it and testing it to show how well it works there. So here's a quick summary of some of the static testing results. These results were taken at ambient pressure with 16 centimeter square pads. And what you can see is that we're able to attach to both composites or insulators and conductive materials. We've been able to determine that the attractive force does scale linearly with the attached area. So we can usually get about 15 millinewtons per centimeter squared at ambient pressure. And we do see that we get slightly higher attachment with insulators than conductors, and then dielectrics can sometimes be in the middle. We also found that thin coatings do not determine or do not really affect the attractive force, so it works even with different types of coatings on materials. But we have also found that the mechanical design and the mounting tends to be a really critical impact on how well something attaches in the real world. The other thing that has been very useful to determine with vacuum force testing is that the normal force attachment is significantly higher in vacuum than in ambient, which again makes it ideal for space use. We typically get numbers between 2 and 6 times higher when we're testing in vacuum. Beyond the static force testing, the linear velocity capture results show that we are able to get a sense of what the dynamics would be when we would approach objects with a pad like this in space. So we do see that conductive substrates have a slightly faster electrical response time compared to dielectrics, and so we're able to capture them with a higher velocity than we are with some of the dielectric materials. However, if you coat dielectric materials with a resistive layer like the indium tin oxide that's often used on solar cells, then you can get them to behave more like conductive materials, and that allows capture at higher velocities. In addition, because of the fact that you can create these ETAP pads with conformable surfaces, you can then capture things that come in at off-normal angles. And one of the things that we've been able to demonstrate with the linear track testing is captures at up to 5 degrees off normal. So I will say there again, the off angle and the maximum capture velocity are heavily dependent on how the ETAP is packaged and mounted. So we're very excited to work with Astroscale and AFRL to collaborate and get some more realistic testing done in a dynamic setup. So I've got pictures here from the European Space Agency setup, which is similar in that these are essentially glorified Roombas that get to bump around, and we're able to then test the force that ETAP can exert on a spinning object, and also that the 2D dynamic that happens when two materials are approaching and whether we get the elastic or the non-elastic collision. So simulations and linear track testing are useful, but there's nothing like this real dynamic testing to understand how it will behave on orbit. So beyond the performance testing, we've also made significant progress towards space qualification. We have designed it from the ground up for space suitability, but we've also gone through the processes of testing it in vacuum, both the driver circuit and the pads. And then we're working on thermal testing, vibe, EMI, and EMC testing so that we can really reduce the risk. That being said, all of our materials and design choices are based on components and principles with very long on-orbit heritage, so we don't see any of these as significant risk factors. So that's more about the technology, but what I really want to talk today about is some of the applications that we see for this technology, specifically in the CubeSat form factor. The first one is orbital debris. One of the things that definitely has occurred to me is the similarity between orbital debris problems and kid debris problems. You put two large toys in a room with a kid, 20 minutes later, you've got debris all over the place, just like the Kessler syndrome. So while ETAP can't clean up the Legos from your carpet, it is very well suited for active debris remediation, specifically because it can attach without the need for prepared surfaces, attachment points, and is also highly reusable. So a concept that we put together at Cambrian, which we call Space Payload for Inertial Dispin Efficient Effects, no guesses as to where we came up with that acronym, is shown here. So this is essentially showing an ETAP pads on a deployable 6U CubeSat that can be used to capture orbital debris. The idea here is that it can be deployed from a larger mothership and it can attach to debris, with options to deorbit or otherwise tag. So there really are a wide plethora of ways to do this. You can apply drag just by having the electroadhesion drag along this side of the rotating surface. You can actively despin with active measures there. You can attach a docking plate for a larger vehicle to dock to. You can attach a tag to mark it, or even an IMU that could provide information on rotational rate for servicers that might be capable of handling those. So for this presentation, I asked ChatGPT to generate an OV1 concept of operations and came up with this, which I think is good news because it means my job is still safe for a while, not yet being taken over by AI. But the key point here is that Spidey, which will not look like this, is a deployable and recoverable from a larger servicing mission, and it provides significant reuse potential. So beyond active debris remediation, there's also electroadhesion-enabled workspaces and deployment options in space. So what we've got here is a picture of what we call our ETAP wall, and that is something that can be used as workspace augmentation, camera mounts, anchor points, tool and component management, or the controlled deployment or detachment of subsystems, so that we don't end up with this situation here. Another mission that is easily possible in the CubeSat form factor are those associated with in-space assembly. So there we've got telerobotics and servicing assistance. Here you can see an ETAP augmented robotic arm. So the idea here is that it allows for an attractive force to the grippers, which makes it easier to attach to and hold on to items. So it can augment existing mechanical graspers. In an in-space assembly line, it has an easily controllable amount of stickiness, and it can also be used for in-orbit assembly debris capture. So people have talked about 3D printing up there, and any other types of debris that might be created with milling. Those could be easily captured with a pad like this. You can also use it as a double-sided Oreo filling between items, right? You can have attachment sticky points on both sides. So it easily enables a modular assembly approach. And what's key about this technology is it's almost like Goldilocks. It's not too strong, and it's not too weak, and it's tunable for the specific mission parameters that you need. Another mission application is the docking and refueling missions. So ETAP is ideally suited for unprepared and non-responsive docking, right? So some things that go up there have docking plates like you can see here from Astroscale on their side, but many of them don't. And so this allows for docking to those types of situations. ETAP is low profile and has an extremely versatile topography. You can have arbitrarily shaped pass-throughs that allow wiring, cameras, or anything like that. And then it's also compatible with other types of mechanisms for redundancy. So you can attach an ETAP pad, for example, so that it will, and I keep pressing the wrong button, so that it will attach here, but it can be augmented with graspers or magnetics or anything else to provide extra assurance. So in particular, it can be used for standalone docking or augmenting existing docking solutions. Finally, I want to talk briefly about the possibility of using it for modular payloads. So ETAP can be used to attach a fully functional modular payload to existing satellites. I've got an example here. I've got docking in quotes. Don't look at the arms there. Totally docking. But ETAP is compatible with power, data, and heat transfer, and the CubeSat payload deliverable can be delivered via mothership. So for example, Space Logistics has a mission robotic vehicle that would be suitable. So the capabilities that could be added are almost innumerable to think of, but you could think of ideas for space domain awareness, computational payloads, imaging payloads, comms or other services. And then someday, I hope for satellites that are designed for upgradability and the idea of having intra-satellite wireless comms or modular power supplies that would allow for a deeper integration. So the electroadhesion-enabled mission design principles. What I've tried to do here is the middle panel and talk to you about how these are really useful technologies, even if inside is really just cool space stuff. But that being said, really useful in space technologies. So I'm going to leave you with a couple of design principles. Specifically when coming up with missions for electroadhesion, the most important thing is understanding your mission parameters. What surfaces are you attaching to? What are your likely required forces? What are your approach angles, speeds, and relative masses? Then you can tune for the desired attractive force. That will tell you how much area of attachment you need, what voltage you want to run it at. And then it's best to design for a minimum required force and just always test to that and make sure you exceed it. And that will ensure best performance on mission. Finally, you can design the mission ConOps to play to the strengths of electroadhesion. Because shear forces are so much stronger, if you can make sure that any tension is in the shear force instead of normal, that gives you enhanced attraction. And finally, you can use flexibility and pad conformance to minimize elastic collisions. So in general, I want to leave you with the idea that electroadhesion's unique set of qualities, low swap, and ease of use make it perfect for your next CubeSat mission. And I want to also just say that Cambrian Works is actively seeking partners to help develop ETAP missions, so definitely come talk to us. We are also one of the companies that Jordy mentioned again at the keynote, founded by ex-CubeSat Cal Poly folks. We've got 3 of us at the company, and we're excited to develop the next set of ETAP-enabled CubeSats. Thank you. And it looks like I have time for possibly a few questions, if there are any. Yep. No, so the idea is more that if you know, for example, you're always going to be attaching to, I'll just come up with an example, MLI, multi-layer installation, and that doesn't attract as well. There you'd want to figure out your minimum parameters that you could reach and make sure you had enough coverage to go over that. But all that means is if you ever tried to attach it to a conductive surface, it would stick really, really well. Yeah, unfortunately, it decreases extremely quickly with distance, so it really has to be quite up close and personal. Anything else? Okay, well, thank you very much.
I would like you to join me in introducing Jake von Spanje and Michael Huntington from the United States Naval Academy.
Okay, good afternoon, everybody. My name is Midshipman Michael Huntington.
Midshipman Jake Van Spanje.
And we will be talking about the United States Naval Academy's Robotic Repair Satellite, also known as Arsat.
So a quick overview here. We're going to go through the mission objective, the design, and some of the operations, and a little summary of what took place during our operations using the Arsat when it was on the International Space Station.
So our mission objective. So the goal of Arsat is to demonstrate robotic arm functionality on orbit in order to advance on-orbit assembly, servicing, and manufacturing capabilities. So the on-orbit servicing challenge that we are faced with right now, to sustain an increasingly complex space missions and spacecraft in space, we see that we're going to require on-orbit assembly and repair to extend their mission life. And the current solutions to these problems are either too large, too bulky, or too limited in scope, like single mission focused, to be used more broadly. So the Arsat solution. The Arsat solution is to develop an inexpensive, a reliable, and a versatile system that's capable of on-orbit assembly and repair for a wide variety of missions. We're going to do this through the use of streamlined and replicable production of robotic arms using commercial off-the-shelf components and in a CubeSat form factor.
So our current mission on the ISS, what just concluded a few days ago, basically this whole thing was a proof of concept. What happened was we installed the robotic satellite on the International Space Station's microgravity service glove box, also known as the MSG, and basically it was a test bed to validate the 6th degree of freedom controls, the arm coordination and imaging and identification capabilities needed to develop on-orbit assemblies. And there's a cool picture of the Arsat installed in the MSG.
So I'm going to quickly go over the design of Arsat. So kind of go over the system design. Arsat is two 3U CubeSats placed side by side with each other on an aluminum plate that is then hard mounted with hardware into the MSG. Each 3U CubeSat has one robotic arm. We chose this because, again, as this is a proof of concept mission, we don't want to, we're trying to prevent tangling of wires and stuff as robotic arms are moving around. And of the two 3U CubeSats, only one has a 3D camera that we use for target acquisition and identification. The little picture on the left, on the right, shows how the two 3U CubeSats placed side by side with one robotic arm per CubeSat. Then we have two boxes. One box holds our power control unit, and the other one holds our master Raspberry Pi, which commands the entire thing, which I'll go over a little bit in a couple slides. So our arm design. We have the two arms. Each arm has 7 motors, 6 motors for each degree of freedom, and then 1 motor for the end claw end factor. There's a camera placed on the end of each of these arms, and we have some pictures of that later in the slides. And this is for kind of a first-person POV of what this claw is going to grab and for target identification. And then each motor on each arms can be operated individually for each independent movement of each degree of freedom. This is a quick little electrical diagram of Arsat. To note are the 4 bolded squares. These represent the 4 processors that are on Arsat. The top one is the master Raspberry Pi. This is what controls the entire Arsat. And when you go to control Arsat, you first SSH into the master Raspberry Pi. That controls all the communications and the power management through all of Arsat. Other 3 are 3 secondary processors. We have 2 Raspberry Pis for each arm, ARM Pi 1, ARM Pi 2. Then we have an Odroid controller, which controls the 3D camera. On the bottom is shows 3 more boards that control the motor. You have a motor control board, which controls the power going to the motors. Then you have an Arduino Mini, which controls the communication and data going in and out of the motor. Then you have the motor itself.
Awesome. So now we're going to get into some of the operations of what took place when it was installed on the MSG and how that all unfolded. So our wonderful team of midshipmen over at the Academy were split up into different roles and responsibilities. So basically, some of those roles, we started off with the voice loop operator. This person was basically in charge of keeping constant communication between NASA and the Academy. That was just through a voice loop. And then we had the main operation console operator. This person was in charge of the controls of the connection to Arsat, and that was everything from network connections to the payload, and they were performing the command and control functions. And then we had the operation logger. The logger was basically keeping track of every executed command that took place when we were sending those commands up to the CubeSat itself. And then the planners, those were 2 people that were running the MATLAB script for each arm to generate the motor solutions. And then there's a picture of 2 amazing midshipmen doing those duties. So we're going to roll into some of the operations. This took place from 10 Jan to 2 February, and this main purpose was the installation into the glove box and the testing that took place. So day 1, our main priority here was to get it all installed, make sure everything fit, and to see if all the configurations that we planned on executing were carried out the way we wanted to happen. The results for day 1, Arm 1, 5 of the 7 motors functioned as expected, and Arm 2 completely as planned. Everything worked as we wanted it to, and then the 3D camera test was successful. Our main challenge here on Arm 1, motors 3 were non-responsive, and then there's Laurel O'Hara, one of the astronauts on the space station there, setting everything up, and everything was good.
So day 2 was our first full day of operations on the ISS. The goal of the day was this arm deployment test. Let's get those arms out there and kind of just moving around and see what happens. So the results that on day 2, we were able to take a picture, a little selfie. It's on the bottom right picture. And that's from one of those end effector cameras I talked about earlier on the end of the claws that we pointed to kind of take a picture. And you can kind of see the 3D camera on the bottom of that picture. Arm 2 was successfully carried out. We were able to SSH into Arm 2, and then the 3D camera was successfully operated for target identification.
Awesome. So day 3 of operations, we had just maneuvering in the arms, trying to get used to the actual processes and seeing if everything still worked. The results here, we were able to take some photos and send them back to the Academy. This, if you look at the top center here, there's a little cube with a QR. Basically, we tried to position those arms so they could take a photo of that cube. That was one of our big goals. And then send those pictures back to the Academy. And then here, the Master Pi and ARM Pi 1 couldn't be pinged, so basically we requested a power cycle to NASA. So up on the MSG, they just cycled it, and everything worked after that. And then there's the photo of our little layout.
So day 4 was the last day of operations for part 1 of Arsat. And the goal of the day was to do some more arm maneuvering, but the biggest thing was getting those arms stowed for the Arsat to be taken out of the MSG. We were able to effectively move Arm 2 into its stowed position, but we did have some problems. At the beginning of day 4, we tried a last-ditch effort to try to get one of those cameras on the end of the claws to take a picture of the cube you can see up there. But the challenge we had is that the astronauts installed the cube that we use for identification just too close to the window pane of the MSG, so Arm 2 was not able to grab it. And then when we were stowing Arm 2, we had trouble actually getting in its fully stowed position as the structure of Arsat was in the way. This is a picture kind of shows more about that. The arrow on the bottom right shows how one of the end of the arms kind of got caught on the structure of Arsat. The arrow in the middle showed how there's an aluminum plate within one of the 3U CubeSats, and that was pressing up against our ribbon cable and our motor boards. And then the circle kind of shows how the wiring harness was in a position that was not ideal for stowage.
So now we get into operations part 2. This is the reinstallation of the Arsat. This took place from 19 March to 15 April, and our main goal here was target acquisition. We'll go into that a little bit later. Our main goal was just to grab a ring and gain positive control. So day 5, we got everything back in. Our main goal was just to reinstall Arsat into its spot in the MSG and make sure everything still worked. We ran into a challenge here, motor 1 and Arm 2. Motor 1 on Arm 1 and Arm 2 motor 3 didn't reach their max angles, which led to some problems when we were trying to reach the objects that we were trying to grab. And then our second challenge, Arm 2 motor 3 had limited mobility, as previously mentioned. When you're trying to grab those objects, it's good to have that full mobility. So. And then here, when it was reinstalled, this was the initial positioning of everything. So if you look in the top center of that, there's that blue ring there. Our main target here was to use those end effector claws and go up and grab that ring. And you'll see later on why that's so difficult.
So day 6 was our first full day of operations on operations part 2. Our goal was to get target notification of that ring with the claws and then to try to go grab the ring. So in effect, we kind of caught the ring. We were able to get the arm 1 into position where it was resting onto the ring, but we didn't have full control of the ring. Some network issues during operation day 6 caused some camera issues where we lost signal, but then we reacquired it. But the problem that we had on day 6 and that would persist for the rest of the days of operation was that whenever we try to grab the ring, we'd bump it, it would float across the bar it was installed on and end up in a spot that we couldn't really grab it with our arms due to our range of motion. This kind of shows it how on day 6, arm 1 is trying to grab the ring, but it's in this top right corner, which is the worst position for the ring to be for us to try to grab it. This is a picture from the end effector camera on the claw of arm 1, and you can see how the ring is in the far right corner and like positioned horizontally, where we just cannot really grab the ring with our arm.
Okay, so day 7, we had the goal of a handshake and target inspection, so we're trying to position ourselves to grab that ring again, but our main goal was to set up a handshake, and what that is basically the 2 arms come together and those claws come together and make that handshake. We were able to do this within 20 minutes. The only problem was we weren't planning on doing it in 20 minutes. It was a little rushed. The installation of the camera caused a little bit of delay and everything pushed to the right. So it was a little rushed, but other than that, the camera was bumped, but we got everything done that we needed to get done during this session. And the reduced range of motion motors due to the cabling caused a little difficulty, but again, there's the picture of the successful handshake.
So day 8, our only goal was to grab the ring. We did not grab the ring. So another problem we had, especially on day 8 and a couple other days, that the crew would bump the camera when they floated along the ISS, and that caused the camera to kind of be out of whack. But we still had positive visuals on what we're on the ring. But again, we get this problem of when we try to grab the ring, we'd bump it, and it would just float across, and we didn't have time to grab it. And that was due to when you send a command from the United States Naval Academy ground station, but when you click enter on the command prompt, and by the time it is executed by Arsat, it's about 17 seconds. So it severely reduced our reaction time in regards to grabbing a ring that's like bumped and floating away.
So day 9, this was our final day of operations. Ring acquisition was the main goal. We got it. So the challenge here, we had the ring up in the corner. That property sticker that you look at up in the top left of the photo of the MSG obstructed the ring almost completely. So we were kind of shooting blind where that the arm came up. So we eventually got it, but again, the external wiring on the arm itself caused a little issue in terms of trying to grab that ring. Whenever we got close, the claw would be positioned like this, and then off to the side, some of the wiring would come out, and if that even touched the ring the slightest bit, zero gravity, it would spin around, it would send it down the rod. It was quite the challenge. Luckily, it was on a rod like this, so if the ring spun, it could only spin so much, and then if we had to, we would just wait, and then the ring would spin back to a position where we could grab the ring.
So over the 9 operating days we had on the ISS, Arsat was able to successfully deploy our arms and kind of move them around in 0G. We were able to conduct a 2-arm handshake and then take pictures with the end effector cameras for positive target acquisition of the QR code on the little cube from part 1, and we successfully grabbed the ring. And that was the main goal of Arsat, and we're super excited that we're able to grab that ring. And for that, the mission was a complete success.
So this is a picture of Laurel O'Hara on the left and Jasmine Milk-Belly on the right. That's them with Arsat, and yeah, go Arsat. So,
thank you guys so much for your time.
Questions?
If you guys have any questions.
You guys are great. Yeah.
They were stepper motors, so you can't, Like the Canada arm, they're not powerful enough to move anything on Earth on 1G. So you can only really test them with the full armed assembled in 0G. So that would have to, yes, ideally. So we were kind of forced to have 17 seconds due to how we were hardwired into the ISS communication, and we're dependent on ISS communication down to NASA and then from NASA to USNA, and that was part of the latency issue. If we can optimize the signal transferring within Arsat, that's how we would minimize that the latency. So we actually were able to test it, kind of. So when we were building Arsat, we were able to take some of the motors and we put tape, Kapton tape, around the spindle of the motor, and with that, and there's like a little flag on it, and you could still command the motor. It would spin. It just can't move anything heavy. So we could still simulate how much range of motion in degrees the motor had by just tracking the little tape thing that can move around. So we were able to test the maximum, minimum operating angles of each motor, but just without the full arm assembled. And with that, thank you guys so much for your time.
Thank you.
All right, everyone, please join me in welcoming our final guest of the day, Richard Freeman, representing the United States Coast Guard Academy.
Okay. Oh, thank you. All right, good afternoon, everyone. I'd like to start by thanking the organizers for inviting us and allowing us to speak today. This is the first presentation that we're doing. We have another presentation tomorrow afternoon that's going to be done by Captain Royce James. And I want to talk to you today about this whole idea of how we can localize a radio signal using the Doppler information from that particular signal as it's received by a satellite. Okay, so I want to start with something really basic. How do you know where you are? Well, my department head just always says, I just ask you, and then what do? I pull out my phone. And so in the lower 48, that's a very easy way of figuring out where you are. So you have your cell phone is connected to towers, the towers are getting GPS information, so they know where they are. And based on where they are, they can triangulate and find out where you are. So that's where we are right now. One of those 2 pinpoints there. Okay. So based on where we are here in California, if we were to get in trouble out on the water, if we were out in the bay and decided to go out on a boat, someone accidentally got, hit with a spear gun, a shark is eating the boat is sinking, something catches fire, we're just in a lot of trouble, you would pick up the radio, get on Marine Channel 16, and call Mayday. And the people you would be talking to would be United States Coast Guard using Rescue 21. And what Rescue 21 is really about is this idea of command, control, and search and rescue. It allows the Coast Guard to assess where you are and to get the appropriate assets out there to help you. Now, if you're sitting in a bar somewhere and you've got a Marine radio and you're like, hee, watch this, Mayday, 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 yeah, they will know that you are not out on the water, that you're in a bar somewhere calling Mayday, and send the appropriate assets to, take care of your needs. So that's the basis of Rescue 21. It's the idea that the Coast Guard has the ability in the lower 48, the Virgin Islands, Hawaii, Guam, and including the inland waterways to help locate people and rescue them. Okay. So yeah, this is where we are, District 11, Coast Guard District 11, in the LA Long Beach sector. You can see there's a lot of color on that slide. Each of those colors represents a Rescue 21 tower and the reach of that tower. And so you can see there's a lot of overlap there. If we lose one of those towers, Rescue 21 is still going to function here. Okay. So now let's talk about why we want to do Doppler location. And the way I want to get you there is to go north to the Arctic. Okay. So what do we know about the Arctic? Well, number one, yeah, you're not going to have cell service. Number two, if you are lucky enough to have a satellite phone, you may be able to use that satellite phone to call for help if you get into trouble. Line of sight communications is going to be very limited. And when we look back here, one of the important things is in the lower 48, you have 4 global navigation satellite systems that can help locate you. So you're going to see 4 of them. I know on the previous slide I mentioned this idea of having 6, and that's true. There are 2 that are regional. If you're in Japan or you're in India, you're going to have an additional regional system there to protect you. But if you're up in the Arctic, all those GNSS satellites are going to be low on the horizon. Highest, you'll probably see them is about 45 degrees, and that's not accounting for terrain. And so you won't have a whole lot of coverage. You know, you may get positioning information, you may not. Also, if you're in the Arctic and you are calling for help, your boat's going down, you're trying to get your crew into their survival suits, into their Gumby suits. You're trying to make sure the life raft is inflated and over the side. And the last thing you're going to do is pick up the radio and call for help, because you have a whole lot of other things to do in a very short period of time if you want to survive. So there's a whole lot of things that are going on here. You may have an EPIRB. If you're in an airplane, you may have an ELT. If you're out hiking somewhere, you might have a PLB. And each of those distress beacons is tuned probably to channel 406 megahertz. Now, I'm saying assuming that because the older ones aren't. The older ones may be on a couple of other frequencies. If they're on those other frequencies, your chances of getting help are very, very slim. If you're on 406 and your call gets picked up by Arsat, congratulations, help is on the way. The other thing about Alaska is Rescue 21 is very limited there. It's not the same system that we have down here. Now, if you look on this slide, yeah, it looks like there's a lot of coverage in this area. And you know what? Let's focus in down here, because I want to talk a little bit more about that coverage that's in Alaska. And so if we zoom in on this area here, so here's Raspberry Island, which is here on the map, and some of the other locations, you can see there's multiple towers there. So there is coverage, but this system is built differently than it is in the lower 48. And we'll talk about why that is in a second. But these nodes and links in the system are serial. So if one of these nodes go down, let's say this node right here goes down, or this link goes down, your rescue call may be picked up, but it may not be relayed to the sector. Okay. So when we get into Alaska, coverage is a lot different. If you notice, all that Alaskan coverage is down here. Oh, that's right, we're supposed to be talking about the Arctic, right? I mean up here? There's no coverage there. Okay. So part of what's going on in Alaska is this. So here's a Rescue 21 tower up in Alaska. It's on a high site. You can see the tower itself. You've got your generator. You've got all your equipment. There's your fuel bunkers there. Anybody see a road? Okay. They get about 12 feet of snow up here during the winter. High winds, so I can't bring in additional fuel. I can't drive up if there is a problem with the system. I might be able to get in via helicopter, but I don't know about you. I don't want to be in a helicopter in a blizzard trying to land up there on a high site. So when this node goes down, it may be down for quite some time until the weather clears up, until we can get someone up there, helicopter someone up there. If they're out of fuel, we got to get fuel up there. There's a number of different things going on that we need to be aware of. So in addition to this idea of limited coastal coverage, we're also dealing with just kind of some issues with the network itself. Sites lose power, antiquated relay network. And the result here is we're going to miss some distress calls. There's going to be longer surge times. There's going to be failed missions. And so when someone is in Alaska, when they're in the Arctic and they're in distress, it is a very serious situation. Okay. So maybe we should do something different. Just given the situation, maybe there is another solution or an augment to the current Rescue 21 solution. And so what we can do is we can look at something like SARSAT. So I mentioned the idea, you have an emergency beacon, you activate the beacon, there's a satellite possibly overhead right here. So there's some low Earth orbit satellites here. That's the really the SARSAT piece of this. So these satellites are able to pick up the emergency beacon and relay that information. Now they can relay it either to a local SARSAT location, or they can really kind of transfer that information over to the geosynchronous satellites and get that to a regional SARSAT location. And then help can be arranged from there. So this idea of actually using satellites to geolocate someone is not a new idea. It's an idea that's been around since the 1960s. As a matter of fact, in 1978, that technique was formalized. And so we know how to locate someone using a satellite. Okay. And again, I mentioned earlier this whole idea of if you have a beacon that's on 406 megahertz, it may be heard. And so it becomes, the question becomes, why can't we do this, something like this, with Rescue 21, to augment Rescue 21? And so that's what some of our peers are working on. And when I talk about this idea of doing Doppler localization, what we're getting at is this idea that you have a satellite flying overhead. You have a distress beacon here that's signaling. And what happens is that satellite is approaching, coming over the horizon, over the person that's in trouble, or over that signal source. It's going to hear that signal, and the actual frequency is here. But because of the Doppler effect, because that satellite is flying towards you at a high speed, it actually receives that signal at a much higher frequency. And as the satellite approaches, that frequency is changing. It's going down. When the satellite's overhead, you're going to get the actual frequency. So that's pretty much this idea of the time of the closest approach. This is where the person is. And then as the satellite moves away, continues past towards T1, it's going to receive the same signal but at a lower frequency. Okay. So typically, when you're using a radio, especially a software-defined radio, that Doppler shift is compensated for. And what we want to do is we want to use that Doppler information. And so about 2 years ago, some of our colleagues started working on this idea of doing Doppler localization. They came up with this 3-phase experiment that they want to do. The first phase being working with the reciprocal problem. Okay, so we know where a person is located. We know where they're transmitting from. And what we want to do is take a satellite of opportunity and see if we can use the Doppler information from that satellite as it passes overhead to try to estimate where that signal is coming from. So that's phase one. In phase two, we would like to do some sort of payload on a satellite and actually run the test that we want to do. So we have a satellite, it's coming overhead, we know where that satellite is, we don't necessarily know where the signal is coming from, and then we can compute where that signal is coming from. And then phase three is an implementation test. We want to put up multiple satellites and figure out how we can make all this work as a system. Okay, so with phase one, our colleagues started working on this idea of using FunCube. So a 1U CubeSat, it's transmitting at a known frequency, low power, much lower than someone who would be using a radio would put out. So if you're using a radio, you're probably putting out at least 5 watts on a signal. And what we want to do is use that transmitting amateur radio satellite, measure the Doppler curve, and then pinpoint the location. Okay. So here's one of our cadets standing outside the football stadium. He's got a field fox here with a external oscillator, so we're actually running a phase lock loop here. He's got his antenna. He's pointing at the antenna at where he thinks FunCube is located, and then measuring that Doppler curve. And so you can see here, these are all the data points that were gathered, and then we're able to interpolate a curve that mimics what we saw with SARSAT. So we can see that signal coming in, it's higher than, the frequency is higher than we expect as the satellite approaches, that signal goes down, and finally we get the carrier frequency here that FunCube is transmitting, and then as it passes, we see that signal go down in frequency. Okay. I do want to talk about one thing here, this idea that now we're doing this with just a single satellite, and we assume that we know where the satellite is. And because that satellite is moving as fast as it is, and we have some TLEs that are not updated, we're taking a guess as to where the satellite is. We could be off by a few seconds, and that few seconds relates to kilometers in terms of where the signal is actually being picked up. And so when they did the actual tests and did the analysis, they were getting results that were between 12 and 21 kilometers off. And so if we just knew exactly where FunCube was as we were doing the experiment, we could actually eliminate some of that error. And so when we talk about this idea of moving to phase two, of actually having a satellite equipped for this experiment and knowing exactly where that satellite is, we could actually figure out where that signal source is coming from. And so this idea of Doppler localization, like I said, the technique has been around since 1978. But what didn't exist in 1978? What? GPS, absolutely. So we didn't necessarily know where the satellite was. We were guessing. We were using the TLEs, and TLEs are not constantly updated. And so with this idea of GPS, we know where that satellite is. And so knowing where the satellite is and not necessarily knowing where the signal source is located, we could actually use the Doppler and figure this out. And, oh, by the way, we're going to have a higher power transmission. We're not looking at 0.3 watts. Again, we're looking at somewhere around 5 watts or better. Okay? Now, what that does for us is this. We often think of a search area as being a circle. So here's where I think that person's located, and if I just have a radius around them, I can draw a circle, and we should look somewhere in that circle. And what we actually end up is with something that looks more like an ellipse. And so being able to pick up that signal over a period of 6 to 7 minutes and grab samples and then do the computations, we can shrink this search area down. So that's the goal with phase 2. So actually having a satellite up with the equipment in it, running this experiment, it's got a lot of power to it. And so, if only we had a satellite. And so that's where Sea Lion comes in. This is a mission that we've been trying to run for several years now, for about 3-4 years. We've had some opportunities and some bad luck, but now it looks like we're going to be up no earlier than September 19th. And so we are going to put an SDR on this satellite and run that experiment. And so Sea Lion's going to be in a Arctic or a polar orbit, sun synchronous, at no less than 475 kilometers. These are the tracks that we're expecting to see. And I do want to point out that's the Northwest Passage. So that's a shipping lane that's been there. But this new one, this North Sea route, did not exist. But now that the Arctic is open up, we're starting to see that as well. Okay. So with our phase 2 research, what we're going to do is we're going to have a deck watch officer on the Healy, which is one of our Coast Guard icebreakers, on Healy with a radio simulating a distress call, and we'll be able to pick that up and use the Doppler effect along with GPS information from Iridium to locate the satellite exactly. So we'll be able to really do a good test here. Okay. And then phase 3 is looking at multiple satellites. So I'm calling that Sea Lion 2. It could be Sea Lion 2 as a 6U CubeSat along with Falcon Sat, or it could be a couple of 3U Sats. We haven't figured that out yet. We're trying to get this first one up off the ground. Okay. And we'll do the same thing. This is Sea Lion with its boom deployed. Actually, Captain James is probably going to talk a little bit more about that tomorrow, so I will leave that. But I do want to end by talking about some of the outstanding design questions that we have. So can we use a commercially available SDR? As I mentioned, this thing about a phase lock loop, that means we need to have an external oscillator. That external oscillator is going to help us deal with that drift from the Doppler effect. Can we use a vendor one, or do we have to use a purpose-built one? Can we implement this with our current quad monopole antenna? And lastly, and this gets back to Captain James's presentation tomorrow on the impedance probe, can we map space weather on top of this information that we're getting from these distress calls, so we have an idea of what's going on? Okay. Questions? Yes. Oh, from this system with one satellite, we estimate less than 1 kilometer. Other questions? Yes. For continuous coverage, we're going to need at least 3. Yes? We expect about 2 years. So this Sea Lion started out as a 3U CubeSat that was going to be at 179 kilometers. We were expecting to be up for 2 to 7 days, not in a polar orbit. And as I said, things kind of happened along the way. We lost that launch opportunity, picked up another opportunity that put us in a polar orbit. And so we're expecting about 2 years. Any other questions? Okay, I realize I'm the last person between you and dinner. I appreciate your time and attention and your questions. Thank you.
Thank you very much. All right, that's our last presentation for today. And as you heard, we have our networking dinner up next. Couple reminders about the networking dinner. First, in San Luis, and especially at that site, it can be breezy sometimes. So if you have a sweater, you might want to bring it. That's just for those of you who aren't used to San Luis weather. It seems nice now, but it does kind of get cold in the evening. The appetizers will come out about 6 o'clock, and then the main courses will come out after that. So, I'm not worried we're not going to run out of food or anything, but it's possible that we have to switch from appetizers to the main course earlier, depending on how many people eat all the appetizers. But there's not going to be any food issues there. Let's see what else. I don't think San Luis Obispo has enough Uber drivers for us all to take an Uber over there. All right, so my suggestion is to try to, if you're going to Uber, or if you're driving, try to carpool to help alleviate that a little bit. What am I missing? We start again tomorrow morning at 9 a.m. And I hope to see you all there tonight. Thank you.